Hello everyone, welcome to the GATE crash course conducted by the GeeksforGeeks. So in this session, we will discuss about the array and pointer, which is one of the most important topics in programming and data structure. Not only from GATE point of view, but array and pointer is also very important from if you are appearing for any company. Okay, but right now we will discuss this topic from GATE point of view. And before starting the topic, actually, before starting the this topic, so I will take 2 minutes and let me tell you first of all what's the benefit of this Gate crash course. Why you people have to take this Gate crash course? Okay, what's the benefit? So first of all, this course is having the duration of one and or more. This having the duration of 1.5 month maximum, even less than that. Okay, so in the time period of 1.5 month, actually, we are covering all the subject in this course, and we are covering all subjects means we are covering the five most important topics from every subject. We are covering five most important topics from every subject. Okay, like this is one of the most important topic, array and pointer in programming and data structure. And actually we are covering these topics, like this topic we are covering this topic in its entirety, means we are covering these five topic complete way, in complete way, means once you have taken this topic here in this lecture, in today's lecture, then you do not need to go anywhere else for array and pointer. Everything will be covered, every point about array and pointer will be covered in this lecture. In this 2 hour lecture, everything will be covered, and here itself we will solve the questions from Gate. Not only me will solve the question, you people will able to solve the questions, because I will share all the necessary information related to this topic. Okay, so what I'm telling you about the complete Gate crash course is, in this complete Gate crash course, from every subject we are covering five most important topics we are covering from every subject. These are the five most expected topics, I have to say, which can come in Gate 2023. Okay, so there is a very high probability. See, we can talk about the probability only. There is a very high probability that the question will come from these five topics, and we are covering these five important topics in its entirety. Like, I'm covering array and pointer in its entirety in this lecture. Okay, and this will go with the complete series. So what's the benefit of this series? There are two types of students who can take benefit from this series. One is who say that, sir, we cannot, we are not sure that we can crack the Gate exam or not. Okay, one student is those who are saying that, sir, we are not sure whether we will be able to crack the Gate exam. So if you are taking this complete series, one thing is sure, you will be able to crack the Gate exam, because you are covering the most important topics from every subject, which is having very high probability to come in the exam, and you are covering all these topics in its entirety. So you are able to solve the Gate questions after taking these lectures. So definitely you are going to clear the Gate exam. One thing we are ensuring this by this series, actually. And second thing is, if you are already serious candidate about the Gate and you have already completed the syllabus, still this series is beneficial for you. Why this series is beneficial for you? If you have already completed even you have completed the complete syllabus and PYQs, maybe you right now you are taking the test series. See, we are covering five most important topics, so you will be able to revise these most important topics. Okay, you have to revise. Revision is very important in Gate. So if you right now revising the complete syllabus is not a good idea. I don't think so. At least you can revise these five most important topics from every subject. So both type of students are getting benefit. One is who are beginner, that is going to crack the Gate exam with this complete series. Another one is the I will say, okay, who are studying from long time and they are serious about Gate already, and they have covered the syllabus and revised the syllabus, and oh, they are taking the PYQs. Even they completed the, maybe they completed the PYQs also. Now they are going for test series. For them also, this can be a revision for most important topics. Okay, so this was all about this complete series, so that you can connect. And if you want to register for this series is free. The complete schedule is given on our website. The link is given in the description. You can register there. This series is completely free for you people. Okay. Okay, so this was about the GATE crash course. Now let me move to today's topic, that is array and pointer. So let me promise you one thing before moving on. You will be able to solve all the GATE questions after taking this complete lecture. Even we will solve the GATE question here itself in this lecture itself. I will tell you all the concepts, all the important concepts I will tell you here in this lecture. There will be nothing left. You do not need to go anywhere else after this lecture regarding array and pointer. Okay, we will cover each and everything. And I'm sure that the people who are setting the paper, they cannot ask the question out of these points which I'm going to share with you, because I'm covering all the points. Actually, I'm covering all the points, all the logical points I'm covering. After that, what they can do is they can just use these points, and they can make the questions out of these points only. Okay, so they make set the tricks out of these points only. Okay, but one thing is sure, we are going to cover each and everything now about the array and pointers. Okay, so good evening, Nishu. Good evening. Okay, I'm going to start this topic now. So, if you have any doubt related to GATE crash course or related to GATE itself, uh, any means you are preparing for the GATE exam, any doubt, if you have general doubt, even you can ask me. Otherwise, I'm moving on this topic, array and pointers. Okay, I'm moving on. So I hope this screen is visible to you. I'm going to cover from very basic. I'm assuming that you don't know anything. I'm assuming that you don't know anything. And even you know, I have challenges for you. Okay, I have challenges for you if you know many things. Okay, if even you don't know anything, still you can continue with this class. Prerequisite is zero, nothing, none. Prerequisite for this lecture is none, and you will be able to solve the GATE question after these two hours class. Okay, even during the 2 hours class, we will finish this topic. Okay, so definition again, starting from very basic definition. What is an array? So array is a collection of similar items. Similar items. Either that will be all integer, all characters, all float. So that will be a collection of similar items which stored in contiguous memory locations. Contiguous memory locations, one after the another. Okay, it's not like one element is at one location, 1000 location, and another element is at 2000 location. It's not like that. Okay, so they are in continuous memory location, maybe 1000, 1001, 1002, like that. Contiguous memory locations items are stored. Okay, so this is the definition of the array. And we have actually two type. We have actually 1D array, 2D array, 3D array, 4D array. You can make any type of array. So let's start with 1D array. 1D array. So let's suppose we have an array A which is having, I don't know, 5 elements. Okay, this is the size of the array. We know these things actually. This is how we declare the array. This is the integer type of array. This is the name of the array. And if let's suppose I'm storing some elements here, 10, 20, 30, 40, 50. I have 5 elements in the array. So 0 to 4 locations are there. So our array is starting from 0 location going up to 4, and we have stored these 4 elements in this. Let's suppose the starting address is 1000. Then if this is an integer type of array, and let's suppose integer is taking 4 bytes. Let's suppose integer is taking 4 bytes in memory to store. One integer is taking 4 bytes to memory. So this is the first element will be at 0th element, I say, will be at 1000 location. Let's suppose this is the starting address of the array. Then second will be 1004, third will be 1008, 1012, 16, Okay, so this will every time I'm incrementing with 444 because every element is taking 4 byte to store. Every element is taking 4 byte to store. Okay, so this is how our array look likes in memory. Okay, so the you can see that okay, elements are stored in contiguous memory locations. After 1000, then the next element is immediately after the zeroth element. So first element take 4 bytes. After that, the second element start at 1004 and goes up to 1007, and third element start, I mean the second element start, if I talk according to the index, that start from 1008 and goes up to 1011. Okay, so if I want to access, let's suppose one element. Okay, I want to access, if I ask you, this is our array and I want to access this element, I want to access, okay, let's suppose this third element in the array I want to access. This is this element I want to access actually, and which is at third position. Okay, 40 I want to access. So how actually array access the elements is, so that is starting from 1000 actually. This is the formula we use to reach to the address of a particular location. Okay, if you want to access an elements in 1D array, your compiler use this formula. Okay, how this formula works is simply, okay, you can see directly here that this the element at third index is actually is 40, and which is at this location, which is at 1012 location. Okay, but how compiler actually access this location is simply that take the base address of the array. So base address we are assuming is here is 1000 plus, and what is the index which is we are searching for? 3 is the index. And what is the size of each element? We are assuming that the size of an integer is 4 bytes. Okay, size of the integer is 4 bytes. Okay, simply 1000 plus 12, so that is 1012. At this location this element is present, so the address of this element is calculated using this formula actually. Okay, this formula by your uh, by your system. Actually your system is calculating, or your compiler is calculating this address to access this element. Okay, so okay, any doubt in this, please ask. Any doubt in this, please ask. So I just want to know if I'm able to connect with you people or not, so that I will pick the speed actually according to you people only. I need to pick the speed, and but I need to go with you people, so I need to see, okay, with all of you. So, no doubt. Okay, does it say no doubt? Clear. Divyanshu say no doubt. So does it say, okay, sir, the whether the address start with 1000 or anything, that can start with any address. That can, your array will can start with any address. Actually, whenever you are taking a space in memory, so this is the job of the operating system actually, that provides some space, which is free space in RAM, that is provided to your array. Okay, but I don't, we cannot say that okay, that will always go to the 1000 location. Okay, no, this is what we are assuming. We are assuming that our array is starting at 1000 location, because this remains easy for us to make all these calculations. If I say this, even if you will find, if you will open the C compiler, or even you can open the C compiler in the back end, and okay, let me change my screen format also, so that you can see the complete screen. This one, yes. Okay, so if you will see the memory addresses, they are in hexadecimal. They are not even in decimal. They are in hexadecimal. Okay, you will see the memory location like A1 to B, C, A to H, like that. Okay, so you can take a pointer and you can check out the address at that pointer, or you can check out the address of any variable. You can check out by compiling it, you will find out the address in hexadecimal. But here we are taking starting address easy one, so that we can calculate the everything in easy format. Okay, okay, so this is clear now. Let me now ask a interview based question now to you people. Let's start from the first slide. I will ask the interview based question from you people. Usually this if somebody is asking question, they will ask you question like this. This is a good question actually for interview. Many times I also use at GeeksforGeeks. Why array indexing starts with 0? Why array indexing starts with 0? I said you that okay, this was our array. Even I mentioned you that okay, let's suppose I'm having an array of name A which is having 5 elements. So the indexing is I started the indexing with 0. I started the indexing with 0. You will find out most of the languages is starting the indexing of the array with 0 only. Okay, if you will see C++, Java, even Python, all are starting with 0. All are starting the indexing with 0. Why they are not starting with 1? As a human being, I am comfortable with 1. I'm not comfortable with 0. As a human being, counting from 1, I'm comfortable with 1. I'm not comfortable with 0. But still, all you will see all the popular languages using the indexing starting from 0, array indexing starting from 0. Why they are starting the indexing from 0? Why not they are starting from 1? Even when I write a of 3, actually if you access this element, actually see, you are accessing the 1 2 3 fourth element. You are accessing the fourth element. Okay, but which is at the third index, because our indexing is starting from 0. Okay, so this is a good question. Why array indexing start with 0? Can anybody tell? Can anyone? This is a good interview based question actually. Good question. Anyone? Any idea? Any idea? Anyone with any idea? Okay, so let me tell you. See, if you are starting indexing from 0, you are using this formula to access location of one element. Simply in this formula, what you are doing is you are just simply starting from the base address. You are starting from base address. Let's suppose this is starting from 1000. Okay, you are starting from here. Wherever you want to go, let's suppose I want to go at this location. I want to access this element. What I need to do, I need to pass 3 elements. I need to pass how many elements? 3 elements. So what I do, I take the base address and I say that okay, I need to pass how many elements to reach to this location. To this location, I need to pass 3 elements. So I simply pick this index. I say that I need to pass three elements, and every element I just multiply the size. Number of elements are 3, and I multiply it with size of each element. Size of each element. I don't know what is the size of each element. This can be character array also. Okay, let's suppose this is character array. Then the size of each element is, let's suppose, 1 byte. 1 byte. Okay, actually the size of character, integer, float, this depends upon the compiler, actually on type of compiler you are using. Okay, so usually in maximum compiler, character takes 1 byte, and integer nowadays, the new compiler is taking 4 bytes. The old one, if you will check out the old one like turbo C++, in that they were using 2 bytes. They were using 2 bytes for integer to store in memory. Okay, but now the integer is taking, most of the compiler is taking 4 byte. Okay, float is taking 8 bytes. Okay, so that depend upon compiler to compiler. Okay, so simply what we are doing, we were multiplying with the size. So what we are doing, see what we are doing, we are jumping three into one. This much locations we are jumping. This much locations we are jumping. So this locations we calculated. This much locations we calculated from this thing, or I say index into element size, and add it to the base, and we get this address. Okay. So this is what we were doing if we were doing the indexing from 0. If we were doing the indexing from 0. But if we are doing the indexing from 1, if you are starting the array from 1, see what you need to do. You need to change this formula. If I'm doing the indexing from 1, let me draw the array here. 1, 2, 3, 4, 5. Okay, and I want to access, let's suppose, this element again. This element I want to access. So now this element I want to access, actually a of 3 is this, because indexing is starting from 1 here. So I want to access this element. Okay, earlier the, there were three elements in front of this particular element which we were searching, but now we have two elements. Okay, so what actually you need to done is you need to generate the how you will calculate this thing. Actually, you need to take the base address, you need to take the index which you are searching for. Index is 3, index value is 3, but you cannot take 3 here because you need to jump two elements. You need to jump two elements to reach to this location. To You want to access this element and you need to reach the starting address of this element. You need to jump these two elements. So index value is 3. Actually, you need to jump index minus 1 elements. You need to jump index minus 1 elements, and you need to multiply it with the element size. You need to multiply with the element size. Okay, so this is what you are doing. 1000 plus now 3 minus 1 into element size. Let's suppose 1 byte. Okay, so you can see here 3 minus 1 is 2 into 1 plus 1000. So this is 1002. So you will find out this element at 1002. This was at 1000. This was at 1001. This is at 1002. If I'm taking one byte, I'm taking character array. Okay. So important point here is that see, whenever you are using array, whenever you are using the array in your program, you will be notice that you are using the array element so many times. You are using the array element so many times. You put the array inside the loop. You put the array inside the loop. You keep accessing their elements by putting I here. You keep accessing the elements of the array. See, you access the array elements again and again and again. Thousand of times you access the array elements. Even you have 10 elements in the array, but you access the elements so many times. You access the even same element so many times. So every time the compiler need to process this thing, and every time the system need to process this thing, this formula. Okay, if the indexing is starting from 0, I will say, let me erase all this. If the indexing is starting from 0, then you will use this formula. But if indexing is starting from 1, you need to use this formula. Every time you are accessing one element, every time you are accessing one element. Okay, element size. So here you can see earlier, if we are using indexing 1, then you need to perform one more operation, one more extra operation you need to perform every time. Every time you need to minus 1 from the index. Here you were not making any minus. Okay, so unnecessarily every time you access one element inside the array, you need to perform one more operation. You will consume one more CPU cycle. So it's better to use zero indexing, which do through which we do not need to consume one extra cycle to minus 1 to perform this operation, index minus 1. So this is the reason actually why the array indexing is start with 0. Why maximum compilers support this thing. Okay, and why compiler do not support one base indexing. Okay, although in exam they can ask you the question from one base indexing. Okay, so any doubt you can ask, otherwise let's start with the question now. You people have enough information with you to solve this question. You have enough information with you to solve this question, and I want that you people please try it yourself, and believe me, you people can solve this question. Okay, this is ISRO 2009 question. So if you will solve it yourself, that will benefit you more as compared to I will solve it for you. Try it. Try it. Everyone, please try it. The most important part is you are trying or not. Otherwise, you will find the solutions over the internet. Okay. Lots of information is there. But the only difference is you are trying or not. You are here with me. You are wasting your time with me. You are not going to the Netflix and enjoying at this time. And you are spoiling your life with me. So it's better at least solve this question. Don't sit idle. Please try. Share the answer in the chat box. Everyone, please. So we get one answer already, but let's wait. Ravish also already given one answer. It's okay. You please believe on you in yourself and keep trying. Okay, what other people are doing, let them do that thing. They have their own life and they have done their own practice already. So please try. And if I am disturbing you people, I am speaking and again, put me on mute. Okay, put me on mute also. You can put me on mute if you think that I am disturbing. Deep also say the same answer. Okay, Digit also say the Digit say different answer, that is A. Okay, we get two different answers. That's great. So wrong or right doesn't matter at this time. That will matter in the exam. So let's check out. So this is, we have one dimensional array A. The indexing is starting from 1 and going up to 75. Okay, see, the indexing is starting from 1. Okay, each element is a string that takes three memory words. So the I can say that the size element size is 3 words. Okay, word actually can be word is the name given to one location in memory. Okay, one location in memory. So array is stored at location this is the starting address. This is the starting address they provide us. Starting address, this and the starting address of this element. They're asking about this element. Okay, simple. So we know that we have a formula, but here you need to apply the formula for one base indexing. Okay, you should not cram the things. If you will cram, you will not be able to solve the ISRO and GATE questions. So simple, we are starting from this address 1120. Okay, and we started from this address. How many elements we need to jump? We need to find the address of this element. We need to find the starting address of this element. So we need to jump 48 elements. How many elements we need to jump? 48. Directly you can say even 48. Otherwise, what you need to do, if you are using the formula 49 minus 1, 49 minus 1, total elements you need to jump is 48. And what is the size of each element? The size of each element is 3 words. So multiply with 3. Okay, so I just put it according to formula, index minus 1 into element size and plus base. So you can add it. So this is actually 48 into 3. And what is 48 into 3? I think this is 114, and this is 4 and 6 and 2 and 1. So this is the right answer, 1264. Let me check. Yes, C is the right answer here. So simply, even see, you do not need to cram any formula. If you will cram the formula, believe me, you will not be able to solve the question in GATE exam. You need to understand actually what we need to do. We are at this array is starting from this location, and array is starting from this location, and every element is taking 3 bytes. Let's suppose 3 bytes, 3 words. This is the size taken by every element. How many elements we need to pass to reach to the 49th element? Indexing is starting from 1. How many elements are ahead of it? 48 elements are here. Simply you can even replace this thing with 48, and every element is taking three words. So multiply with 3. So this much memory we will pass on. We need to pass this much memory. So starting from this location and pass on this much memory, so we will reach the starting address of this will be 1264. Okay, so C is the right answer here. Don't worry, we have lots of questions related to ISRO and GATE with us. So let's move to the now 2D array. So again, I will say please don't cram anything. So let's talk about 2D array. In 2D array, 2D array is just a It's just like a matrix only. Okay, so it's a matrix only. 2D array is a matrix, is a 2D array. Okay, and we can store this matrix in two ways, either row measure order or either column measure order. In row measure order, how we store this matrix into our computer is, we take actually row number 1, this is row 1. Okay, this is row 2, and this is row 3, and this is row 4. So actually, either this is 1D array, 2D array, all will store in contiguous memory location. All the array will store in contiguous memory location. Okay, so this matrix will store also in contiguous memory location. So if we are using the row measure order technique to store 2D array, or I will say this matrix is a 2D array actually. So you will store row 1 first in memory. After that, immediately after row 1, you will store the elements from row 2, all these elements actually I'm talking about, then row 3, then row 4. Okay, so or all the rows, row by row you are storing, that is row measure order. If column wise column you are storing, column wise column, you store first column, then you store second column in memory, like this. Like you store the first column, then you store the second column elements, then you store the third column elements, then you store the fourth column elements, like that. Then you are using the row column measure order. How you are storing the elements in memory? So that is two way you can store. One is row measure order, another one is column measure order. Okay, so now let's see how we access the elements in the array. Okay, in 2D array, how we access the element. Okay, so let me take an example here. Again, I'm starting the indexing from 0, 1, 2, 3, 4. So we have five columns here. These are columns, this is row, 0, 1, 2, 3. So we have 4 rows here, 0 to 3, 4 rows and 5 columns. Okay, let's suppose I want to access this element. Let's suppose. Okay, so this element is actually in the array is second row, that is in second row and third column. Okay, so according to index I'm talking about. Okay, according to index I'm talking about. So at this location is 2 and 3. I want to access this element. So what is the address of this element? What is the address of this element? See, we know that in row measure order, first we store this row, first row, then we store second row, then we store third row. So these three elements, 1, 2, and 3 elements will be stored before this element. Okay, so I can see that I am storing complete two rows, and some of the elements which are present in the same row in which this element is present, and these all elements will come before this particular element. Okay, so if somebody asks me the address of this element, what I need to do, you see what I need to do, think logically. I need to start from the starting address, and I need to start from the starting address of this array, and I need to pass all these elements. 1, 2, let me write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. What I need to do? I need to pass 13 elements. I need to start from the base address, and I need to multiply this 13 with the size of each element, and that's it. This will be the base address of this element. That's it. Okay, so the important, this formula is just like 1D array, but calculating this 13 is little for calculating this 13 we need to perform some more operations. Actually we are calculating 13 with like this we are calculating. How we are calculating? Simple. See, simple how we are calculating. How many rows are here? Let me calculate it. 2 rows are here, and in each row how many elements are here? 5 elements are here. So total number of elements were 10 in both the rows. 10 elements were there, plus how many elements were here? 3 elements were here. Simple. Now let's suppose base address is 1000. Let's suppose base address is 1000, and plus 13 we get from here. We simply skip the elements in the row which are coming before this element, and some of the elements are also in the same row. Okay, three elements are there, into whatever comes here, I multiply the size. Okay. Okay, one more thing I want to tell you here now. See, logically you need to think, you do not need to cram anything. We are human beings. If you will we will cram, we will forget. One thing is sure, we will forget. Even I'm prime minister, I will forget, because I am a human being. Okay, so please understand this formula now. Please understand this formula. What this is trying to do is, see, you people tell me. Okay, this 2 is telling me number of, if I say number of rows, how many rows are ahead of this. Okay, this is telling me number of elements. If you find that I'm telling something wrong, if you are not able to connect with me, please let me know in the chat. See, this 5 is telling number of elements in each row. In each row, see how many elements are there. 5 elements are there in each row. 5 elements are there in each row, and number of rows are 2, which are coming before this element. Number of rows are 2, and this 3 is telling me number of elements which are coming before this element in the same row. Okay. Okay, so what we need to do is, now we need to find out, okay, how we will get these three information. They will provide us the base address. We do not need to bother about the base address. We do not need to bother about the base address. We do not need to bother about the size. They need to provide this thing in the statement itself, question statement itself. Okay, the only thing is that how we will get these three information, these 2, 5 and 3. See, we will get this information from array structure itself. Array structure. So let's suppose our our array is of this size, m into n. So if I compare this array with this matrix, so m is the number of rows. So whichever come first, that is row, and whichever come later, that is column. Okay, so how many rows are here? 4 rows are here. 0, 1, 2, 3. 4 rows are here. M value is 4, and n is the column. How many columns are there? 0 to 4. 5 columns are there. This is telling the size. This is telling the size. This is not telling the index. Okay, this is telling the size. Total elements into, how many elements are there in this matrix? 4 into 5, 20 elements are there. Okay. Okay, and what we are searching, we are searching the accessing the element at I and jth location. So let's suppose if I compare it with this, I am searching for this element 2 and 3. So I value is 2 and j value is 3. Okay, I'm trying to generalize this formula. Actually, I'm just trying to generalize this thing. So if now you can tell me, you people tell me, I will not tell. You people please tell me, what is this 2? What is this 2? This 2 is I, j, m or n. What is that? What should be the 2? What should be the 2? What should be the 2? This 2 should be this value, or the size of the array, this value or this value. So can you people tell me in generalized format? Okay, so this is the base address. 1000 is the base address. Base address plus, what should be this 2? How I will know that how many rows are coming before this element? How I will know this thing? How I will know this thing, that how many elements are coming, how many rows are coming before this element? How many rows are coming before this element? How I will know this thing? Who will tell me? Who will tell me? So I will tell me, j will tell me, m will tell me, or n will tell me? Please write in the chat. Who will tell me? Who will tell me this 2 value? Who will tell me? I. Does it say I? And you are right. So this value itself will tell me how many rows are ahead of this element. Okay, how many? Why this is happening? Because array indexing is starting from 0. So definitely, if I'm accessing the element in second row, if I'm accessing an element in this row, second row, there will be 2 rows before it. Okay, so this is I actually. This is I. If I'm generalizing, okay, into what will be this 5? 5 is telling number of elements in each row. Number of elements in each row. So number of elements in each row, number of elements can be determined by Number of columns, how many columns are there, the columns I can get here from here. N is telling me about the columns, n is telling me about the number of columns in each row. That will remain same, that will remain n only. Okay, so 5 I will get from here. See, n value is 5 here, you can even compare, n value is 5 here. Okay, plus now what is this 3? How many elements are just in front of, just before, come in the same row, just before coming to this element? So these I can find out with this value, okay, means with j value. So this, how many columns I'm skipping, how many columns I'm skipping, 1 2 3, so 3 elements will be there. So this is j actually. Okay, and after that simply I will multiply with the size. So this is the same thing actually. I'm explaining this formula only because you are going to solve many questions based upon this formula. I don't want that you cram this thing, because if you will cram and if there will be a little modification in this formula, then you will face problem. And if you understand this thing, if you understand, please write +1. If you understand, please write +1. Please write, so that I can move on. Then we will talk about, I will ask you one question, one very interesting question I will ask you. Please write in +1 if you know, if you understand this thing, how this formula is working. Please write. Okay, mine say +1. Does it say? If you don't understand, write -1. No problem at all. I will be able to know that. Okay, where is the problem is coming. Okay, so if you able to understand, can you tell me, if my array is starting from 1, if indexing is starting from 1, not from 0, this formula is for 0 indexing. This formula is for 0 indexing. But in GATE exam, they will check whether you understand the concept or not, or you are simply cramming the formula. Okay, they will check, they will try to find, do you understand how this formula is coming? They will ask you. If the indexing is starting from 1, I will share the question also like that. If if the indexing is starting from 1, what should be the formula? Please write in the chat. Actually, the difference will come here in this portion. You can write simply this portion. Size will remain same for the element, base address will remain same. This thing will change. So what will be the change in this? If indexing is starting from 1, please write in the chat. If indexing is starting from 1, what should be the formula? Believe me, see, you need, if you will follow me, I will give you guarantee. I will share you many questions now. After this, I will show you many questions. You will be able to solve all the questions yourself. That is important. That is, I'm solving the question. That is not, that will not make it that much impact actually. So if you really want to crack the GATE exam, you, after learning the concept, you yourself should be able to solve the question. You should feel comfortable. And if you will think logically here, then you will be able to solve. So we get some answers. Let me check out. So, okay. And Ravish, you are doing great actually. And again, right or wrong doesn't matter at all. Important thing is you are trying. Okay, so I'm telling the same thing now. So you can check out in the. So let me write. Okay, you can check out otherwise the chat box also. Let me write over here. Pen is here, and if I'm using the indexing from 1, see, indexing from 1, then the formula will be I minus 1 into n, okay, plus j minus 1. So how that is coming? How that is coming? Very easy actually. If we understand, then very easy. See, only this is the only thing we need to worry about. And you know what is this? Total. What is this total? This is telling me total number of elements. Let me write total number of total. You must understand the meaning. Total number of elements which is coming before this element. We want to access this element. We want to access any value of I and j can be there. We want to access this element. Let's suppose this element. So how many total number of elements are coming before this element? So this statement is telling me, this thing is telling me. Okay, now let's go a little bit more deep. To find out total number of elements which is coming before this, I need to count how many rows are there. And if I multiply number of rows with number of elements in each row, then I will get total number of elements in these two rows. So actually this thing is telling me number of elements in rows, all the rows, I say all rows, which is coming before 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 our element, actually before this row, all the rows, I'm covering these elements. Actually here I'm covering these elements. After that, what is j is telling me number of elements which are covering this area, number of elements here. Okay, so now if I'm starting from 0, then number of rows which are coming before this 2 is 2, which is already tell by this 2. Okay, if I'm trying to find out this element, so number of rows which are coming before this element is how many? 2. I is telling me. But if I'm starting the indexing from 1, 2, 3 and 4, then number of rows coming before this element 2. Now 2, see for this actually, let me little bit make a space here. This is going little meshy. Like this. This is very easy. Very easy. 1, 2. This is the 0 indexing. This is 1th indexing. Now in 1 indexing, where is this element? This element is 2 and 3. This element is this actually in one base indexing. Okay, so now how many rows are before this? One row is this, but the I value is how much? I value is 2, so I need to make minus 1 here. I need to make minus 1. That's why we are making minus 1 here. How many rows are here? 1. Number of rows is 1 before this element. Before this element, number of rows is 1. Okay, and similarly, how many elements are ahead of this in the same row? 2 elements are there, but here is 3. But here is 3. So I need to say 3 minus 1, or I need to say j minus 1. I need to say j minus 1. Okay, so this is how we are getting actually. And Mehak also say the same answer. So this is the idea. If you still have doubt, please ask me. Please ask the question. Otherwise, can you people write the formula for column measure order yourself? Can you share the column measure order formula? One more chance you have now with you. If you are if you are not able to understand now, try one more time and try to find out the formula for column measure order. Column measure order. Believe me, you can find out. That is easy for you people if you understand this thing. That is easy for you people. In column measure order, you know that first we store this column, then this column, then this column, like that. And if I want to access, like, the indexing is starting from 0. Okay, we are assuming that indexing is starting from 0. Let's suppose you want to access this element. So how you will access 2 and this element? So you need to pass how many columns you need to pass? 1, 2, 3 columns you need to pass, and 2 elements more you need to pass to reach to this element. Can you write the formula? We need to start from the base. Base will be remain same, size will remain same. This thing will change. Can you think yourself? That is important. Can you think yourself? I will give you many questions related to this. These questions, that question will not be mine. That questions already coming in GATE exam or ISRO paper actually, and you people will be able to solve if you are giving me this formula. So see here you can see this was telling how many this I was telling number of rows. Now you need to find number of columns. So this must be j is telling you uh, j is telling you this is j, this is I. Okay, so how many columns you need to pass? 3 columns. This value is get by j. You people are right, you are writing right in that in the chat box. Number of elements is n is c. Some people are writing n, no, yes, some people are writing n and many people are writing m also, m. And how many elements are there in one column, how many elements? One, two, three, four. That depend upon number of rows. How many elements each column have? How many elements each column have? That depend upon number of rows. That depend upon number of rows. So m will come here. Okay. So in place of n, m will come. Now you need to pass two more elements. So who will tell me these two elements? This two will tell me directly. This I will tell me. Simple. That's it. And multiply with size, add the base address. So this is the answer. You already tell me, and you people are right about this. And here is the questions for you people now. Please try it. This is the level you need to achieve actually. These are the real questions you need to solve. I have already taken the examples and question from my side. Let's take the question from the GATE and ISRO now. Let's see whether we are able to achieve this level or not. So not here also indexing starting from 1. Indexing is starting from 1. And this RMO means row measure order. So one hint is already given, but you cannot use this formula because the indexing is one base indexing. Then you already provided me the formula for one base indexing, that was I minus 1 into n plus j minus 1. You already provided me this formula into size for one base indexing. So base address they provided us, that is 100, and I they don't provide I and j. So this is I minus 1, and n value is, this is m, this is n actually. So we know that actually, do not need to remember this thing also. We know that this is the actually number of elements we are passing on. These are the number of rows we are passing. In each row, how many elements are there? N elements are there. Means 15 elements are there. Okay, and after that, these are the elements which are lying in front of the element, this element actually. Okay, so that is I think j minus 1 only, and the size they provided of each element is 1. So this is again 100 plus, this will be 15I minus 15. I multiply this here, and plus j minus 1. I open it, and this is multiplied by 1 only. So this is 100 plus, this is actually 15 plus, do I make any mistake? So j, so this is okay, no, so this is 15 I, and plus I can say j minus 16. Okay, so you can minus this 16 from the 100. So 15 I plus j plus 84. Okay, that's it. That's it. So A is the right answer. Okay. So I'm moving on. I hope this is clear. if you want any explanation in this, I can you can ask for that. Otherwise, I'm moving to the another question. So A is the right answer. Please try this one. Keep trying. Please try this one. You have already done enough to solve these questions. Okay. These are all GATE question and ISRO question. You will try, please solve yourself. So we have two-dimensional array with us, this, and we are using main memory. Byte addressable means they are trying to tell that, okay, memories, one word is taking, actually character take 1 byte, we are assuming this thing. And the array is stored from the starting address is 0. We need to find the address of this element actually. Okay, so we already know the formula. So that is base plus I into n plus j into size. Okay, so base is 0, and what is the this is this is j, 40 is 40 into, and this is, we know this is m, this is n, so this is 100, n is 100, and what is j is 50. Okay, into 1, so this is 4000 plus 50, 4050, this is 0. Okay, so B is the right answer, and you people are right. So let's move to the next question. That is 2014 ISRO CS 2014. Please try it yourself. Please try it yourself. So again, this is the row measure order, and indexing is starting from 0 and ending at this location actually. So number of elements, how many that will be? 101 and 101. Okay, so number of 0 to 100, 0 to 100. Okay, and we need to find the address of this element. So starting address is 0, so 0 plus, I'm using this formula which is given downside. So base address is 0. Now what is the I value? I value is 6. This is I, this is j. So I 6 into what is n value? This is n, this is m. So 101 plus what is j value? J value is 10. Okay, and into what is the size? 1 bit. So what size is 1 bit? Okay, for every pixel. So that's it. So 606 plus 10, so that is 616. So D is the right answer. Yes, Mehak. Any doubt? You can stop me. Okay. Okay. So let's move on. Otherwise, please keep confirming this thing also if the things are clear to you. So you can take a snapshot and you can solve it yourself. I hope you people can do it. So the answer is C here. You can check out. I'm not stopping right now here. So you can, I believe you people can solve it. This is ISRO 2020 question. Definitely you people will be able to solve, I hope. And so this question is asking actually, okay, if I'm using row measure order and column measure order, okay, to store an array, so which will take if I want to access one element, so which will take more time, who will take more time complexity? Okay, so I have an array, I'm storing in memory in row measure order, and the same array using column measure order. He's saying that if I want to access one if I want to find this thing, if I want to multiply both the matrices, I want to multiply both the array, which will take the which will take more time actually nobody will take more time, both will take same time. Okay, this do not depend upon this thing. Okay, both will take same amount of time. You know that both are using a formula to calculate, and both will take constant time to calculate something, and both will take same time to multiply the matrices. Okay, so this is independent of the storage scheme. You can check out this question in more detail. People can do it. That's why I'm jumping little faster. So D is the right answer here. You can check out. You can take the snapshot and you can check out it. I hope I definitely know you people can do it. So okay, that I have some very important points actually to share with you people. That's why I'm moving little fast now. These are very important points. First point is that, so this is our array, okay, which is having 5 elements. So you people know this thing. This is the name of the array. This is the size of the array, and this is the elements inside our array. Okay, we know this thing. Now this is our second array, which is having 5 elements. You people tell me, can I can I do this thing? Can I store the array 1 in array 2 with assignment statement? Yes or no? Yes or no? Please write in the chat. Please write in the chat. I have two array. One is array 1 in which I have 5 elements 1, 2, 3, 4, 5. I have second array, array 2. The size is same. Size is also 5 there in array 2. Can I copy the element of array 1 into array 2 simply by making the third statement which is written on the screen? Actually, we cannot do this thing. We cannot do this thing. Okay, we array name actually this actually store the address. Array name store the starting address, of the array actually. Okay, so let's suppose this is our array in memory 1, 2, 3, 4, 5. Okay, and this is our array. The starting address is, let's suppose, 1000 and so on. Actually, I don't know, so on. So this started first element address is stored inside the in the name of the array. Name of the array actually keep the starting address of the array itself, we can say. Okay, because the starting address, the address of first element will be a starting address of this complete array. Okay, so this is storing the address. Okay, and we cannot copy the elements like this. We cannot copy the elements like this. This is having the address. This is having the address. ARR1 is the name of the array, and name of the array store the address of the starting address of the array. That store the starting address of the array. Okay, name of the array. Okay, so we cannot copy the elements directly inside this. So this is one important point you need to know. You can verify this thing in online C compiler. Even you can execute it side by side. I'm not going there because we don't have time for that. I have lots of important things to share with you. So wrong, this is not allowed. Second thing, can you people tell me? Okay, so second important point is that array name points the base address of array. So if we will print the if we print the this array, actually if I write, okay, array 1, let's suppose this array, so this will print the starting address of the array. Okay, so array name point to the starting base address of the array. That will point to the base address of the array. It's like that only. Okay, this is, let's suppose the starting address of the array is 1000. So this name is given to this location, which is having this starting address of the array. This is our array which is starting with this location. Okay, and this is our array. Okay, so simple, same thing we have already discussed. Okay, another thing, very important one. So all these statements are same, all these work in the same way. So if I write a of I, if I want to access ith element, I can access it like this also. Value at, its mean is that value at a is telling me the base address and how many elements I need to jump, I element I need to jump. and this is same as this is value at operator. Value at. Okay, so value at I plus a. This you can see, you can just interchanging these two things. This will not make any impact. This is actually whenever, let me tell you, whenever you want to access some element like a of 5, you want to access this element, fifth element in your array, 0 1 2 3 4 5. Okay, so you want to access this element, then actually the compiler converts this statement into this statement. Okay, and a address, let's suppose this is our a array which is having the base address 1000. I say that array name store the base address 1000 plus 5, you will reach to this location, you will get the address now, address of this location, and this is telling me the value at this address, so this is 1000, this is 1001, 1002, 1003, 1004, and 1005. So at 1005, value at 1005 is 5. I don't know what is the value here, so let me store here, I don't know, we can store 50 maybe. So value at 1005 is 50. Okay, so let's suppose every element is taking more than 1 byte, then the locations will be like this, 1000. Let's suppose every location is taking 2 bytes. Okay, so 1002, 1004, 1006, and so on. Okay, and so fifth element will be at the location of 1010. So in that case, actually, if you will add 5, so that will not, what that will do is actually, so if you are adding 5, actually that will add 5 into 2. That will add 5 into 2. Total size of the elements. Whenever I will add 1 in 1000, I will add 1 in 1000. So that will not be 1001, that will be 1002. Okay, that will be 1002 if every element size is 2 byte. If every element size is 4 bytes, then starting address is, let's suppose, 1000, and if I'm adding 1 in this address, I'm adding, so this is not 1001 I will get. If every element I'm adding 1 means I'm telling that, okay, how many elements I need to jump. Okay, internally again that will behave like this. More internally, if you will go, this statement will behave like this: base plus index into size. Okay, more internally, this statement will work like this. So size we are multiplying. So if I'm adding 1 and every element is taking 4 bytes, so the next element will be 1004. Next element will be 1004. Okay, and digit is asking, okay, how this is equal to this thing. So again, see, you tell me, I tell you here, okay, let me erase everything first, make some space. I'm asking one question, I'm telling you, through this I'm asking you, please take 1000 steps, you take 1000 steps. Okay, then I ask you, please take 5 more steps, you take 5 more steps, and you reach to some location. Okay, here I'm asking like that, and here I'm asking, please take 5 steps, and then I'm saying, okay, please take 1000 steps, 1000 more steps. So where you are reaching, you're reaching to the same location where you were reaching here. Okay, where you were reaching here. So it's like that, you're initially you are taking 5 steps, and then you are taking this much steps, and here initially you are taking this much step, and then you are taking this much step. Okay, so these both will behave the same way. These both, even these 4 will all will behave the same way. All are same thing, actually, all are same thing. Okay, these are some important points which I'm covering. Okay, so this is 3D array means I can use a word for this. This is an array. See what I'm doing. This is an array this is an array. This is an array of matrices. Of matrices. This is an array of size 4, of size 4. This is an array of matrices. And what is the size of matrices? Size of one matrix is 5 into 4. Size of one matrix is 5 into 4, 5 into 8. And how many elements this array have? 4. Okay, so I can say that I have four matrices of how much size? 5 into 8. 4 matrices of this much size. Are you able to understand? If you are able to understand, then can you tell me how many elements will be there in this array? How many total elements are there in this array? Total elements here in this array is 5. Total elements in this 2D array is 5 into 4. 20 elements are there. How many elements are there in 3D array? In this 3D array, can you tell me? Please write in the chat. How many elements will be there? So simply you multiply 4 into digit, you simply multiply actually 4 into 5 into 8. See, you have 4 matrices of this much size. So how many elements? Every matrix you have this much elements. So 8 into 5, 40, and 40 into 4, 160. 160 elements are there. Please solve this question. Please solve this question. No points will be left. We will cover each and every point. After that, only silly things will be left. You people will be able to understand all that silly things yourself. We are covering all the points related to array. So okay, let me try it. So simply this is 3D array actually. So how many elements are here? 8 elements are here. How many elements are here? See, starting from -5 to 5 plus 5. So 1 -1 to -5, 5 elements. 1 to 5, again 5. 1 is 0. Total element is 10. See, -1 to -5. How many elements? 5. And 1 to 5, again 5. So, and 1 is 0 also in between. 0 is also coming, 1 index. So total element 5 plus 5 plus 1. So total is 11. So here we have 11 element. How much element we have here? So 1 to -1 to -10, 10 elements. 1 to 5, 5 elements. And 1 is for 0. So total is 16. So total answer is 8 into 11 into 16. So you need to multiply it. And one thing is sure, at the last unit digit will be 8, and that is B. So B is the right answer here. B is the right answer. If you have any doubt, please write in the chat box. Otherwise, we are now moving to the pointers. We have covered all the important points about the array. We have covered all the necessary important points about the array which you required in the GATE exam or ISRO exam. Okay. Okay, let's talk about pointers now. Again, we are starting from very basics, definitions. So pointer in C are used to store the address of a variable or a memory location. Okay, we are storing the address of a memory location. For example, if we have a variable like a variable in which we have value 10, so what we are doing is, so this variable is stored in memory like this. So we have a memory location in which we store 10, and the name of this location is var, where. Okay, and this is the address of this location, address of where the 10 is stored. Now this is how we declare the pointer, by putting star in front of the variable. So this is a pointer. Now we can store the address. This is the address of operator, address of. So we say address of var. So we are accessing the address of var, this variable, which is 2008, and we are storing in this pointer. Okay, so we store, we created a pointer. This is also variable. This is also variable, but this is a variable which store the address, which store the address of another variable. Okay, so this is storing the address of this var, let's suppose to 2008 address. So this will store 2008 here. Okay, this pointer can have its own address. I don't know, maybe I don't know, some different address. Okay, it's okay, Mehak. Okay, so and how we will access the element using the pointer. If I want to access the element at this address, so I will use the value at. We know that this is value at operator. Value at, this is address of. You simply read it like this only, address of, value at. So we use this statement to find the value at this address. Value at 2008 is what? 10. So we replace that 10 with actually 20 by using this statement. Okay, so this is the basics of pointer. So if somebody asks you what is the size of a pointer, how much memory that take, so we know that integer variable take, let's suppose 4 bytes in memory, 4 bytes to store integer. Okay, but how much space a pointer take? Actually, that depend upon the computer architecture. Okay, that depend upon computer operating system to operating system. Okay, actually that depend upon the memory size. Okay, I'm going to cover all these things. Before that, I'm moving to this question directly. You people please try this question. Okay, so let me explain this question and then we will move to the important concepts of the pointer. So let's finish this question and then we will move to the important concepts of the pointer. So we have an array with us and two variables I and sum. Sum is having initial value, sum is 0, and we have a pointer here which is having the address of which location. Actually, a store the address of the starting element. A is the name of the array which is having the, we know that array name store the address of starting element, first element, zeroth element if I say. And if I add 4 in this, so 1 2 3 4, so this location is the address of this element 10, last element. Okay, so b will store the address of 10, b will store the address of 10 in memory. Okay, after that we have a loop which is executing from, okay, let me write it here, 0 1 2 3 4. This is our loop is executing, for loop is executing, and we are summing the value, and after that we are printing some value. Okay, so what we initial sum value is 0, and what we are doing, we are performing this operation. What we are doing, see, this is value at operator, we know that this is value at. So what is the value at b? B is having the, initially b is having the address of, b is having the address of 10. Okay, so this last element address is stored in b, so value at b is 10. B is having the address of 10, so at value at b is 10. Okay, so 10 minus I is how much? I value is 0. I value in the starting is 0. Okay, so 10 minus 0 is how much we get from here? From here we get 10 minus 0, we get 10. Okay, and what we are doing here, we are having the address of 10 in memory, address of 10, and we are subtracting I from that. I value is 0, I is 0, this is I rotating. Okay, so I value in the starting is 0, this is I. So we have the address of 10 and minus 0, so we get again, but this is having the address of, this is having the address of 10, and what is the value at here? This is the value at operator, so value at address of 10 is 10 only. Okay, so 10 minus 10 0, so initial sum value was 0, so after 0th iteration, this iteration first time we will the sum value will be 0. Okay, and this loop will keep rotating, okay. Let's execute it once again, that will be more clear to you people. Then I value is now 1. So b is storing the address of 10 in the array. Okay, so we can draw it also. 2, 4, 6, 8, and 10. So the address of this location I don't know. So maybe 1000 is here. One for easy, I'm writing in sequence: 1001, 1002, 1003, 1004. So this is the address is in B. Okay, 1004. Okay, so simple. One for I value 1. Now what will be the value here? From here what we will get in place of 10 now? So value at B is 10 minus 1. 10 minus 1 is 9. We get 9 from this thing, this statement. And from this right statement what we get? So B is having the address of 10 and minus 1. If I will minus 1 from 1004, what I will get? 1003 means the address of 8. Okay, so what is the value at address of 8? That is, the value is 8. So here I get the b minus I means b minus 1. B was having the address of 10. So 1004 minus 1 is 1003. So 1003 value, what is value at 1003? That is 8. That is 8. Simple. Okay, so 9 minus 8 is 1. So what was the earlier value at sum? 0. 0 plus 1 is 1. Okay, again I'm repeating the same thing. So let me again erase it, so that same thing I will repeat 2 more times. The same thing I will repeat 2 more times, so we have chance to understand this thing. Okay, now some value, some value is 1. Again we need to execute it. We need to execute up to 4. Okay, so now can you people tell me what will be the value here? So b value is always 1004 once. And what is the value at this address? 10. So 10 minus I value is now 2. We are here now. Okay, I value 2. So 10 minus 2 is 8. From here we are getting 8 when I value is 2. Okay, now and from here what we will get? Address of b is this, minus 2 will be this. So from here value at this address is 6. So we get 6. Okay, so 8 minus 6 is 2. So we get 2, and earlier was 1. 1 plus 2 is 3. Okay, again I will repeat now. Okay, again I will repeat. So let me erase this sum value now. Again the same thing I will repeat. Now sum value is 3. And what will be the values here at both of these places? So can you people write in the chat what will be the value here now at when I value is 3, so that I can understand. Okay, you people know now what will be the value here when I value is 3 now. What will be the value here? 7. Yes, 10 minus 3, 7. Okay, and what will be the value here? So 1004 minus 3 is actually this. That will be 4. Okay, 7 minus 4 is 3. What we get from here? 3. And 3 already we have in sum. 3 plus 3 is 6. Some value is now 6. Okay, so now again we have one more chance now. So some value is 6. Again we need to execute this statement. So value at b is 10. Already b is having the address of 10. So star is saying the value at b is 10. So 10 minus I value is now 4. 10 minus 4 is 6. From here we get 6. And what we get from here? So again b is having the address of 10. 10 minus 4 I will reach to this address. And what is the value at this address? With star operator I am finding, that is 2. So 6 minus 2 is 4. I get 4, and already I have 6 and I add 4, so what I get? 10. So I will print simply this sum value, that is 10. So A is the right answer. If any doubt, please ask me. Otherwise 10 is the right answer. A is the answer for this question. There are many things actually in this. Also there are some concepts which I'm explaining in previous these slides actually. So let me move to these slides, because these slides have some very important points. These actually they will ask the question from these points only. Whatever points I'm going to tell you, they will ask the question from these points only. They cannot ask from, they cannot create their own points about the pointers. We will cover all the points. Okay. And I'm just, I've taken the, just like I will say that this is the cream I'm giving to you. Complete all about all everything about the pointer. I'm just taking example and telling you. Okay, directly like that. Okay, so some more important points about the pointer. Let's try to understand. So this is actually known as address of operator or reference operator also. This is known as, and this is actually this is star. This is not percentage. Star is known as the dereference operator or value at operator. Star is known as dereference or value at operator. You know, people know already. Can you people tell me what will be the output of this? What this will print? Please keep little bit pace with me. Who people join right now, they can also, now we have started the pointer, they can keep with me. Believe me, after this session the pointer will be complete finish and you will be comfortable with pointer. And pointer, believe me, is one of the toughest topic, one of the toughest topic in DSA. Okay. uh, in programming and data structure. Okay, that is one of the toughest topic. But if everything will be clear in sequence, I have put everything in sequence, then you will find it very easy actually. So please keep whatever I'm asking, please telling me, keep telling me what will be the output, what this will print, what this will print. Divyanshu says that 23 and its address. Yes, this will print the 23 here and the address. This is the address of 23. Address of 23. See, P is saying that this is the pointer type. Okay, this is the what type of data type is this? This is pointer type. Means this will print the address. This will print the address. Address of, this is the address of operator. Address of age will be printed. So if age is in memory, this is storing 23. If the location is, this is the address of age, then this will print 23 and 5000. Okay, so you people please tell me what will be the output. Please keep telling me, please keep trying. That is important. Keep trying. We will finish the pointer. Nothing will be left. Nothing will be left. They can ask any type of question, any whatever they can ask anything. No problem at all. But please keep trying to give the answer of all the question. So what will be the output? So we have declared a pointer here, which is having the address of this. And let's suppose the address of age is 5000. Then what this will print? This and this. Same, but in reverse order. Now this will first print 5000, then this will print 23. This is value at this pointer. Value at this pointer is, value at this address is 23. This is value at operator. This is value at. So value at 5000 is 23. And this is simply printing the, what is the value at PTR. So PTR is in memory, which is having this value, address of this. Okay, this pointer itself can have its own different location in memory. Maybe, I don't know. Okay, another point. So another thing, if you are declaring the pointer, you can declare it like this. Means star, this star can be near to the data type. This star can be near to the pointer name. This also the same thing. And space, there can be space here and here. So all the declarations are allowed actually. All declarations are allowed. Okay. This is also fine. This is also fine. This is also fine. In this, star is near to the data type. In this, star is near to the pointer name. In this, star is middle. Is one space away from int or one space away from num. Even that can be 100 of space away from each other. So this all are the declaration of the pointer. Okay. So these are the basic points about the pointer. Let's see now pointers and array together. Okay, from where the usually question comes. So let's suppose we have an array. So we know that array name store the starting address of the, we know this thing now, starting address of the array, starting address that store the starting address of the array. So we can store this address now in a pointer, because pointer store the address. So this pointer now store the same address, starting address of this array, starting address of this array. Okay, so this base address of array will be copied to ptr here. Okay, we know this thing. Another important point, uh, array name is a representative of complete array, while pointer stores the address of only one location in memory. Okay, based on this statement now, can you tell me what will be the output for this program? This statement is given to you now. I'm explaining here what you mean by array name, what is the difference between array name, what is the difference between this array name and this pointer. Although I'm storing the of starting address of this array here in this pointer, but still these both are different things. This ptr and this array both are different things. Okay, and what is the difference that I explained here? Based upon that, can you tell me what will be the output of this? So size of operator will tell me the size in bytes, actually. Size of a particular thing in bytes. I'm a little bit, no doubt, I'm a little bit going fast. Just my motive is that I give you all the points. Okay. So array name, what I'm telling here is that array name is different from this thing. This is a pointer. This is a pointer, and this person is representing the complete array. This person is not about just having the starting address. Okay, no doubt this is having the starting address, but the array name is not about only the starting address. He is the representative of complete array. This is the representative of the complete array. The complete array, this complete all the elements in the array is represented by the array name. Okay, and this is just a pointer. Okay, even after this statement, I'm storing the starting address of this array in this pointer, but still both things are different, and you can find out this with this example actually. So here we have an array. Okay, we have an array, and we store the starting address of this array in this pointer. Okay, and now we are printing the size of the array. If we use a size of operator on the array name, even you can say that now array and ptr both are having the same address, but this will represent the size of complete array. Complete array. What is the size of complete array? This is character array. If every character take 1 byte, this will take 1 plus 1, 3 bytes. How much bytes this arrays will take? 3 bytes. This will take 3 bytes. So this will take 3 bytes. This will represent 3. And what this will represent? This will represent size of the pointer. Pointer is a variable. Pointer is nothing, just a variable which is having the starting address. Let's say starting address is 1000 of this array. This is having the starting address of the array, and the size of the pointer we already explained in the starting slide, one slide. Size of a pointer depend upon the computer architecture. Okay, means that depend upon the memory size. See, this is storing the address of one location in RAM. So this will depend upon the total size of the RAM. So actually, so usually if we are using 64-bit operating system, so in that case, right now if we are using 64-bit operating systems, so our architecture, CPU architecture is of 64 bits. So that's why how many bytes this will take? One address will take 8 bytes. Okay, So if you will print this, even you can print this, you can copy this code as it is in online compiler. You can check out. You will get what you will get: 3 output here and 8 output here. Okay. Okay. So what I was trying to tell you, let me summarize. Although array name having the starting address of the array, but this person is representative of complete array. If I'm talking about array, this arr, I'm talking about all the elements. I'm not talking about one element. But here I'm storing the starting address of the array. So this person is talking about only address of one element, address of starting element, address of starting element, address of starting element. But this person is the representative of complete array. So that's why this person, if I will ask, what is your size? He will say my size is depend upon the array size. My size is not the size of the one location, one address. This person will say that, this ARR will say that my size is the size of the complete array. So this will return 3. And this person will say that I'm not bothered about the size of the array. I have the address of the first element. Okay, so I'm storing the address of first element. Okay, and my size depend upon computer architecture. So if I'm using 64-bit processor, 64-bit operating system, my one memory location size will be 8 bytes. And these days you will find the answer, that's why 8 bytes. Okay. Okay. So I hope this is clear. If any doubt, you can ask me. Otherwise, let me move to another very important point. We can access array elements with array pointer. See, you can access the array elements like this, but you can access the array elements with this pointer also, with this PTR also. Okay, so PTR store the starting 1000. If I say, okay, 1000 plus 1, now I'm able to access next element. Okay, so if I write PTR plus 1, value at PTR plus 1, this is same as if I'm accessing one element. I can access the element in array like this. With pointer, I can access the first index element like this. If I want to access the second index element, this one, this will be like, I need to access like this. I need to access like this, PTR plus 2. Okay, so this will take me to this location of the array, this element. So what I want to say is that we can access array element with pointer, array pointer. This is our now array pointer. This is the pointer which is pointing to an array. So we can access, but we need to use the syntax like this. I hope that will be clear. So let's move to the next point. Any doubt, you can stop me, you can write the question. Okay. So okay, we can increment the pointer also. Okay, we can increment the pointer like PTR plus 1. Okay, so if we have an array, so suppose we have an array, this is integer array. Okay, this is integer array, and starting address is 1000. If this is integer array, let's suppose integer take 4 bytes, 4 bytes in memory. One integer take 4 bytes. So next address will be 1004, next will be 1008, 1012. So if I'm saying PTR is having the starting address of the array ARR, which is actually 1000. So if I'm saying that this thing 1000 plus 1, so it means I'm accessing now this location, next location. Okay, so just like in array, if we are adding 1, so we are not accessing 1001 location. What we are accessing here, we're accessing the next element. Okay, we jump to the next element. Here similar way we will jump to the next element. Okay, we will not access like 1001 here, we will jump to 1004. In the case of float, 8 bytes I will keep adding 8 bytes. I hope this is clear. Any doubt, please stop me and ask me. Okay, another important point is, so this is the array of pointers. This is the array of pointers. This is my array P, which store the pointers, which store the address of other variables. This is also the address. 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 So actually in this case, let me draw it. So in this case, this is storing the address of different elements. ARR, ARR plus 1, this location, ARR plus 2. Actually, if we have an array of like of ARR, 10, 20, 30, 40, and the address is, let's suppose, 100, 1004, 1008, 1012. So here we are storing 100, 1000, here 1004, here we are storing 1008, and here we are storing 1012. So this is the array of pointers. So we have an array, but this array is storing the addresses. This array is storing the addresses. In this case, this is storing the address of different elements in array ARR. Okay. Okay, I hope this is clear. Still any doubt, please stop me. Your doubt is more important than new information. Okay, your doubt is more important than new information. So you can ask the question anytime. I will go back to the previous slide also if you will ask me. Otherwise, I'm going on now. Different operations which we can perform on pointers. Okay, so I'm taking this session a little bit more longer one because let's complete all the important points about the pointer. So there are some operations which we can perform on pointers. Pointers store the addresses. So on addresses, one thing you know now, we can perform addition. We can add the integer. We can add like you were doing. You were doing PTR plus 1. You were adding some integer in the pointer. You can perform this operation. Similar way, there are many operations. Some operations you can perform, some you cannot perform. Okay, so let's see which operations we can perform. Okay, let's see which operation we can perform. So assignment of pointers. First thing, can we assign one pointer to another pointer? I have two pointers. These are two pointers. Can I say like this? Is this allowed? So yes, we can assign. Yes, we can assign. They are pointers. They are pointers which store. They are pointer variables. They can store any address. Provide them any address. He A is not bothered about what the address B is having. He can hold the address. Okay, why he can hold the address? Because the size of A is equal to size of B. This will also take 8 bytes in memory. This will also take 8 bytes in memory. Okay, both will take the 8 bytes actually. Okay, so two pointers of same data type can be assigned to each other. So if both are integer, then I can assign. But what about if they are not? What about if they are of different data type? What about if they are of different data type? Like one is of integer, for example, one is of integer and another is of character. This is a pointer to character, B is a pointer to character, A is a pointer to integer. We can assign that also, but we need to perform typecasting. We need to perform typecasting. We need to convert it. We need to convert. Okay, we need to convert it into integer. I'm storing B address now into A, but we need to convert it into integer. Okay, why we are doing this thing is actually because let's suppose you are accessing the elements in an array. You are saying PTR plus 1. If you are saying PTR plus 1 and I'm saying that if PTR initial value is 1000, and what will be the next value if I'm adding 1? That will depend upon data type of PTR. That will depend upon data type of PTR. If this is integer type, then the next value will be PTR 1 plus 1 will be 1004. But if this is of character type, then PTR plus 1 will be 1001. Okay, so uh, that's why data type matters. That's why data type matters. We can, what I want to say is that in the final, we can assign the different data type pointers like integer and float or integer or character, but we need to perform type conversion. Okay, okay. So this is one operation you can perform. Yes, we can perform assignment. One thing is sure. For the same data type, directly we can perform. Directly we can perform for same data type pointers. For different one, we need to perform typecasting. We can perform, but we need to perform typecasting. That's it. Another operation. You people tell me, can we perform addition and subtraction in a pointer with an integer? Like, can I do like this ptr plus 1 or ptr minus 1? Can I perform addition and subtraction in a pointer? Can we perform? Yes, we can perform. We already done this thing actually. Okay, that is allowed. But see, this is allowed for integer only. This is allowed for integer only. That is not allowed for float, long, or any other data type. You cannot say that, okay, PTR plus 1.1. This is not allowed. You cannot say PTR plus C. This is not allowed. Okay. Only for integer is allowed. Okay. And one another thing. You can perform only addition and subtraction. You cannot multiply or you can perform multiply, not subtract, multiply or division. You cannot say ptr is equal to ptr into 2. You cannot multiply any integer with ptr, with pointer. You cannot multiply, you cannot divide. These are not allowed. Only addition and subtraction are allowed. What I want to say in second point, only addition and subtraction are allowed in pointers, and only with integer. Only with integer. Only with integer. Now we are getting nice messages also. So only with integers we can perform addition and subtraction. We cannot perform multiply and division, and we cannot add, subtract, float, long, or any other data type. Okay. Okay, so this is the second important point. Third operation which we can perform. See, third operation. Subtracting and comparing two pointers which are member of same array is allowed. Let me give you an example. So let's suppose we have an array. Listen, look at here. We have an array of size 5. We have two pointers A and B. We have two pointers A and B. We declare two pointers. What we are doing, we are storing some address into in A pointer. So let me draw it here. So 0, 1, 2, 3, 4, 5 elements we have. So what we are doing, we are storing the address, first address. Let me erase from here so you people can see here. So we are talking about this address of this element actually. Let's suppose this is 1000, this is 1001. Let's suppose this is integer, otherwise this can be 1004. Okay, 1008, 1012, 1016. So this address 1004 is stored now in A. Okay, by this statement. In B, what we have stored, the address of this, which is 1008. Okay, so we can check like this statement. We can perform this statement. What this statement is saying, we can compare the two pointers. Is A is less than B? Is A is less than B? We can make this type of comparisons. Okay, we can make the comparisons between pointers, and we can subtract two pointers. I'm subtracting b minus a. B is also a pointer, a is also a pointer. So in this, so what I will get actually here, I will get, what will be the output here? B 1008 minus 1004. So that will actually return number of elements between 1 and 2. Number of elements actually. Okay, so this will return one, actually one element, including the starting elements. So this, if you will subtract it, actually 1008 minus 1004, so you will get 4 bytes. 4 bytes is used for storing one element. Okay, so actually this is talking about this element, let me tell you. Okay, so what I want to say, that we can subtract 2 pointers, we can compare 2 pointers, but that should belong to, these 2 pointers should belong to, this should be the member of same array. That should be the member of same array. Excuse me. So any doubt, you can ask. Please ask if you have any doubt. If you will ask doubt, then that will help other people also. Okay. But addition of 2 pointers is not allowed. Addition is not allowed. Subtraction is allowed of 2 pointers. I cannot say b plus a. I was doing b minus a, that is allowed. Because you can see b is 1008 and a is 1004. This is meaningless. 1008 plus 1004. I don't know where we will, this location will not be in the memory. If we will add, that will not, at least will not be in the array, in that array. So subtraction is allowed, but addition of 2 pointers is not allowed. Okay. Actually, no other operation is allowed. You cannot multiply, you cannot divide 2 pointers, you can multiply 2 pointers, you can only subtract 2 pointers. Here, in the second point, we were talking in the context of one integer, one pointer. We can perform addition and subtraction. But here we are talking in the context of 2 pointers. We have 2 pointers with us, and we can subtract them. But they must belong to the same array. They must be the member of same array. Means one pointer may be pointing here, and another pointer is pointing here. In the same array. They should not be in the different array. Otherwise, that will be meaningful. That's it about the operations on pointer. You will not find anything else except this on operations on pointer. Actually, these are all the important points. So C actually is telling us about the number of elements. Number of elements here. See here, you're talking about this. If you will subtract 2 pointers, that will tell you how many elements are there between these locations. Between this location and this location, let's suppose 0, 1, 2, 3, 4, 5. So what I need to do, 5 minus 4 plus 1. Okay, so this will, what is q minus p is actually this thing. This will be 5 minus 1. P location is 1, q location is 5. So 5 minus 1 plus 1, because we are including p itself. How many elements from p to q actually this thing is telling us. So that is 4 plus 1, 5 elements. 5 minus 1 plus 1, this will give us this thing. This is giving number of elements. That's why we are taking int c. Here. Nice question. Beautiful question. We will not get the address. By subtracting 2 addresses. We will get number of elements coming between those two addresses actually. Number of elements. That's why we write int c there. So you already solved this question. You have already solved this question. Here we already apply some operations. You can see we were subtracting the value. We were subtracting from the pointer. So we already covered this question. We were performing some operations on the pointer here. Now let's talk about pointers to pointer. So let's take an example. We have variable age 23, and this is a pointer which is having the address of age. This is the pointer to pointer, which is having the address of p. This is having the address of p, pointer to pointer. So if I draw it like this, so this is our age variable, which is having 23. Let's suppose address of this variable is 1000. Now we have a pointer p, which is having the address of the age, which is 1000, and its own address I don't know, maybe 2000, the address of p, which is further stored in another variable, that is pp, which is having the address of p. So address of p is 2000. Okay, so p is storing address of a pointer, or you can say address of a pointer. So this is a pointer to pointer. Okay, pointer, which is also a pointer. Okay, pointer to pointer. Okay, so if you know this thing now, so we know that this is a value at operator. Value at. So okay, so if we draw the same thing, age 23, 1000. This is p, 1000, 2000. This is pp, pointer to pointer. Let's suppose the address here is 3000, but this is having 2000. So what is the value at pp? Value at pp is 2000. And what is the again value at 2000? Which is 1000. Okay, so this will print. What this will print? This will print 1000. Let me check once again. Yes, value at pp is 2000, and again I'm checking value at 2000 is 1000. Okay, so this is giving me 1000. Yes, yes, Divyanshu. Okay, if the p is having this address 1000, okay, this will result in this case 1000. If I'm putting one more star, that will give 23. That will give 23 as output. Okay, so let's move to the another example now. So can you people tell me what this statement will print? We are covering all the possible scenarios actually with these examples, starting from the very basic one and going to little bit advanced level. We will go little bit more advanced after this, but step by step we are going. Can you people tell me? So this is a simple array we have. This is the array of pointer. We know about now this array of pointers, which is having the address of the, this is an array. Array of pointer is an array which is already having the addresses that don't have values. They have some address of something. Let's suppose this is the address, and this is having the value. So the value, this array is having the addresses. This is the array of pointers, which is having the pointers, which is having the addresses of other things. In this case, this is having the this is having the addresses of these elements. So first element address, second element address, this element address is here, this element address is here. Okay, if we draw this array A, so 1 2 3 4 0 1 2 3. Let's suppose that this address is 1000 and this is 1004 1008 1012. Okay, now so we have this array. This array is simply having the addresses, these addresses, because starting address, array name is having the starting address, and then next element address, next element address, next element address, which is this 1012. So this is our actually P. Okay, and so add now this array is also stored at some address. Okay, this array is also stored at some address. Let's suppose the array address is 5000. I don't know, means this array is starting at 5000 in memory, which is storing further addresses. So this 5000 will be stored in ptr. Okay, so let me make space here. So 5000 will be stored here in this pointer to pointer. And what will print this? Now I'm asking this thing. So now we have all the data with us. So what this will print and what this will print. After first statement, print statement, what will be the output? After covering all these concepts, no question from pointer will be there. You will not be able to solve actually. 1000. Yes, one is a is having the starting address of the array, and the value at a, this is the star is the value at operator, value at a is 0. Yes, so this is 1000 will be printed. And what about this? What will be printed here in the second statement? What will be the output of this second statement? I'm asking this thing now. We have already find out what will be the output of this. This is printing the a address. What is the value at a is the name of the array which store the starting address, and value at a is 0. Okay, fine. What about this second statement? So 5000 1000 0 from digit we get. Let me write here 1000. So let's see how he get this. So he is printing the address of p. Address of p is 5000. Yes, that is right. And value at p is again I can say, okay, value at this is the starting address. This is the starting address from where this array is stored. Okay, and what is the value at this address? Value at this starting address is 1000. That is 1000. Okay, that's nice. And what is the value at this address now? 1000. Value at 1000 is 0. That is also right. Yes, you are right. So what about this statement, third statement? What will be the output here? So this ptr is pointer to pointer. So we do not mention this the address of this ptr. So that's what the nice thing you mentioned. You said that that is the address of ptr. Okay, so let's suppose that is 10,000. I don't know. So that's right, Divyanshu. So that is the address of ptr we are printing here. And then value at ptr is 5000, and you write 5000. Yes, that is also right. You write 5000 for this, and this is the address of ptr, that is 10,000 now in this case. And we are finding, okay, value at ptr is 5000. Okay, and what is the value at 5000? Again we are finding value at 5000 is again 1000. That is again 1000, and you already tell that thing. So okay, so we are getting 10,000, 5,000, and 1000 from this. Okay, so I hope this is clear to you. Any doubt you can ask me. We are going for more detailed pointers. We are going step by step. You need to keep with me. Okay. So can you people tell me what is the output of this program? Please write the output of this program. Please keep trying. What is more important is keep trying. Okay, please try this. Right or wrong will not matter. Now, this is the next topic actually. Pointer strings we are studying, or array strings. We will see the difference between array string. This is the array string, and this is the pointer string. So we can use any of them in C language to declare a pointer. Okay. Okay. So let me tell you one thing, how they store in memory. So if we are declaring a string, with array, character array, that will be stored like this in memory, means at the end there will be null character also in memory, just like ordinary array, but like integer array, but in character array, null pointer is also added automatically by the compiler. Okay, this will happen in the case of pointer string also. This is pointer string. We take a pointer and we generate the string. This will also store in the same way. This will also store in the same way. There will be, that will also end with the null character. Okay, so what's the difference between them? That is important. What's the difference between them? The difference is that this is constant string. This pointer string is constant string. Constant string means I cannot change the value here. I cannot change its value g from g to a, anything I cannot change. I can change here. I can change here in character array. I can change these values. I can change these values, but I cannot change here. These will remain constant. These value will remain constant. So whatever the string you are declaring with pointer array, that will be a constant string. This is the main difference between these two. Okay, and can you people tell me what will be the output? Okay, this was the one point. String, pointer string is a static string. Yes, that is a static string. Pointer string is a static string which cannot be updated, which cannot update its value. Okay, we already discussed this point. So yes, you are right. This will print 8. What this will print? Value at p. Actually, p is having the address of first element, and first element is g. And what is the size of g? Actually, that will return in the byte. Size of operator will return in bytes. How many bytes this g will take in to store in memory? Size of operator give the output in bytes. So what will be the output here? This is like size of g. G was here. So size of this character. Size of character is 1 byte. Okay. Yes. Size of character is 1 byte. Size of character is 1 byte. Character. Let me write. Character have take 1 byte in memory to store. Integer take 4 bytes in memory to store. Float take 8 bytes. I'm not confirmed. Long also take 8 bytes. You can check out. But this is again, this is not. This will. These are most of the compiler have this thing. Okay, most of compiler take 1 byte to store character in memory, 4 byte to store integer in memory, 8 byte to store float in memory, long 8 byte. Most of the compiler these days, but still in exam they can change it. They can mention different thing in out of this, and they can ask you the question. Okay, they can say that integer take 8 bytes. Let's suppose integer take 80 bytes. We need to take that thing. Okay, but if they are not providing and we need data, then we can use then this information. Okay, so this will return 1. What about this string length? This will return. Okay, actually this function will start from this address. P is the starting address of this, and string length function, let me tell you, will keep counting unless we reach to the null. Unless we reach to the null. So this will print all the characters in the string. So this will print 5. This will print 5. This will print all the characters in the string. This will print 5. String length. Simply this will print the string length. Okay. And what about this? This is size of A. See, this only you need to tell me now. This is very important actually. Size of A. A is what? A is the name of the array. This is important. And after that, this is nothing. This is the length of again array. This will again print 5. This is important. And this is important. That's why I'm asking from you people. That's why I'm not sharing from my side. So size of A is the representative of complete array. A is the representative of complete array. P P is the pointer. P is a P is a variable which stores some address. Okay, so the size of P is usually 8 bytes. So how much one address take to store? Okay, in memory. That depend upon the computer architecture. But A is the representative of complete array. A is the representative of complete array. If somebody asks you what is the size of A, that will be the complete array size. That will be the complete array size. So here the complete array size is 6, including the null. Including the null. This complete array size is 6. 6 here. And this is 5. This was important. A is the representative of complete array. Okay. Although you can store this address in some pointer, this is pointing as the starting address, and we can store the starting address in this pointer. That is fine. But if we are only talking about A, if somebody asks you who is A is representative of complete array. Okay, and yes, that is pointing to the starting address of this complete array, and that is having that's why that returned the starting address of this complete array. But he is the representative of complete array. If somebody will ask the size of this, so he will say that I am complete array. Although I am returning the starting address of this complete array, but I am representative of this complete array, so I will return the complete size. I will return the complete size. Okay, this will again return in bytes, but this is a character array, so 6 characters are there, so this will return 6 bytes. Length, string length is returning number of characters in this string. So this will start from the starting address and will keep going on until this will find out null. So this will count number of characters except the null. This is how this function is behaving. This will go up to the null and simply print number of character find out. That's why this is giving 5 and 5. This point was important. This and this, if you will compare. Okay, that's it from this. Now this is a GATE question. You people can try. You can try it. Okay, later on you can take the snapshot. Let me tell you the answer. Answer is B. You can try it yourself. So let me go in fast way. And so simple. We have string pointer here. String pointer. Okay, and we are storing the same address in some other pointer also, P. Then we are printing something. Okay, we are printing some value. What is that value? We need to tell. Okay, what is that value? So one thing is clear. We are printing the string length. String length actually. So this is the GATE. This is the array. Actually, GATE. I'm copying all this. C S I T 2017. Okay, and we are counting the string length of this thing. Let's see what is this thing. So C is what? C is the starting address. C is the starting address of this complete array. Okay, we have the starting address. Let's suppose 1000. Okay, and then we write this thing. We know that P of 2 is same as 2 of P. Okay, so 0 1 2, this is talking about this element. 3 4 5 6 7 8 9 10 11, this is accessing this element actually. So what it get from here is T. Okay, and from here this is accessing the 6th element in P. 6th element is actually I. From here this will get I, so T minus I. Okay, and after that this is getting -1. Okay, Now, so here this is telling us actually, see, this will convert this t to subtract it from, if we want to subtract two characters, actually this will convert it into a sky value of this. Okay, so I don't know what is the sky value of t, but one thing is sure, I come first in alphabets and t comes later. Okay, and if you will count from IJKLMNOPQRST. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 minus 1, T minus I. So this will count. I don't know what is the sky value. You do not need to know. Okay, you do not need to remember that, but the difference between the value here and value here, t and here, t minus I will be 12 minus 1, that will be 11. So from here I will get 11. 11 again minus 1 is total is 10. Okay, from here, so I can say from here I'm getting 10, and I'm adding this 10 in the starting address. Okay, so if I'm adding 10, so I will get 1 2 3 4 5 6 7 8 9 10. I will reach here, I will point to this element now. So in this total I will point to this element. And string length, we talked in previous slide, will that will get the starting address, and that will keep moving on until that will not get the null. Okay, so null will be at the end. So this will tell how many characters are there. How many characters are there? 1 and 1 2. Two characters are there. Okay, so 2 will be printed actually. So this will print return 2, and which will be converted in the form of integer, and that will be printed. So 2 is B is the right answer. You can pause, you can after the recording will go, you can check out the explanation by slowing down this video. Otherwise, I hope this is clear. So how many people can tell me, okay, is this clear to you? Is this clear? +1 for clear. Otherwise, okay, you can come back here. Okay, so important, you can solve this question. Okay, thanks for reply. B is the right answer. This is the precedence table, and sometimes they ask question like this. So how the operators have the precedence. So can you tell me what will be the output of this statement? If x is having 10, this is a pointer which is having the address of 10. Okay, and what will be the value of y? Can you tell me what will be the value of y? So this will calculate the value first. This will calculate this thing 1. After that, this will calculate this. This is based upon this precedence and associativity. So here you can see that star have higher precedence than plus plus. So that's why I executed this one, then this. And if we talk about the binary operators, actually, so sorry, this was the div reference operator actually. So both are having the same precedence, but both are right to left associative. So that's why right to left. So this will execute first, then this will execute first, and after that this multiply with 2 will execute. Okay, so value at ptr is 10. From here we will get 10, and we will increment it. 10 plus plus will be 11, and then we multiply with 2, so that will be 22. Okay, so you can check out this precedence table. This is one example I take, that's it. Okay, 22 is the right answer here. Okay, so the last topic I'm coming out right now in pointer, that can be the toughest one. Although only I see one or two questions only. I think one question only from function pointers. Means Function pointer store the function pointer. If I am declaring a function pointer, that store the starting address of a function. So let's suppose the starting address of this function. This is a function we write add function, and starting address of this function is 1001. So I declare a function pointer which store the address of this function. Okay, so how to declare that? So this is a simple variable pointer. Okay, integer pointer. So this is integer pointer, we know this. So we are recapping also. Okay, we are recapping everything. So what is this? Can you people tell me what is this? Please let recap and wind up. I'm winding up. So please keep replying in the chat box, and now I'm winding up. Array pointer, yes, this is array pointer. Array of integer pointer, I can say that that is having this is an array of pointers. Array of pointers means this is having the address of something which is a integer. Okay, can you tell me what is this? This is a function pointer. See, this thing is a pointer. This statement, this declaration is a pointer. This is how we declare a pointer. And what type of pointer is this? We know that we declare the function with the brackets, these small brackets. So this is a function pointer. This is how we declare the function pointer. Okay, so this is how we declare a function. This function pointer can store the address of a function. Okay, so this is a function pointer, or we can say that this is a pointer to a function which return an integer. So this is a pointer to a function which returns an integer. So this is a pointer to a function. This is a pointer to a function which returns an integer. Okay. So now next statement is, can you tell me what is this? What is this? So you know this thing. What is this? This is the array pointer. This is the same, this thing. This is the array of pointer which is pointing to functions. Now we have an array of pointers, means we have some addresses here now, but these addresses belongs to some function. These addresses belong to some function. Function 1, function 2, function 3. Okay, and I can say more. These functions are returning what? What these functions are returning? These functions are returning integer. I hope this is clear. Same thing written here. Array of function pointers. Array of function pointer. This is the array of pointers which point to the functions, and these functions return the integer. Okay, keep replying, so I will be knowing that okay, you are understanding. This will go a little complicated. Can you tell me this thing? Can you tell me this thing? So see, this is a pointer. One thing is sure, this is a pointer A. This is a pointer A which is pointing to what? An array. We have an array, and this pointer is having the address of this array. This is a pointer which is pointing to the address of this array. This array is of integer type. This array is of integer type. It is storing integer values. And this is having some address. Starting address is 1000. And this starting address is stored where? In A. So this is different from this. This is a pointer array. In this array, integer value are not stored. This is storing some addresses. This one. and this address is belongs to some integer. Let's suppose 10, 20, so on. Is that clear? You can write +1 if that is clear. We are moving to little more complicated part. So any doubt, please ask. Keep asking. Otherwise, writing +1. So A is a pointer which is pointing to array of 10 elements, which is of integer type, I can say. Okay. Can you tell me what is this? This statement. So again, this is a pointer. One thing is sure, this is a pointer. This is also a pointer. This is a pointer of array. This is again a pointer. This is a pointer of array of pointers. This is a pointer again. This thing is same as this thing or this thing or this thing. But here, this is pointing to a function. This is pointing to an array of integer. This is pointing to a function again. This is pointing to a function. All are different. All are different. 1, 2, 3, 4, 5, 6. All are different here. Okay, I'm coming to your point. So before telling that, what is this sixth point? This is a function. This is a pointer to function. That function is taking int as a parameter. For example, if I write a pointer to this function, so that will be like this. I will write like this: int. This is returning int. So I write int, and I need a pointer to this function. So for function I need to put bracket, but this is having two parameter of integer type. I need to write int, comma int. So this, I can say that this is a pointer to a function which is taking two parameters and returning an integer. So here I am returning one integer. So same thing is written here. F is a pointer to function. F is a pointer to function. See, these brackets are showing that F is a pointer to function. F is a pointer to function which will take integer as parameter. Integers as parameter, and return integer as output, as output. Okay, and you're asking, these two are different actually. These two are these are not same. This is a pointer to, this is an array pointer to array of pointers. I will say array of pointers, or I can say in English, array of addresses. This is an array which store the addresses. This is a simple integer array. This is simple. Let me write simple integer array. But the address of this integer array is stored in this pointer. Starting address of this integer array is stored in this A pointer. So here I have an array of integers which is storing some integer like 10, 20, 30, 40. And let's suppose starting address is 1000, which is stored in A. But here I'm having a array which store the addresses, which itself storing the addresses. This was storing the integers, this is storing the addresses, but these addresses belong to some integer value. So 10 and 20 are integer, but the address of these integers are stored in this array, and this starting address is stored in A. Okay, A is storing starting address of a pointer array of pointers, array of pointers, array of addresses. But here in fifth statement, A is storing the starting address of an array of integers. Okay, so let's move to more complicated part now. More complicated part. What is this? You are going to end the pointers actually. Pointer will start running from you, will start operating from you. It will solve 2 3 more questions actually. Can you tell me what is this? See, this is a pointer. We know this is a pointer. This is a pointer, and we know that this is a pointer to function. Opening bracket, closing bracket. This is a pointer to a function which take two parameters. One is integer, another one is this. And what is this? Let's see this now. From outside, everything is clear. This is a pointer to a function which is having two parameters. One is int, one is this. What is this? What is this parameter? Actually, this parameter is received. See, what is this parameter? Here we have a pointer. Again, we have a pointer. This is a pointer to a function. We know this is a pointer to a function which is returning a void. Which is returning a void. So this will return what? This will return. This will return a void. Okay, I'm repeating. This is a pointer to a function which is returning a void, and whatever will be returned, that will become the parameter of this function. So this function have two parameters, one is int, one is void, and the address of this function is stored in this pointer abc, and this function outer function is returning void. This outer function is returning void. We can draw it. We can make a function. We can make a function here. Let's suppose we have a function x, y, z. Okay, which is actually returning void. Okay, so I'm making this thing first. We can make this thing. So which is returning void, and this is simple, not taking any parameter. This is not taking any parameter. Okay, and the address of this function is stored in def. Def is having the address of x, y, z. Okay, okay, this thing is clear, and this is again a function which having two parameter. One is int and one is whatever is returned by this function, that is void. Okay, and another function is that is returning the void. Okay, okay, so let me see what you are talking about. Pointer of a function with parameters returning void. Pointer to a function, yes, pointer to a function. This is a pointer to a function with parameters returning void, yes, which is having these two parameters and returning void, yes, and parameters are integer and another. This parameter is will be actually void. This parameter is actually void because this function is returning this function. This is again a pointer to a function which is returning void. So from here we will get void, which is one parameter. Another parameter is int, and this is a pointer to this function which is having these two parameters and returning void. Yes, you are right. Okay, same thing is written here. So I'm covering it. Even if people are not able to understand, still I'm covering it so that if you will go a little slow, this is in more same thing I have explained here, so that you can check out this thing later on. Same thing what I was explaining here. So that is in a little neat and clean way. So you can check out it later if you think that you are not able to understand. Okay, another function. So we have two more slides, that's it. So this is, see, what is this? Let's start from innermost. So we know what is this. What is this? This is a array of pointers. This is an array of pointers. This is an array of pointer. We know this thing. This is an array of pointers which store the addresses. This store the address, or address of what type? Address of function type. These addresses stored here, actually these are storing the address of functions according to this statement. This one, okay, and these functions are returning again pointers. These functions are returning pointers. Okay, and this pointer, the pointer returned by this function, this pointer again belongs to some function. This pointer again belongs to, this pointer actually belongs to some, this pointer is having the address of some function, which this function is returning again a pointer of character type. This function is again returning a pointer of vector type. I can say, okay, this is cap star. This is a returning pointer of vector type. That's it. So you can see the same explanation here and more clarity diagram here. So this is a array of pointer which points to a function, and this function is return a pointer, and this point which points to a function, and this function, the function return a character pointer. Is this clear? Is this clear? So don't mind if not clear, not clear, that's great. So this is the last slide, okay? After that we are winding up. We already taken 3 hours. So this is the assignment for you people actually. So that's it from my side. Thank you. Thank you everyone for being with me for 3 hours.
Hello everyone, welcome to the course of, welcome to the GATE crash course offered by the GeeksforGeeks. This course is free of cost, and in this particular session, we will discuss about linked list. We will finish this topic in its entirety, as we are doing with all the topics in this series, in this complete series. We are covering 5 most important topics from every subject, and this is the second topic I'm covering from programming and data structure. Already we have discussed about the array and pointers, and this is the second topic. Although for this particular lecture there is no prerequisite, you do not need to know anything in advance, but after this session you will be able to attempt all the questions in GATE. Okay, and another benefit of attending today's session is you will also be able to solve the questions for any company also actually. Okay, so linked list is the important topic not only in GATE but also from company point of view. So you will also get benefit after this session. You will be able to solve the questions from company as well as from GATE. Okay, and I will start from very basics and we will go to the GATE level. Okay, so before again moving on to this particular topic, let me tell little more information about this course. So if you are new here to this course, let me tell you, we are offering this GATE crash course for GATE 2023 preparation, and this GATE crash course is free. You can find the detail in the description. Still, let me give you little information about this GATE crash course. In this GATE crash course, from every subject. Actually, we are covering 5 most important topics. Okay, 5 most important topics we are covering from every subject. So what is the benefit of this course? So if you are a beginner, means you don't know whether you will be able to clear the GATE exam or not. So this course will make you sure that, okay, at least you will be able to clear the GATE exam. Why? Because here we are covering the most important, most expected 5 topics from every subject. And this course is almost, I think, 1.5 months, even less than that. Okay, so in 1.5 months, this course will ensure you that you will be able to at least clear the GATE exam. Okay, so one thing, so if you are a beginner, if you don't know about so much about the GATE, if you want to clear the GATE exam, so this course will be helpful for you. Another thing is that if you are already preparing for the GATE, then again this course will be helpful for you. This will helpful to revise the 5 most important topics. You can revise your 5 most important topics from every subject through this course. Okay, so these 2 type of students actually can take benefit from this complete series. Okay, so this was about the complete series. So let me move to the today's topic, which is very important topic, not only from GATE point of view, but from also company point of view. Okay, people, I don't know, I see that many people get afraid from the link list, but that I'm giving you a surety that after today's session you will start enjoying the link list, because everything will be clear. Then definitely you will start enjoying the topic. Okay, before again starting this session, let me tell you people, we have zero prerequisite. If you are new to this topic, even to data structure also, you will be able to understand each and everything, because we will talk logically. Everything we will talk logically, and we as a human being like the logical things actually more. Okay, so let's start with the linked list. Again, I will start from very basic, from introduction to linked list, and we will see various operations we will perform on linked list, insertion, deletion, all the operations. We will see different type of linked list: singly linked list, doubly linked list, circular linked list. And then after that, you people will be able to solve the previous year GATE questions. I will just give you little bit help, and you people will be able to attempt many questions we will attempt in today's session. And if you will understand all these things logically, then this will be easy for you attempt. Even in today's session, actually, I inserted some question from companies also, from product-based company. I have to say, from product-based companies, I added some questions, because linked list is important topic, so that you people can benefit there also. Okay, so still the most of the focus is on GATE, but still I have added the question from product-based companies, good companies. Okay. So let's start with the very basic, with the definition of the linked list. A linked list is a linear data structure. Linked list is a linear data structure, but also the dynamic data structure. Okay, so in this line, what they have mentioned, linked list is a linear data structure and dynamic data structure. What is linear data structure? In which the elements store one after the another elements are storing. So linked list is a linear data structure. Array is also a linear data structure. One after the another element are storing. Graph is non-linear, in which some elements storing to the left, some are storing to the right. So that is non-linear. That is not storing the data in linear way, in sequence. Okay, so this is a linear data structure, and this is the dynamic data structure. Dynamic means we can add more data in this data structure. Okay, even while runtime, I can add more nodes in the linked list. So this is the dynamic data structure. Okay, so let me read again the definition. A linked list is a linear but dynamic data structure in which the elements are not stored at contiguous memory locations. Elements are not stored at contiguous memory locations. They can store anywhere. They can store anywhere in the RAM, but they are not stored. They are not sure that, okay, we are storing them in continuous memory location. In array, we are storing all the elements in continuous memory location. But here, one node can be at, I don't know, at 5,000 memory location. Another node can be at 6,000 memory location. Maybe another node is having is at 1,000 memory location. I don't know. They're at different locations. This node is at, I don't know, at 1,500 memory location. So they are not in continuous memory locations. So linked list is a linear data structure, or I can say linear and dynamic data structure, in which the elements are not stored at continuous memory locations. Okay. So I just, actually this definition is created by me. I just try to add some important features of the linked list in this definition. That's it. You can create your own also. You can create your own definition also. This is the little picture of the linked list. Otherwise, so in linked list, let me tell you, we have nodes. This is one node, this is another node, and so on. We have nodes, and there is a pointer. This is a pointer which is pointing to the starting element, starting node. There remain a pointer which is pointing to the starting node. Okay. And what another feature you can see here? The last, you can see the structure of a node. You can see the structure of node. So a node is having two information. One is the data which we want to store. Every data structure we are using to storing the data. So this is the data we are storing in every node. And another part in the linked list in the node is the address of the next node. So in this area we are storing the address of the next node. For example, the address of this node, like 5,000 is the address of this node. I am storing here. So that's how one node is pointing to another node. So this node is pointing to this node because the address of this node is here. I'm starting from very basic, but slowly I will move to the very advanced level. So at that time, so that you cannot say that, sir, I don't know this thing. That's why I'm starting from very basic, but I will cross the limits. I will go to the product-based companies also. I will go to the GATE questions also. Okay. So listen carefully every information, and after that you people need to work on those questions. Okay. So this is little bit information about the linked list. Let's see that in more detail. You people tell me. Let's talk about the time complexity. Of singly linked list. I'm talking about singly linked list. This was the singly linked list. Actually, this was shown here. This is a singly linked list. So there are other type of linked list also, like circular linked list, but here I'm talking about singly linked list. I'm not talking about doubly linked list, in which I can go forward and backward, but in singly linked list I can go only forward. Like that, like the structure shown here. Okay. So you people tell me, we have a singly linked list. Let me see how many people you know already this thing. Can you tell me what is the, okay, I'm talking about the worst case time first. What is the worst case time to access one element inside singly linked list? What is the access time? You want to access one element in the singly linked list. What is the worst case time complexity? So order of 1, yes, that is order of 1. If I want to delete the first node, that will take constant time, because I just need to point the head here. To insert the element, to insert the node, I can generate the node, and this node will point out here and head will point out to this node. So this generating a node will take constant time, and pointing this to the front node will take constant time. So total that will take constant time. But for searching and accessing, you need to go through all the elements, all the n elements. We are saying, let's suppose we have n elements in our list. So you need to go through all the elements. And the average case also, we are assuming that as average case also of the singly linked list is order of n. And insertion and deletion at the front is actually order of 1. You already tell that thing. And the space complexity, in the worst case, space complexity. So one node is taking one space, I can say. One node is taking one space. We have n nodes. So total space is order of n. Order of n is taken by a singly linked list to store in memory. Okay. So this is the different time complexity. You already tell me all that. This is the space complexity. Otherwise, these are the time complexity. Average and worst case, you already tell me. of this data structure. Okay, so now let's see the structure of a node. So this is the structure of a node. In a node, again, I have already discussed this thing. Otherwise, we have data and we have address of the next node. So next is showing here. I'm storing the address of next node. Okay, and I have also one pointer head which is pointing to the first node, in the linked list. Okay, and how to create this node in the using in C. Actually, in C language, how we create the node, we use the structure. So this is the keyword, and this is the name of the structure, node we want to create, and we want to store data in that. We want to store some data. Two information I want to store. One is data, one is the pointer. One will be the pointer. So next is the pointer which will store the address of next node, that will store. Okay, that will store the address of next node. So two information we are storing in every node. Okay, so this is how we can create the structure. And this is the head which can point to the starting node, Okay, so this is how we reserve the memory for a node. I want to create this node in memory. Okay, no doubt. This is how we this is the code for a node actually, but we need to reserve the space for this node in memory. Dynamically, we are reserving the space dynamically. Linked list is a dynamic data structure. Okay, so for that actually we can use the malloc function. Malloc function is used in C for reserving the memory dynamically at runtime. Okay, and size of is an operator. This is not a function. This is an operator. We need to tell, okay, how much memory I need to reserve. I'm saying that, okay, I need to reserve the memory of the size of a node. How much memory is required for this node? This much memory is required. Let's suppose I required 4 KB. This much memory, I don't know. So let's suppose, okay, this require 1 byte. This require, okay, let's suppose 8 byte. So total 9 byte is required. So 9 byte will be the size of this structure. This will return actually 9. The size operator will return 9 after looking at this node, and this will reserve 9 bytes, and this will reserve 9 bytes malloc in memory. 9 bytes that will reserve, 9 byte space will reserve, and starting address of this memory location of 9 bytes, should be of this type, should be of pointer type. Pointer of what type? Structure node type, because we need to store the node here. So this address will be of type struct node, and starting address of this node will be stored into the head. Okay, so this is how we store we reserve the space for a node in memory. Okay, if you have any doubt, please ask me. Please write in the chat box if you have any doubt. Okay, little bit I'm moving little fast, I know, but I'm assuming that you know these things. If you don't know, please write in the chat. Okay, please write, then only I will be able to connect with you. So simply I'm repeating, we are reserving the size of a node with the help of function. This function, we get the space in memory after this, and that space will be of this type, and the starting address of that space will be stored here in the head. That's it. And this is the code for generating a node. Okay, so this is a structure of a node. I can say this is the structure of a node in which I am storing data, and the address of next element will be stored in a pointer. So this is a pointer. Okay. So if any doubt, you can ask me anytime. Okay. Otherwise, let's move on. Now, little bit, I'm moving on. Accessing linked list elements. Okay, so this is our linked list. If you don't know anything about the linked list, please let me know. Otherwise, this is our singly linked list. I have mentioned here the head, the address of every node, the last node, the next part of last node is null. We know this thing. because there is no further node, so the here will be null. Head is storing the address of the first node, yes, 4800. This node is storing the next part of this node is storing the address of this node, and this is this is this, so on. This is our data we have stored. Here we are storing the integer. Data can be integer, character, float, whatever is that. So I create a pointer. I create a pointer of type struct node of a node type. Okay, so let's see. Simple. That is very simple actually. See, what is the value in head? 4800. Let me write here 4800. And what is the value at the next? See, every node is this. One is data. This is data, and this is next part. Okay, so what is the next of what is the, I'm talking about this thing now. What is the next of 4800? Next of 4800 is 4900. So let me write here 4900. From head of next I get 4900, and from again I'm talking what is the next of this further. Next of 4900, next of 4900, next of 4900 is 5000. So at 4900 have two information, one is data, one is next, address of next node. So next of 4900 is 5000, that is 5000, or shortcut way 5k. Okay, so the value at PTR will be 5k. The value at PTR will be 5k. The last node point to first node now. After this statement, the last node will start pointing to the first node. This will become the circular queue. Sorry, this will become the circular linked list. This will become the circular linked list. Think again. Last node point to head. So let's see that how this is becoming circular linked list now after this statement. So we know what is the value of PTR. PTR value is 5000. PTR value is 5k. Let me write here. 5k is very nice. That is coming in very low space actually. So here the next of 5k, what is the next of 5k? Next of 5k is 3000. Let me write 3k here. So the next of 3k is actually nil. I'm talking about this address, this position, this address. Here I'm going to store some data. I'm talking about this location now. Actually, this is left hand side. This is left hand side statement. So here I'm storing some data now. What data I'm storing here? I'm storing head value here. I'm storing head value. I'm storing here 4800 now. So what will happen? Means this node will start pointing to the first node. 4800 is this node actually. So this linked list will become the circular linked list after this statement. This linked list will become the circular linked list. We have lots of questions with us, so you can think again and you can answer. Please try this one. We have lots of questions with us. Okay, so please try this one. There is no syntax error. Don't think about the syntax error. Maybe you are saying that, okay, sir, the P is capital. Don't think about that. Please tell me what will be the output of this printf statement. Please think over it. That is important. So head value is 4800. Very easy. I'm here. What is the next of this? Next of this is 4900. And what is the next of 4900? 4900 next is 5000. And what is the next of 5000? Next of 5000 is 3000. And what is the next of 3000? The next of 3000 is actually that was pointing to now this node, that was 4800. So here is 4800, and what is the next of 4800? That is the data at 4800 is actually 10, and you people are actually right. So this will print 10 only. This will print 10 only. Okay, that's great. So let me erase this. So what is this doing? So what this statement is doing, I hope you know this thing. Now this will not point out here. This will start pointing to here. And what will happen to this node? Actually, what will happen to this node? I want to ask this thing. Through this statement, I want to ask, if head will point out to this node, now that is storing 4900, what will happen to this node? What will happen to this node? This node will get lost. This node will get lost. Okay. we will lost this node. We will not be able further to access this node actually. Okay, if this is not circular linked list, if this is not circular linked list, although in this case this is circular linked list, so in that case we will be still able to access, but if this is not circular linked list, we will lost this node. Okay. Okay, so let's this was the accessing of elements in linked list. Now let's perform other operations on linked list, like traversing of linked list. I want to traverse all the data here, means I want to write a code, I want to write a program to print all the elements of this linked list. Okay, I want to print all the elements of the linked list. So how I will print all the element in this linked list is, see, I will start from the head. I will start from this node. I will print the data of this node. Then I will move to the next of the head. Next of head is this node. So I will print data at this node, then next of this node, then next of this node. Keep doing that in a loop actually, and keep printing the data until unless I'm not getting the null. Until unless I'm not getting the null. Okay. So my question should be like, so pretty, I don't know about, you are asking about last point. So in last point I was talking that, okay, if head is pointing to this node, then definitely in singly linked list this node will be lost. This node will be lost because I don't have address of this node anywhere. I'm pointing to this node, and I cannot access this node now anyway if this is a singly linked list. If head is pointing to this node, then I will lost these two nodes actually. I will lost them. They will be treated as deleted actually. Okay, I cannot access these nodes now because I don't have address of these. I can address of further nodes because the further nodes are stored in the address of further nodes are here, but I don't have the address of this node. That's why this will be lost if head is pointing here. This was I'm talking about. But right now I'm talking about, okay, can you write a code? Can you, and anyone share the code to print all the elements of this linked list? Can you please write the code? That will not take too much time. That will be of 2-3 line code actually. If you can write the code and you can show me how you will able to find out. So let me share the code with you. Okay, let me share the code with you. I will ask the question here now. I will ask the question here, and I'm sure that Ravish will be able to give the answer because I can see his first statement. When he write the first statement, I see that, and he will be able to at least give the answer of this question I'm going to ask. Before that, let's see this code, how this code is helping us to print the elements. So until unless our head is not going to null, we are not reaching up to null, we will keep running this loop, and we will keep printing the data. Means first initially the head is not null, so we come inside the loop and we print a, and then what we do, our head is now pointing to this node. Our head is now pointing to this node. Head is pointing to this node, and through this node actually, through this statement, head is equal to head next. What is the head next? Head next is this node. Initially the head was this, so head next is storing the address of this node. So now my head is this due to this statement. Okay, now head is here. Head is not null. Head is not null. No, this is not a null. So I will print the data here B, and again now head will point to the next node, next of head. Now head will point to this node actually. I will print the data again C. Again head will point to this node. This is still not null. I will print the data D. Again head will point to now null actually. Head will point to the next of this. What will be the next of this? That is null. That is null. Null is stored at the last node. At the next of last node, null is there. So head is having null now. We will come out of this loop. So we print all the elements here. We print all the elements. Okay, that's great. We traverse all the elements here. We traverse all the elements. We printed all the elements. Can you people improve this code still? I want to improve this code. I want to add something in this. There is some problem in this code actually. Still there is no doubt this code is printing all the elements, but still I want to improve this code. Can you improve this code? Can you write some line? Can you tell me where the problem is occurring? What should I have to do to improve this code actually. No doubt there's a loop which is initially pointing to the head. I print the data of head, then I'm pointing to next, then next, keep printing data, keep moving until I'm not getting null. So I'm doing this, I'm printing all the data. This is what is required. I want to print all the elements, but still I'm saying, okay, I want to improve this code. I want to improve this code. I should not use the head. To move on, I should not use the head. I should not use the head pointer. This pointer I should not use. If I'm using this pointer, I'm moving this pointer here next time, let's suppose from here to here, I will lost this node. And then further again, I'm moving the head pointer. Further now again, I'm moving the head pointer. And the last, the head pointer will point to the null. So in that case, actually, I will lost the complete linked list. How I will lost? Because I don't have address of any of the node. I was having the address of first node in my head pointer. Head pointer was pointing to the first node. But while traversing here in this code, I move the head. I move the head here. Okay. So if you are moving the head, you are losing previous nodes actually. If you are moving the head, you are losing previous node. There is no way to access these nodes. I don't have address of these nodes. Where is the address of this node? Here at this position. But where is the address of these nodes now? I don't have. I cannot access. I have the address, head is pointing to this node, and through this node I can point to all the further nodes, but I cannot point the prior nodes. Previous nodes I cannot access. So these are getting lost. Every time I am moving the head forward, I'm getting lost these nodes actually. Okay, if somebody asks you to traverse the linked list, that doesn't mean that you have to lost the linked list, because maybe he want to traverse again. One customer come, one user come, and he want to see the data in your database, in your data structure. He prints the data. That doesn't mean that now the data structure will be lost. Another user will also come that also want to see that, and the solution is already given by the River of Rhythm and the Ravish Kumar. They say that, sir, please create a pointer. They say that, sir, please create a temporary pointer. Store the address of the head in that. Now you please move, you play with the pointer. You play with this PTR. So this code is same as this code actually. This part of the code is same as this part. But now I'm using the PTR. This is a temporary pointer which is moving on. Temporary pointer is moving on. But head is still pointing to the first node. Head is still pointing to the first node. Okay, so if head is still pointing to first node, we are not lost the linked list. We have not lost the linked list. So you people are right. We need to take a temporary pointer in which I will store the address of starting node, and I can play with this temporary variable. I can print the data. Okay, so this is better code, and this is not a right code actually. Okay, so this is how you will traverse the linked list. Any doubt you can write in the chat box. Don't hesitate at all. We don't know each other. You can simply ask the question. Nobody will even can laugh on us also. Okay. So let's see insertion in the front of a singly linked list. SLL means singly linked list I'm talking about. So I want to insert this new node at the start of a singly linked list. What I need to do? So what I will do, let's suppose the address of this node is 1000, address of this node is 2000, here is 3000, here is 4000, and this is null actually, and this will be 2k 2000, this is with 3k 3000, this will be 4k 4000, and head is also having the address of starting node, that is 1000. Okay, and what I need to do first I need to create the new node, and I want to insert in the front of the singly linked list. So what I will do, I will store the address of first node here 1000. So this will start pointing here, and now the head can point to the head can point here, or I can say head equal to new. Head will start pointing here. Now our head will become this node, and this will be our linked list. That's it. This is the thing you need to do, and this is done here actually. So can you people tell me, is there any problem here in this code? Please check out the code. whatever I have done here, I try to do that thing here in this code. Can you please think over it and tell me if I'm doing something wrong here? If I'm doing something wrong, please let me know. You can share the correct code or you can share the problem, whatever you can do. So yes, you people are saying there is a problem. Then what's the problem? Amitesh is saying head is lost. If I'm storing 1000 now in head, actually I'm storing new. So let the address of this new is 500. Okay. So I'm storing now 500 in the head. Okay. Now, what will be the value at here? The new of next will be, what will be, I will store here. I will not store 1000 now. The value of head is changed now. That is 500. So I'm storing 500 here. That's it. This is what I'm doing in this code. Simply I'm storing head is equal to new. Now new value is 500. So I'm storing 500 in the head, and this 500 I'm storing, this 500 I'm storing at this position. Actually, that's it. I'm not storing this address. Actually, I lost this complete linked list now. I lost this complete linked list. I left with one node, this node only, which is pointing to himself, So this, there is a problem in this code. So new of next is equal to head. New of first we are executing this, and then maybe we are executing this statement. Okay, the sequence will matter. So what we need to do here is, so we cannot write this statement here. We have to write this statement after this statement. After this statement, if we will write this statement, that will work. Now this is fine. This is fine. This sequence is fine. If I write this statement in the starting, that will create the program. So sequence will matter. This statement should come after this statement. That's it. Okay. So let's move on. Keep helping me. Now I want to insert the element at the end of linked list. Okay, I want to insert at the end. I'm sharing the code also. So let me discuss about the code. There is a pointer. Temporary pointer I'm using because you know that I cannot use the head. If I will use the head, we will lose the linked list. We will lose the nodes. So always we will take a temporary pointer, which will point to the first node. Now I want to insert this node actually. I want to insert this node at the end of the linked list. Okay. So I'm using this pointer, and this pointer will keep moving until unless I'm not going to reach the null. Not going to reach the null. Pointer will keep pointing to the next. After reaching to the null, after reaching to the last node, after reaching to the last node, what I need to do is, after reaching to the last node, what I need to do, I need to add the new node here. So the address of this node, let's suppose the address here is 6000, that will be stored here. Okay, and here I will store the null. That's it. Okay. So this is what I'm doing here. So again, actually I'm making this code is still not perfectly right, almost right, that is, but still there is a improvement I need to do here. So logic we know. We are taking a pointer. That's great because we cannot use the head. This is pointing to the next until unless we are not getting the null. After reaching to this node, I will store this address of this new node. Actually, I have written here 6000 here. In the next of PTR, this PTR will point to the last node then, and in the next of this part, I'm storing null. In the next of this, I'm storing null. That's it. So the main job is to reach to the last node. Okay. So still I'm asking the same question. Can you please improve this code? There is some problem in this code. So actually, if I need to replace this PTR actually with PTR next. Okay, PTR. Next, I'm checking the this part of a node actually. Okay, if I'm not setting this to the PTR next, then my PTR will jump to the null. At the end, PTR will point to the null, but I want to keep PTR pointing to the last node. So what I'm doing is I will stop, keep moving forward when I will find out PTR next is equal to null. When I will find out PTR next is null, when I will find out, okay, this part is null, then I will stop. Rather than I will stop when PTR itself will be the null. If PTR itself will be the null, then how I will store the data at this node, because I don't have the data of this node now. PTR is pointing to the null now. Okay, so at the end PTR should point to the last node. For that I need to write PTR next null. ये ऐसा ही है, इसको मेरे पहले ही देख लेना है कि आगे नल आने वाला है, नेक्स्ट इज गोइंग टू बी नल. सो ये पहले ही देख ले रहा है, उससे आगे नल आने वाला है, इस नोड से आगे नल है, तो ये आगे नहीं जाएगा, ये यही रुक जाएगा, क्योंकि यहाँ पे तो उसको नोड स्टोर, यहाँ पे तो एक नोड अटैच करनी है, उसको यहाँ पे नई नोड अटैच करनी है, तो वो यही रुक जाएगा. उसके लिए मेरे को यहाँ PTR नेक्स्ट लगाना पड़ेगा. PTR नेक्स्ट वी नीड टू इंसर्ट हियर. सो रादर देन PTR वी नीड टू put PTR next. Yes, you people are right. Don't worry. Slowly, if you are not also getting the answer, it's okay. You are getting the idea at least, and that is enough to solve the questions. Okay, I'm making little complicated so that you can think over it. If you will not think, then there will be no learning. Let me tell you, you need to think. If you are thinking, then only learning is happening. So these were the insertion at the end. Let's see now. So this code is not working perfectly. Now let's insert in the middle of the linked list. Singly linked list I'm talking about. I want to insert, okay, I want to write a program to insert a new node after the node which is having B data. Means after this node. After this node I want to insert the data. So how I will do that? Again I will take the temporary variable, and this is the node I want to insert actually. So what I will do, let me write the node here actually, this new node. Here I'm writing. So I will store the address of this node. Let's suppose the address of this node is 1000. I will store 1000 here. Now this node will point out here, and this node must point out to this node. Node must point out to this node. So address of, let's suppose the address of this node is 2000. 2000 will be here. Okay. So what I need to do is I need to keep moving on with the loop until unless I don't find out this data. When I find out this data, I will stop here and I will perform two operations. Then I will store the address of this node in new node, and address of new node in our this node. After B we want to store, so this node will be inserted in between this node and this node. That's it we need to perform. And here is the code also. I'm taking a temporary pointer which is having the starting address of your linked list. Until unless I'm not finding the B data, PTR is now pointing to this. This is not storing B, so I will keep moving on. PTR will point to next. Until unless I'm not finding the B data, I will keep moving on. After keep moving on, I will store what I'm doing here is I'm storing the address, this address actually here, and this and new next here I'm storing the address of this node. Okay, I'm doing that. Simple, that's it. So still I make a little problem in this code. Can you help me to improve this code? Still this code will not work fine. This code is working fine, but there is one important point. See, whatever important point I'm leaving here, let me tell you, whatever point I'm leaving in every question, believe me, that is the interview question. They will ask you the question like this: let me switch these two statements, let me modify this thing, what will happen? That's it. First they will write to ask to write the code, and then they will switch the statement, or they will make little modification to check out that okay, you really understand what you are writing, or you just have crammed the things, or you have just crammed the things. When first we need to write this line, then we need to write this line. So why we need to do that? Why Shivam is saying that, sir, please write this line first and then write this line? Why you write this line first? If you are writing this line first, even your PTR is here. At the PTR of next, at this, you are storing the address of new node, that is 1K, let's suppose. You are storing 1K here. The moment you are storing 1K here, you lost this linked list. You lost the address of this node. You lost the address of because the address of this node was here. The moment you overwrite here the address of new node, you lost this linked list. You lost the address of this node. With this node, you lost everything actually. Okay, so it's better he is saying that, sir, please write it later on. So here it's better first you write the address. First what you do is write the data here. He is saying the address of, let's suppose this node is 2K. Please write 2K first here, so that we have the address of this node. After that you can store 1K here, no problem. So please store this, write this line after this line. Yes, that's right. That's right actually. I hope you understand. So yes, this statement I cannot write. I have to write this statement here. Okay. So now insertion we have done at the beginning, middle, and the last. Let's do the deletion at the beginning of the singly linked list. I want to delete actually this node. So here is the code for that. I have write head now is pointing to this. That's it. Head of next. Head was pointing to this node. Now head is pointing to the head of next. Head of next is having the address of next node actually. So head will start keep pointing to this address, 2K address. Head of next is 2K. So head is now start pointing to 2K. Can you improve this code further? So that's so easy to delete the first node otherwise. With one single statement you can do that. But still you can improve this. I want to delete the node, that's it. I am pointing now here, that's it. This every time I'm saying if my head will move on, I will lose the previous node. Yes, I lost the previous node, that's it. I deleted that, that's it. But I'm saying, can you please improve this code? Please take a temporary pointer to this node. After that, move the head. And after that, free this memory. You are not the actually, what we can say that, okay, means you are not behaving like the right citizen. Like you are throwing the garbage. If you are moving using this statement only, it's like you are throwing the garbage in the city. You are throwing the garbage in the RAM. You have leave this node as it is. This space is reserved in memory. This is not freed. You do not free this space and you move on. You leave your garbage, your program garbage here in the RAM. That could be used for other purposes. That space could be used for other purposes, but you leave it here. It's better. It's better. He is saying that, sir, please take a temporary variable which will point out to this node. After that, you please keep moving your head. No problem. This is same. You can keep moving on. What is the benefit of this pointer? Now with the help of this pointer, I can free the space. We can use the free function to free this memory reserved by this node. Okay. So behave like a nice citizen. He's just trying to say me this thing actually. Okay. So any doubt you can ask me. So let's move on. Now delete. These are the initial conditions. Again, I'm not telling you actually initial condition. There could be some initial conditions also. Maybe the head is null. If the head is null, we will return simply because nothing is to delete. And there may be only one node. If we have only one node, if we have only one node, then this will be null actually. If we have only one node, this node, then this part of the first node will be null. So that this next of the head will be null. Then free the head and head will point to the null. So these are some initial conditions. I do not tell you actually. These also we need to check. So before starting to delete some node, maybe we don't have any node, then we will simply return. Maybe we have only one node. If we have only one node, so our head will be in that case will be null, and we will simply free the head. So these are some initial conditions, that's it. Okay, now delete at the end. At the end of singly linked list, I want to delete the last node actually. I want to delete this node. So what I need to do, I need to move from here to here to here up to this node, and here I need to store the null. That's it. This is what I need to do. So here is the code for that. I take a temporary pointer rather than using head, and that will keep moving until I don't get the null, and after reaching to the null, I simply free that node. And I store the null in the PTR. Okay, I simply store the null in the PTR. Still there is some improvement needed in this code. There is some little improvement needed. If you want to change some statement, actually this code will not work fine. There will be some problem here. If you can think over it, why I'm always asking again and again this question, I can directly tell you the solution also, because that is actual learning. If you're thinking, you're getting the answer or not, that doesn't matter. If you're thinking, that is the learning actually. That's why I'm always leaving something in this, in the code. Can you help me in this? Can you improve this code? So PTR starting from here. So if PTR next is null, then if PTR next is not null, I will move on. I will move to the next PTR. Then again, I will check is not null. I will move on. Okay. And according to this code, actually, I'm reaching here. My PTR is reaching here. And after reaching here, I'm deleting the node and storing the null here in these two statements. But the pointer should be actually here. The PTR should be here. PTR should not reach up to here, because I want to delete this node. PTR should be here. PTR should point to the second last node. PTR should point to the second last node actually. Okay. But according to this code, PTR is pointing to last node. I want to delete this node. So what I need to do is, they says that, sir, please replace this PTR to next. Please replace this with this. PTR next of next. PTR next of next. Please replace this thing with this thing. So now, after standing here, I am checking, oh, PTR next is this node actually. If PTR is here, then PTR next is this node. And what is the next of this node? That is null. If this is null, I want to remain at this node actually. Why I want to remain at this node? So that I can delete this node. I can say that, okay, please free the PTR next. Please free this node. PTR next is this node. If PTR is at the pointing to this node, PTR next is this node. So I want to free this node. I want to store the null here. Where? At the PTR next. PTR next is this location. So I store the null here. Okay. So I don't want to move to the last node. I want to move to the second last. That's why I need to write. I'm checking one step ahead. That's why I'm checking one step ahead. Okay. So that's why we need to replace this thing with this thing actually. Let's move on. So this is the right answer. You already given the right answer actually. So let me erase the board and show you, so that you can, if you want to check out later also, you can check out this thing. Okay. So let's delete from the middle. Let's delete from the middle of the linked list. Maybe after the node which is having C data, this data, I want to delete a node which is having C data. I want to delete this node actually. What I need to do? First, I need to come to where? See, I need to come at here. I need to take a temporary pointer, set a loop until unless I don't want to reach here. I want to reach then one node earlier to here. Okay. And I want to store the address of this node here. That's it. Okay. This is what I need to do. And I will free this memory. I will use the free function. I will free this memory. So 3 tasks I'm doing. One is I'm creating a temporary pointer. with loop I'm going to the just immediate first node of this node and storing the address of next node, this node here, and making free this space. That's it I'm doing. And here is the code also for the same thing. I've taken a temporary pointer which is pointing to the head, or PTR you can say, you can take T, any pointer you can take, and I'm checking, okay, PTR next, and the data of next is C or not. If that is C, then I am moving to the next node. Okay, so benefit of this statement is that, okay, I will remain at the second last node. Which node I want to delete? I will be at this node. If I'm writing this statement, you can check out. Okay, so after that I'm simply storing the address of this here and deleting this node. But still there is some problem here. Can you crack this code? There is some problem here. Can you crack this code? Still there is some problem. I left it for you people so that you can think over it and you can learn. Please think over it. Take in the pointer, temporary pointer, PTR or say T. Okay, T you can write, and T of next is this node actually, and I'm checking data here. So after standing here, I'm checking the data here. This is what I want. So after standing here, I'm checking data here, and if that is matching, until unless that is not matching, I'm keep moving on. After that is matching, I'm performing this task. So I think there should be problem somewhere here. So we take up another pointer here, which is pointing to the immediate next node, and this T is now will point to this node by using T of next, and we will free this node. That's it. So there is no problem in this code. Every code don't have any problem. Every code should not have any problem. The river of rhythm also says no problem. Yes, this code is working fine. That's it about single linked list. Now let's talk about the circular linked list. Okay, and let's talk about a circular linked list. Simple. That is just like single linked list only. The address here, there is no null now. We have the address of first node now here. We have the address of first node. That's it. This is our single linked list, and that's it. We finish it. Okay, so let's move to the doubly linked list. Let's move to the doubly linked list. In doubly linked list, here every node is pointing to the previous and the next node. Okay, both the previous and the next node. That is, for example, this node is pointing to the previous node also, having the address of previous node and having the address of next node. So the structure is like this. In doubly linked list, we have data, and we have the address of previous node, and we have the address of next node. So this is the structure of a node in a doubly linked list. Okay, and here will be null actually at the last, and at the front also there will be null. And let's suppose the address of this is 1K, 2K, 3K, 4K. So the head is having 1K, and address here will be 2K, the address of next node. And what will the address here? 1K, the address of previous node. What will be the address here? 3K, the address of next node. Here 2K, address of previous node. Here 4K, address of next node. Here 3K, address of previous node. There is no node further, so null is here. So this is the structure of doubly linked list. Okay, this is the structure of doubly linked list. That's it. Now it's exam time. Okay, so I will take first some company based question. Actually, I find some company based questions which were related to the GATE itself. So that's why I involved that questions also, so that you can feel that, okay, you can solve those questions also. So let's move to the first question. Can you people tell me? So this question is actually, you people need to tell me what is the function of this code. Please check out this code, read this carefully. Tell me the function of this code, what this function is doing, what this function is doing. Please read this code, try to find out what this code is doing. This question is asked in so many companies. Disho, Goldman Sachs, so many companies are there. Make My Trip, Joho, but so many, these all company ask the same question. So think over it. Tell me what is the function, what is the job of this function, what this function is doing, what this function is doing. So now we have done actually with the linked list. We have done enough practice. Okay, now we will solve lots of problems, and actually you people will be able to solve the lots of problems actually if you know what how everything was happening in previous slides. So try these questions now and please write in the chat box. Everyone, please write in the chat box. This will also help you in the company. Believe me, we have covered all the basic, most important things in linked list. And that will be proved with the help of the questions I'm taking here from product-based companies, and from the GATE, I will take many questions. And you people will be able to solve those questions actually. You people will be able to solve those questions. Please try it, think over it. With one question, you will solve two questions. One is also in GATE. So what we are doing here, you can take this diagram, you maybe think over it. We are reversing the singly linked list actually. We are reversing the singly linked list here. How we are reversing the singly linked list? Very easy. See, we get the head pointer, of the linked list. Okay. We create two more pointers here. One is pointing to the previous node, one is pointing to the next node. Okay. So maybe I have a linked list like this. So this is my previous node, this is my next node, this is my present node. Okay, maybe head is here right now. So head is here, I will keep moving. Initially, the previous will be null actually. Okay, currently I'm here. This is my previous node, this is my next node. Okay, we know this thing. So these are the pointers to store the address of previous node and the next node actually. Okay, these pointers are created. Initially they have null because there is initially they are initialized to the null. After that, until unless head is not going to null, this loop is moving on. When head will be null, then we will come out of this loop. Okay, so what we are doing here is in the next node we are storing head of next. So head was pointing to this node actually. Now in the let me write here. Okay, next node will point out to this node by executing this statement, because head next is 4900. So next of head will point to this node. That's it. And what we are doing in this statement, head of next is pointing to now previous. Okay, now we are storing here what we are storing here in the head of next. This is the head of next space, but this is at the left hand side. So I'm using this space now. I'm storing something here, but I'm showing previous. Actually, right now in the previous we have null. So we store null here. Okay. So now this node is not pointing to this node. Now you can see this node is having null. So this link is lost. Okay, but we already have the address of this node in this pointer. Okay, don't worry. So here in previous we are storing the head. Now previous is pointing to the head actually. So our previous is pointing to head. So this will become our previous. Our head is pointing to this 4800. 4800 will be stored in the previous. So this pointer will point to this node. This pointer is pointing to this node, and where the head is pointing to the next node. Head is pointing to this node actually. Here is our head. After executing these four statements, again I will come back in this loop, and this statement actually, initial statement, what that will do, that will move this pointer to this node. That's it. Okay, that's it. So here I'm not pointing here. So again I will execute the same procedure. What I will do, see what I will do. Again I'm repeating the same procedure now. Now earlier my head was here. I move the head 1 point. Previous is pointing here. next is pointing here, okay. And now I'm executing these three statements. What I will do, see what I will do. I will store in the first statement, you can see in the first statement, in the head of next, I will store the address of previous node, which is 4800. So this will start pointing to this node. Okay, this node is pointing to the null now. This node is pointing to the null. And this node is pointing to this node after executing this statement. Okay, and what about this statement, this third statement, previous equal to head? Now after doing this, our previous will become this. Again we will move one step forward. Okay, head will move here, next head will move here. Okay, that's it. This is what we are doing. And in this statement, this will become head, and again when we will move on, now next of head, this will be this. So you can see here what we are doing here is this node start pointing out here. Again now this node will start pointing out here, this node will start pointing out here, and at the end actually I will be pointing to the last node. Previous will be pointing to the last node, which will be the head of the linked list. So previous will point out to this. So you can see we have reversed the linked list. We have reversed the linked list. Otherwise, I have one more question for you. And this is also from one product-based company, that is Morgan Stanley. You can try this question. Can you tell me what this function is doing? Please keep trying. You are getting answer or not, that will not matter. Right now, that doesn't matter. You are learning right now. Okay. So right now, the answer doesn't matter. Right now, what matters is you are trying or not. Please try. Right or wrong doesn't matter. If you're trying, you're learning. That's it. Please try it. Please let me know. These are product-based company question, no doubt. And believe me, you people can solve it. Why am I asking from you people to solve it? If I will solve it, you will not get the confidence. But if you will be able to solve even a one question, you will get then only you will get the confidence actually. Okay, please try it yourself. Please let me know what is the function of this. What is the job of this particular code? What this code is doing? So we are actually deleting the alternate nodes. Here. How we are deleting the alternate nodes? You can think over it now. This now also. You can execute it and you can think over it. So PTR, P is pointing out here. P is pointing out to the head. And until unless the next of P is not null, we will keep moving. And now Q is pointing here. You can see Q is pointing to the P of next. And P of next is now pointing to Q of next, which is this. So I will store the address of this node here in this statement. I will keep doing this until unless I will not find out the null to the null. I will not find out the null to the next node actually. And after every if statement, the P is here again. P is here. So what I'm doing simple. There is no null here. And I take up another pointer Q, which will point to the next node. I will simply store the address here of the next of this node, which will be the Q of next, in this statement. And after that, now actually P will point to this node because P is pointing to this. So P of next will be this node. So P will point out to this. Again, we will repeat the same procedure. So what we are doing, deleting the alternate node. So this is Morgan Stanley question. Although they asked the question that, okay, please write the code to delete the alternate nodes, Okay. Yes, B and D is lost. Shivam, you are right. So please try this question also. One from good companies, Amazon, Microsoft. You people can try it, believe me. Please try it. You need to delete. Okay, what the question is, let me tell you. This is the question, you can read also. Otherwise, the question is like that. We don't have the header. Head we don't have in this linked list. This is the linked list we have. We don't have head here. We have a delete pointer here. This is the pointer which is pointing to a node which we want to delete. I want to delete this node. What I have? I have the I have this node address. That's it. What I have the address of this node. Okay. I want to delete this node now. I have the address of this node only. I want to delete this node. So what should be, okay, what should be the logic? If you know the logic, the answer is of only 2-3 lines. Think over it and write the answer. So first think about the logic. What should be the logic? I want to delete this node. I'm standing at this node. I'm not standing at this node. If I'm standing at this node, then simply I could do is that if del is here, what I could do, del of next is equal to del of next of next. That's it. This was working fine if del was here, but I am standing on here. I want to delete this node only. So I need to store the address of this node here in this node, but I don't have address of this node. I need the address of this node to store the address of this node here. Then only I will be able to delete this node. But I don't have address of this node. I have address of this node, C node. What should be the logic? That's why this question is in product-based company. There is some logic you need to think over. These people are stealing the questions from the GATE itself. Okay, that's why I steal their questions. I bring them here. So I'm writing the same thing what he has written in the chat box. So he write that, okay, del of data is equal to del of next of data, and he's then making free del of next. So let me see what he's trying to do. He's saying that, sir, store the data here. He's storing actually the data of the next node. He's storing the data of next node. Next node data is D. He's storing D here. And after that, after storing D, he's deleting the del of next. Del of next is this node. He's deleting this node. Yes, you are right actually. This must point to the next node. This must point to the next node. That's it. Okay, otherwise you are fine. You have given the right answer. So simply what actually River of Rhythm is doing is simple. What he's trying to do is, what he's doing is, he say that, okay, if I cannot delete this node, what I can do is, let me copy the data from here. He copied the data of next node and he deleted this node. He copied the data of this node here. So D is here. So now this node becomes this node actually. So he just delete this node rather than, because he cannot delete this node, so he deleted this node. Before deleting this node, he copied the data here from here to here. And this node will point out to the next node. Now, this node can point out to the next node, no problem. So he deleted the immediately next node, because we cannot delete this node because we don't have an address of this node. So he cleverly deleted this node by copying the data. Okay, that's it. That's the right answer actually. That's the right answer. So the same thing written here. So we take a del of next. Del of next is actually now T is pointing here according to this code, and we store the data of this D here in del, and after that we simply del. This is actually pointing to the T of next. T of next is the next node of this, next node of this, right here. That is null, so null will store here. Okay, and after that we free the T. After that we free this node. That's it. Okay, so we also steal the question from these companies. They steal our question from GATE, so we also steal. That's it, and that was right one. So let's start with the GATE questions now. I think I should not help you people. This is GATE 2004 question. I think that you people are giving the question of product-based company, answer of product-based companies. So please answer this question. Sushant, simply, okay, let me explain you by wording. Meanwhile, other people attempt this. So what we were doing in the last question is, it's like that, okay, I'm standing at particular node. I do not know the address of previous node. So what we are doing here is, I want to delete the immediate, I want to delete myself actually, I want to delete myself. So what I'm doing is, actually I'm copying the data of next node to in my data, replacing my data with next node, okay, and I'm deleting the next node actually, okay. Indirectly what I'm doing is I'm deleting to myself, because my data is lost, my data is lost. The structure of all the nodes is same, the structure of all the node is same. So if I'm deleting, I cannot delete myself, because I don't know the address of previous node. So because I don't know the address of previous node, that's why I cannot delete myself. So what I am doing, I'm deleting the next node. First I'm copying its data in my node, I'm deleting him, okay. So it's behaving like, okay, that I deleted myself, because my data is deleted, although my data is deleted, because I have copy paste the next node data in my node, okay. So this is how the previous question was working. So we get some answer here. Everyone please keep trying, keep trying, keep trying. That is the most important part. Pratik, I'm expecting from you, please. Oh, you get the already given the answer, that's great. So Pratik is saying D, and Shivam is also saying D. Amitesh is the right person actually here, I think. Amitesh is the right person. I'm coming to your question, Sushant. That is a nice question actually. I'm coming to that. Before that, let me finish this question. P is the singly linked list, and Q is the pointer to an intermediate node X. So I don't think, yeah, answer is A, but I don't have diagram here, okay. So P is a singly linked list, we have a singly linked list, and Q is a pointer to some intermediate node X, okay. In the list, what is the worst case complexity of the best known algorithm to delete the node X? I have some linked list, okay. P is a singly linked list, and let Q be the pointer. Q is pointing here, Q is pointing here to this node, okay. I want to delete this node now. I want to delete this node. The same question was asked in the Microsoft, the previous question you solved actually. So what is the time complexity here is, see, yes, you people are right. So we can do it in constant time actually. We can do it in constant time, because Q is pointing to the intermediate node, previous question itself. So A will not come here, you people are right. A will not come here, you people are right. D is the right answer here, because the explanation is this, the same thing what we have done here. We have a pointer to a node, and this thing will take actually, this operation will take constant time to perform it. This operation will take constant time to perform. So this will take constant time. This operation will take constant time to perform. So what we are doing, we are deleting the immediate next node, rather than deleting this node, copying the data of this node here, and this all operation will taking constant time. You people are right, you people are right, and I have written wrong here actually. So A is not the right answer, D is the right answer here. D is the right answer. Very good, very good. D is the right answer here. Let's move to the next question. This is again from GATE 2004. In 2004 and 2006 also, 2003, these were the years actually when the most tricky questions were asked actually. One of the most hard questions also were asked in these years. Please try this question. Please try this one. But Amitesh, he is asking the worst case complexity of the best algorithm. Worst case complexity of the best algorithm. So best algorithm is taking order of 1 time in worst case. Best algorithm is taking order of 1 time in worst case. Okay, and what is the best algorithm, which we discussed just immediately in the previous question that was we discussed already. So we write only 4 line of code. So 4 line of code will take constant time to execute. So in even I will say that The previous question will take constant time in every case, best case, average case, worst case. Okay, so it's theta of 1. Actually it should be theta of 1. Okay, Ravish is asking, cannot there be more than one nodes after that in worst case? Cannot there be? I don't understand. Cannot there be more than one node? You please, people, please try this question and write the answer. Meanwhile, I'm trying to read your queries. You please write the query and forget about that. I'm thinking over it. That is my duty now. You please keep thinking over these questions. Okay, that is your duty. So this is theta here. So this is actually theta. Theta of n, theta of n log n, theta of n square. Okay, this is n square. In made easy book, you are saying that that is, I think, order of n. So that is wrong actually. We have proof with us. We have proof. We have done that. Actually, I have taken that question from the internet, answer also from there. But we are right now, we are solving that problem, and that is coming order of 1, and that is order of 1. We have solved it. Somebody is saying something, that doesn't mean that okay, that should be right. Otherwise, I also write order of n because I also copy the question from the net only. These questions are copied from the net only. But we have analyzed that. Now that is order of 1. I don't understand what Ravish is asking about. And another question was again from Sushant. Can it happen in doubly? Yes, if that can happen in singly linked list, that can happen in doubly, even though we don't need to do anything. We know the address of previous node also. We know the address of previous node. There we do not need to use this logic. We can directly delete the node. Because we know the address of previous node, we know the address of next node. We can directly point out. Because we know the address of previous and next, and previous node need to access the next node. So in doubly linked list, even we do not need to do this. We do not need to use this logic also. We can directly delete the node and point out. In the case of doubly linked list, I'm talking about previous question. Okay. So we are, okay, let me check out. You're discussing that thing. So please take the snapshot of this. So let me check out once again the question if you are discussing. So we want to delete this node only. Even though we have many nodes here, we are not bothered about that. We can simply copy the data here and point out this here. What's the problem your people are facing? We don't need loop here. This is not an array. We are simply storing the address of this node here. That's it. And we are deleting this node. We are copying the data here. We are copying the data here, pointing this node to here. Now we can point, and we are deleting this node. So this will take constant time. What's the problem? Even I have 1,000 nodes here. Even I have 1,000 nodes here. No problem at all. Even I have 1,000 nodes here. That is not making any impact. I'm not shifting those nodes. I'm simply copying the address of this node here. Okay. I'm simply copying the address of this node here. That will take constant time. Okay. So please tell me the answer of that. The answer is order of 1 only. That is sure. And please answer the question. Answer for this question. Everyone, please try it. No, Amitesh, in this actually, they have mentioned that we have the pointer to a node which we want to delete. We have specifically mentioned the pointer P, which is pointing to that node. Okay, so they are specifically mentioning this thing. If they are not pointing that pointer to us, then only we need to come from the starting. Okay. But here we already have the pointer here in the pointing to that particular node. Okay, so you please can think over it, and I'm not going in more detail. And what I can say is that you can think over it, and please, if you still have doubt, please write in the comment section, and I will reply there only regarding that question. So from my side, still the answer is order of 1. Order of 1, I'm giving the answer. And still, if you have doubt, please write in the chat box. Not in the chat box, in the comment box. There we can discuss. Here, let me move to the next question. So you people are giving the answer of A. Amitesh is saying A, and Mukesh is also saying A. So let's see what is the question. Consider the problem of reversing a singly linked list. To take an example, given that we want to reverse this singly linked list. You already solved this question. This was the first question, if you remember, which I asked you, what is the code for reversing a linked list actually. Okay, so this is related to that only. So consider a problem of reversing a singly linked list. So we are reversing this linked list like this. Okay, which of the following statement is true about the time complexity of the algorithm that solve the problem in order of 1 space? Means I'm not taking any extra space. I need to replace this data here only. I need to replace the data here only. So which of the statement is right? Okay, and you already have reversed you have already seen the code for reversing a singly linked list. So this is the code actually, not this one. This is the code for reversing the singly linked list. Here you know that you were moving from starting to end. There is a loop here. So until unless head is not going to null, so head is starting from the first node and going up to the last node. So this loop will take order of n time. All other will take constant time to execute. So this code will take order of n time to execute. Okay, so reversing a linked list will take order of n time to execute. So the same question is asked in the GATE, and so that's why the best algorithm actually to solve this problem will take theta of n time. That will take theta of n time. The best algorithm will take n log n. No, that is taking n time. We already seen this type of algorithm which is taking n time. So why should I have to say n log n and n square? Okay, it is not possible to. That is possible to reverse the linked list. Okay, with this space, we have already done this in our first example. So A option is the right one, and you have already have the code of this for this problem. First question was the code for this problem. So let's move to the next one. So A is the right answer. Yes. So next, move to the next one. GATE 2020 question is that. Please try it yourself. Again, please try it. Keep trying it. Important part is you people are trying. That is the most important part. You people are trying it. Keep trying it, please. What is the worst case time complexity of inserting n elements in an empty linked list? If they are talking about linked list, they are talking about singly linked list. Okay. If they are saying linked list, they are talking about singly linked list. If they want to talk about circular linked list or doubly linked list, they will mention it. Okay. So what is the worst case time complexity to insert n elements? We want to insert n elements into an empty linked list if the linked list need to be maintained in sorted order. If we want to maintain the sorted order, and I want to insert n elements. So Amitesh says C. Any other answer? Ravi says C. C. Okay. So you want to insert the element so that you want to maintain the sorted elements. Yes. Actually, you are taking an every time you need to compare with all the elements. Every time you are inserting a new element, you need to compare it, you need to find its position, and you need to store that element there. Okay. So maybe first element is taking 1 time, second element is taking 2 times, third element is taking 3 times, and so on. So last element is taking n time, because every time you need to search the right position of that element. So this is actually n into n plus 1 divided by 2, which is asymptotically n square. Okay, according to this you are right. According to this, actually you are right. Again, this question is also having some statement issue. We can say that actually this question is having statement issue. They don't mention that, okay, these elements are given one by one or all together. if the elements are given one by one to insert in the linked list, then that will take n square time, which is the answer you are giving actually. Okay, but they don't mention that thing. They don't mention that we are giving it one by one. They don't mention that what is the worst case time complexity of inserting n elements, inserting n elements into empty linked list. They don't mention they are giving one by one. If they are giving one by one, so this will take this much time, that will be n square. Thus option C is correct. If they are giving all together, if they are giving all together all the elements, then we can sort the elements. We can first sort the elements, and sorting the element will take n log n time. After sorting the elements, I can insert elements into the linked list, that will take n time. So total that will take n log n time. In that case, B is the right answer actually. So again, there is some the statement is not correct of this question. So the question answer can be B or C. If the elements are given all together, then n log n, because we can sort them, and sorting take n log n time, and inserting element in linked list then will take n time. So n log n time, otherwise n square. Let's move to the next question. Please try this. Okay, so please let me know which of the following operation is performed more efficiently by doubly linked list. More efficiently by doubly linked list than rather than a singly linked list. Linear linked list means singly linked list is talking about. Doubly linked list will help you will perform which operation more efficiently. Delete a node whose location is given, search an unsorted list of a given item, insert a node after the node with the given location, traversing the list to process each node. So okay, actually A is the right answer here, but again A will take little more time than the doubly linked list, but still actually that is also taking the constant time here, because the location is given to us. Again the same question come, the location is given and we are deleting that element. Okay, although the answer given in the key is also A, whatever you are mentioning here. Okay, so let's move on. You can think over it. ISRO 2013 question. Keep answering the question. So what is the what these following steps are doing? Pop operation in stack, removal of node, inserting a node, modifying an existing node. So which is what we are doing here in this code. Get node is generating a new node for us. That is generating a new node for us. C is the right answer. So we are simply inserting the node here. Actually, we are generating a new node, and this is list is actually just like a pointer to the head, which is pointing to the list actually. So now we generate a node whose address will be in the P pointer, and we store the data in that node, new node, and the list actually this new node will start pointing to the list, and this list, this is a pointer which will start pointing to this node. So we insert this node actually in the starting of the linked list. We insert a node in the starting of the linked list. Okay, yes, you are right. C is the right answer. So please try this one. This is ISRO 2018 question. So simply let me tell you the question. Okay, we have a doubly linked list structure. This is the doubly linked list structure. We know that in doubly linked list we have data part, value part, and one pointer to which point to the next node, and one pointer which point to the previous node. Okay, so here backward node is pointed by this pointer, forward node is pointed by this pointer. Now where forward and backward represent the forward and backward link to the adjacent element in the list, yes. Which of the following segment of code delete the node pointed by X? So we want to delete the node which is pointed by this X pointer from the doubly linked list. From the doubly linked list, it is assumed that X points to neither the first nor the last node. Okay, so simply which of the following code will actually help to delete this node. And he is saying that this X is not the last node, not the first node of the doubly linked list. Okay, he want to delete this node. To delete this node, which of the statement he need to write? He is asking this thing. Which of the statement he need to write to delete this node? Please try it. So we know that how that will happen actually. The address of here I will store the address of this node, and at this position I will store the address of this node. Okay, we know this thing. This is going to happen. Okay, that's it. This is what we need to do. Here I will store the address of this node, and here in the previous of C I will store the address of this node, and in the next, or I can say in the forward, they are using the word forward in the place of next, and backward in place of previous. So in the next of this node I'm storing the address of this node, and but right now I'm having the address of X, the node which I want to delete. Yes, I can access the address of this node also from this node, because the address of this node is here and the address of this node is also here. So which statement is right? So we get the answer also from Amitesh, River of Rhythm, and Divyanshu. All says A, and A is the right answer. Let's see how A is the right answer. So we are going to the A of backward. We are checking the back side of this X. So actually this position is having the address of this node. Let's suppose let me give the address. This is 2K, this is 3K, let's suppose this is 4K. Okay, so this is having this position is having 2K. This is having data 2K. Now he's saying he is using this data. He's saying that okay, he'll get 2K from here, 2K. And 2K, the forward of 2K, he says that here the forward of 2K is this. Okay, so we get this actually, this position. At this position, we are storing something that is at the left hand side. What we are storing is, we know what we need to store. We need to store the address of this node. Actually, we need to store 4K here. Okay, he's doing the same thing. What he's doing storing X of forward. So this 4K we know that is stored here. This 4K is stored at here. So X of next, X of forward is having this address. This is giving 4K. So we store 4K here. One thing we done, and second thing we done is we need to store here the address of this, means 2K we need to store here. How we are doing? We are taking X of forward. X of forward is this, which is 4K, which is the address of this node. 4K we get, and 4K back at the back is this. At this position we are storing something. What? X of backward. X of backward is 2K. We are storing the address of this node. Okay, we are storing the address of this node. So this node is automatically get deleted. So A is the right answer. You people are right. Let's try the next question. Please try this one. Keep trying. The more question, if you will keep trying, I will keep giving you more questions. And if I will stop that. If you people will stop, then I will also end the session, because the time is almost also over. But if you will keep trying the answer, giving me the answer, so we have many questions with us. We can solve these questions, and that will not take too much time actually. And we will be able to solve all the questions actually. Answer is A. That we have a 2 pointer. One is F, one is L. F is pointing to the first node, L is pointing to the last node, and that is asking the time of which of the following operation depend upon the length of the list. So deleting the last element. If I want to delete the last element, I need to traverse up to the second last element actually, so that I can store null here. So for that, deleting the last node. For that, I need to have the address of second last node. So to find the address of second last node, we need to traverse all the linked list. And so deleting the last node will depend upon the length of the linked list. That will depend upon the length of the list. So you people are right. So A is the right answer. Yes. Try next one. Here we have a doubly linked list. The number of pointers affected by inserting a new operations will be new node. Okay, you can write. I want to insert a new node. I want to insert a new node, and how many pointers will be affected? Number of pointers will be affected if I am inserting a new node in a doubly linked list. How many pointers will be affected? So please take the snapshot of this question. I'm moving to previous slide, and please answer for this question. I'm moving to previous slide. So Divyanshu is asking why not C for previous answer. So let's see, check out the C. Add an element after the last element of the list. See, we have the address of last element. We have the address of last element. So what is the size of this linked list? That is not impacting us. Simply I can generate a new node, and I can store the address of this node here in 2k, and here I can store null. So the length of this list is not impacting me to insert this node. Okay, I can insert the new node because I have the address. They provided the address of the last node. Okay, so that's why C is not impacting. And I get one answer from River of Rhythm, and River of Rhythm is right. The answer is D, none of these. Actually, adding one node will depend where you are adding the node. Actually, where you are adding the node. If you are adding the node in the middle somewhere, then number of pointers affected will be different. Okay, you can say, okay, 4 pointers will be affected. One from here, one from here, one from here, one from here. Okay, but if you are inserting in the middle, but if you are inserting in the front, in that case, number of pointers will be affected here is this pointer will be affected. Actually, this pointer will be affected. Okay, 1 or 2 pointer you can say, okay, head will be here, you can say that. So 2 pointer will be affected. Or if you are inserting here, again number of pointers will be different. So if you are inserting in the starting, in the middle, in the previous, in the last, so that will depend where you are inserting, that will depend on that. So we cannot say anything about that. So none of these will be the right answer. So let's move on. D is the right answer here. Check out this one. So this is about the circular linked list. Which statement is false, which statement is true? Actually, this is asked in the context of time complexity. Means if we are performing this operation or this operation, if that is taking more time, then we should not do that. We should not do that. That is asking in this context. If that is taking constant time, it's okay. If that is taking order of n time, then that is not okay. Okay, it's like that. So both are false. Actually, both will take order of n time. This will also take order of n time. This will also take order of n time. Okay, please check this thing. Okay, I'm not going to explain this. Whatever members we have right now with us, I believe all are actually good member. I can see here. All are actually good members here who have enough knowledge. Now you can check it yourself. This will take order of n time. This will also take order of n time. That's why both are false. So you are given the answer B, and you are giving the right answer also. Yes, both are false. Check out this one. This is good question actually. This is a nice question. This is the nice question actually. I have seen this question asked in various interviews also. People love this question to ask in interview also. The right answer is D actually. This will take constant time to find the element in this list that is neither maximum nor minimum. We have a list of elements. We have a linked list of elements. And we want to find an element which is not the maximum, which is not the minimum. Okay. What we need to do is we can simply take starting 3 elements. Let's suppose this is 10, this is maybe, I don't know, 5, this is, let's suppose 15, I don't know. So I will compare these 3 elements, and I will say that, okay, I will return this 10. I will return this 10. I will say that 10 is not the maximum. 10 cannot be the maximum because someone else is also there who is more than 10. Although maximum can be someone else also, even there can be 50 also, but 10 is not the maximum, that is right. And 10 is also not the minimum because 5 is also present in the list. Although 1 can also be there, 2 can also be there in the list, but I'm not bothered about that. I'm confirmed that 10 is my answer because 10 is not the maximum, 10 is not the minimum. So I just need to compare three elements. I need to just compare the three elements. So to compare the three elements, you need constant time. You need constant time. Okay. So order of 1. So try this one. And please try this one. This is little tricky question. Again, so I think this is log base 2, log base 2n, not log square n, log base 2n. So this question is for your homework. You please try this at home and please write the answer in the chat box. In the not in the chat box, in the comment section, please write this the answer of this question. Please try it yourself. This is a nice question actually. And let's move to the next one. So this one is little easy one. You can check out this one. Previous one, please answer the question. Answer in the comment box. Check out this one. The concatenation of two lists is performed in order of one time. Which of the following implementation of a list should be used? So I want to perform the concatenation is in order of 1. So which type of linked list I have to use? In the singly linked list, doubly linked list, circular doubly, or array implementation of list? I want to concatenate two lists actually. One after the other we can attach. Yes, C is the right answer. In circular doubly linked list we can do that. Yes, Ridham, that is right. Yes, Amitesh. So let's move on. And that's it. This is the last question. Please take the snapshot of this question also. And I'm not going to discuss this thing also. And please answer the answer for this question also in the chat box. This is also the nice question. This is also the nice question. Please answer in the chat box. That's it for this session. I hope you people enjoy the session. So tomorrow we will come with another session from asymptotic notations. I will discuss. Again, I will discuss in very detail. I hope you get lots of useful information from this session. So thank you for being with me from last more than 2 hours. So take care. Good night, everyone. And you can check out this GATE test series. Otherwise, you can register for our this GATE crash course, which is free of cost. The link is given in the description. And we are coming with AM3 also, All India mock test, in which the student from all around the India is participating, and that is free of cost. AM3 is free of cost. You can appear for that also. And this series is also free. You can register for this series also. You will get more details, more information also related to this series. Okay. So okay, thank you everyone. Good night. Hello everyone. My name is Puneet Kansal. Welcome to the GATE crash course. In this session, we will discuss about the stack and queue. We will cover stack and queue in very detail. So we will start from very scratch actually, and we will reach to the gate level. Okay. So prerequisite for this session is actually nil. You do not need to know anything in advance. We will start from scratch and go to up to the gate level. As usual, we are doing in other. You do not need to know anything. So as usual we are doing with other sessions also. So every session we are covering each topic in its full detail. So here also we will cover stack and queue in its full detail, so that you will be able to solve the
gate level questions actually. Okay, so I will cover all the most important points about the gate, about the stack and queue in this session. From 6 to 8 we will cover this session. So let me present my screen. So in this session we will cover stack and queue, and this is the part of actually gate crash course, which is the series going on on this GFG gate channel. And you can register for this course actually in the you can check out the link in the description and register for this course. This course is actually free. And if you are actually, if you are new here, let me tell you, uh, this course is beneficial for students uh, who actually are saying that okay, they are not enough prepared for the gate. They are not sure okay they will be able to clear the gate exam or not. So if you are taking this course, then you will be definitely will be able to at least crack the gate exam, because here we are covering the five most important topics, five most expected topics from every subject in this course. Okay, and the detail of this complete course is, you can find out the link in the description, and all the detail is given there. And even if you are a serious gate aspirant, means you are preparing from last many months or maybe years, then this course can help you to revise the most important topics. Okay, so this is going to be beneficial for you in both the cases. If you are new, then still that will be beneficial, and if you are already working on it, then that will be beneficial. And one more, if you want to just learn the concept of DSA, you are preparing for companies, and you want to learn about stack and queue, then again this session is going to help you, because we are going to cover each and every important point about the stack and queue. So after that, even you can jump to the company based problems also after this session. So three type of students are taking benefit here, who are not sure okay they will be able to clear the gate exam or not. They will get benefit. The second one is those who are very serious, they can revise their concept here. The third one is they are not interested in gate, but they want to just learn the DSA concepts. So for them also, this video will help you actually to understand each and everything about the stack and queue. So let's start with this session, and let's cover stack and queue in from very scratch, and let's take this topic to the gate level. Okay, let's start from very basics. I'm assuming that you don't know anything, so I will start from introduction to stack, and we will cover introduction to queue. We will see various applications of the queue, and we will cover here many examples I will take while explaining all these concepts. Okay, how the stack is working, how the queue is working, what are the various applications, and then again we will cover the various gate question. We will be able to solve the gate question after covering the all the most important points about the stack and queue. This is my promise to you people, that I will cover all the most important points of the stack and queue here. So this video will be sufficient for you people. If you are even you are just want to learn DSA also, this video is going to help you a lot. Okay, okay, so let's start with the stack. I'm starting from very basics with the definition itself. What is a stack? So stack is just like, okay, like these are arranged in the form of stack. Okay, this is the first plate. I can say okay, I put one more plate, I one more plate, one more plate, one more plate. So I'm putting the plates actually here in the form of a stack, and important point here is that if I want to take one plate out of this stack of plates, then I need to take the top one. I need to take the top one first. I cannot take the below one first, because that will break the other plates. So what I'm doing here is I'm taking the plate from upside, and if I want to put a new plate, then again I'm putting the plate to upside. This is what is going on in the stack. Okay, So stack and queue are actually data structures, in which data structure, we know data structure are used for storing the data, and so that we can efficiently we can access that data. Okay, so that we can efficiently access that data. So every data structure is having its own properties. Some data structure actually makes easy to access the elements, searching of the elements. Some makes it easy to, okay, insertion. Some makes it easy for deletion, like that. So based upon application to application, we can use different data structures. So we are today talking about the stack first, then queue. So here the definition of the stack: a stack is a container of objects that are inserted and removed according to last in first out principle. So you need to know only one thing. Okay, we will keep it very easy. You do not need to take any, see, you don't, please don't make any concept complicated. Okay, by making it complicated, that doesn't mean that you know everything. Okay, if you, if you can understand a concept in easy way, that is the best thing you can do. Okay, because that is going to help you in actual exam, whatever is the exam, wherever you are using these concepts. So that should be very easy in your mind. Okay, keep it easy. So stack means one thing should come in your mind, that is simple, last in first out, that's it. So this is a data structure which is performing in this way. That's it. So the elements I'm inserting in the last, the elements I'm inserting in the last, that should be out first. That's it. The plate which I'm inserting at the end on this stack of plates, so that plate will go out first. Okay. So that's it. Last in, first out. This is the principle on which stack works. Okay, and this is a diagram you can see here. So this is a stack, and we can push the element on the top, and we can pop the element from the top. Okay, so these are the special name given for insertion and deletion. This is for insert. So if we are inserting element in stack, actually we call that, okay, we are pushing element in stack, we are performing push operation. And when we are deleting the element from stack, we are performing pop operation. Okay, we are deleting element, we are performing pop operation. From where we can perform this operation? Only at one place, and what that place name is? Top. From the top only we can delete and insert the element. We can push and pop the elements. Okay, from the top of stack, I cannot delete this element or this element. Any element I cannot delete until unless this element is not deleted. Top element is not deleted, or uh, I need to access, I can access only top element in stack. Okay, this is how actually this data structure works. And in various applications we can use it, and we will see there are many applications of stack. There are many applications of stack. So first one is like browser history, like you are accessing the various web pages, and there remain a browser history which web pages you are accessing. So the latest one will be at the top, latest web pages, and will be at the top. And editors also used, okay, what is the last edition you editing you have done in your file, like that. Recursion actually is using the stack at the back end. Okay, in recursion is a very nice concept actually. In this concept, the CPU use the stack. The CPU use the stack. Programmer don't use the stack. CPU use the stack. Whenever we recursively call a function, then programmer do not use the stack over there, but CPU use the stack there. Okay, to maintain, okay, which function was called at what time. Okay. Next one is infix to postfix conversion, which is very important from both company point of view and from gate point of view. Postfix evaluation, this is also important. We will cover these two in detail. In more detail, we will cover these two. Matching parentheses, tree and graph, traversals we use, like in BFS, DFS, we use stack and queue. And can you people tell me, okay, which this is one in this is just one easy interview question, I will say. Which data structure we use in DFS? Can you tell me which data structure we use in DFS? Can you write in the chat box? I will keep covering the interview based questions also, meanwhile I'm covering this. So whatever I will find out related, maybe we are focused on gate, but I will try to whatever I will find out here that is from company point of view, I will share that also. Okay, So yes, we use stack in DFS, and in BFS, which data structure is used for BFS. So these are two algorithms for traversing of a graph. Actually, we want to traverse the graph. So here Mukesh already said that okay, we use the stack data structure, and in BFS Mukesh says that we use the queue data structure. Yes. Okay, so in traversal, graph traversal, we use the stack. So these are the various applications, and this one we will cover in more detail. Okay. Okay, so actually, there are two main operations in any data structure. One is insertion, that is push operation in stack. Another one is deletion, and that is pop operation in stack. Okay, so these are the most two important two operations. How to push the element, how to delete the element, how to push the element, how to pop the element from the stack. Okay, this is one structure I have shown you there, and I'm assuming that okay, top is actually just nothing. Top is a pointer actually that is pointing to the top top element actually, which is the top element in the stack. Okay, which is the top element in the stack. Like here you can see 2 is the top element in the stack. So top is pointing this 2. That's it. Okay. So that because we want to, if I want to delete some element, I need to delete from the top only. I want to insert it, then I will increment the top and I will insert. Okay, so I have the position. Actually, I can store the position of the top element in this variable. Okay, I can store the position. Okay, and one more thing, initially the position of top will be -1, and I'm assuming that we are implementing here the stack using array. We are implementing the stack using array. So I'm assuming that the array indexing is starting from 0. Array indexing is starting from 0. In exam they can ask you that okay, they can specify that array indexing starting from 1. Okay, they can ask you like that. Okay, but here I'm assuming that is starting from 0, because uh, in most of the compiler actually start the array indexing from 0 only. Okay, so we are implementing actually stack with the help of array. Okay, see, stack, one other important interview question that comes in my mind is, stack is a data structure, I told you. Okay, array is also a data structure. Okay, array is also a data structure. We can implement any data structure with any other data structure. Simple. I say one line. We can implement one data structure with any other data structure. That's it. Even, let me add one more thing. Let me add one more thing in this. We can implement even stack with stack also. We can implement stack with array. We can implement stack with queue. We can implement stack with linked list. We can implement stack with, I don't know, with uh, whatever the data structure we have, or even we can implement stack with stack also. Okay, so implementing means just I want to ensure that if I'm behaving like this, last in first out, that is a stack. That data structure now behaving like a stack. That's it. I can make my data structure to behave like this. I can make any data structure to behave like this. See, that can sometimes, this can happen that okay, if I'm using, maybe I'm using I'm using linked list. In that case, I don't know, that can be expensive. Performing this operation can be expensive. Okay, and using array, that can take less complexity, that can take less time. Okay, but we can implement, important point is that we can implement any data structure with any other data structure. We can implement stack with stack also, queue with queue also, even that is also. Okay, implementing the data structure means simply how that is behaving. We are just making other data structure to behave like that. Okay. Okay, so now we are implementing, I just tell you one or two things here. We are implementing stack with array. Okay, we can implement any data structure with any other data structure. And this is one format of the stack. We know that we can delete and insert the element on the from the top only. Okay, and top actually here is pointing to the is storing the index of the top element, actually that is 3 in this case. But initially when our stack will be empty, then top value will be -1. I'm assuming this thing, top value will be -1. When I want to insert the element, then I will increment the top, then I will insert the element. Okay, okay. And when I want to delete the element, I will delete the element and decrement the top. That's it. This is how actually stack will work. That's it. Okay, and this is the code part of that performing push operation, and I will show you the pop operation also. So let's look at the push operation first. In push operation, uh, whenever push means you are inserting the element. Okay, when you want to insert the element, there is a possibility of overflow. Overflow means your stack is full, maybe like that. Here also, let me erase again and let me show you. Maybe your top is here and I store one more element, I don't know, 3 here. So now your stack is full. Top is pointing to the last element in this array actually, which is behaving like a stack. Okay, so top is pointing to the last element here. Okay, so in this case I can say that if somebody asks me to insert one more element after that, after this position, somebody asks me, please insert one more element, I will say, please go to hell. What I will say? Please go to hell. My stack is already full. I'm already overflowing. So this is already overflowing. So I cannot insert the element. Okay. So if my stack is full, I will show the overflow. Otherwise, whatever value they will provide me to store, I will store that value inside the stack. Okay, and here n is the number of elements. uh, I have to say, okay, size of stack, or you can say size of array. Okay, we are making array to behave like a stack, means we are saying, array, will you please behave like LIFO, will you please behave like this. So if you can behave like this, you will become a stack. It's like that only. Okay, and here we are passing two values. One is val, which we want to insert now, which we want to push, and this is the size of the stack or size of the array. Okay, so now your job is to tell me these two conditions. First condition, you need to tell me at third position, third line, what condition will come here to overflow occur. What should be the condition? Think over it. In what condition the stack will overflow, the stack will be full? Can you tell me what will be the value of the top? Top is telling me the position, okay, of the top element. So one thing is sure, if top will be at the last element here, last element in the array, then I can say that stack is full, stack is overflow. Okay, so can you write a condition here? Can you write a condition at third line so that I can print the overflow? Can you write the condition in chat box? Can you please try it? It's okay, you just need to try it. Wrong or right will not matter in complete session. I'm asking you to your question because that will actually that from that way you will learn more. Okay, there will be more learning if you will try from your side. So okay, welcome back, Ravish. And you are saying top is greater than equal to n. So let's suppose n is, let me tell you, n is, in this case n is 5. Number of elements are 5. 0 to 4, number of elements are 5. And you are saying that if top is greater than equal to 5, then there will be overflow. Ravish is saying this, and Mukesh is saying that, okay, if top is let me erase it and write it properly from this area, and let me use the pen again, and this is another answer is like this: top is equal to 5 or n. So if top equal to 5, then I can say that, okay, stack is full. So Mukesh is saying this, Divyanshu is also saying this, Roshni is saying that if top is equal to n minus 1, means 5 minus 1, top is if equal to 5 minus 1, that is 4, then the stack is full. In this case, if we relate, so I hope so we have three options here. One is this, and one is this, and one is this. Actually all will work fine, all will work when I have to say this, all will work fine. I think all will work fine, but for that you need to little modify the code, you need to little modify the code, I think. Okay, but if we are starting, if we but we I have already tell you that I'm assuming that top is equal to in the starting top is equal to -1. If you are setting top to -1 in the starting, in that case actually these two conditions will fail, because uh, before inserting the element now I need to increment, before inserting the element now I need to increment the top. Okay, and I can increment the top, I will increment the top in this area, in else part. Okay, and for overflow I'm in if area. Okay, so before even inserting the element, actually in this case the value will not reach to the top, top will not be equal to 5, top will remain to 4 only, 0 to 4, top will remain up to 4 only. Okay, so the right condition will be this one. Roshni shared the right condition, that is the best condition here, but I have shared that n. So maybe we are incrementing first, and then we are inserting the element. So let me check out, this will be n or n minus 1. So this should be n minus 1, this should be n minus 1. Okay, and why is this? Because we are first incrementing. Why this? We are first incrementing. Okay, let me check it. Okay, let me check it at my end also. I need to check it, I think. So I need to check it before saying any statement. So if that will be -1, that will be 0, and we are storing the value at 0th position. Okay, and let's suppose we are at the okay. So if we are here at the last position, okay, and then we want to store the element, and at that time n value will be n minus 1, that will be n minus 1, that should be overflow. Okay, so that should be n minus 1, that should be n minus 1, the value should be n minus 1 here, the value should be n minus 1. So let me recap it, let me repeat the same thing. Okay, so Roshni is right in this case, that will be n minus 1. Mukesh says n minus 1. No, Mukesh, we will not insert at n minus 1. Actually, what we are doing here is, first we are incrementing the value, then we are inserting. Okay, first we are incrementing the value, then we will insert. Okay, so let's suppose a new element come here. Okay, let's discuss about this thing, and okay, let's take this example only given in this stack itself. From here this will be clear very fine. Okay, so our the top value is 3 now, top value is 3, top is equal to 3. Okay, and now I want to insert one element. Let's suppose the value is 10, let's suppose, and the stack size is 5, size is 5. So is top is equal to 5 minus 1? No, top is actually 3 right now, top is not 4, so I will come here, I will increment the top, that will be, so top will be now here, not here, and after incrementing I will store 10, this value in the stack, I will store this value inside the stack. Okay, and now top value is 4, 4. top value is 4. Now again, let's suppose we stored 10 now here. Let's suppose again we come here. Let's discuss this thing. Okay, let's don't cram it. Okay, so let me write 6 value I want to insert now. N is the size of the stack. Okay, so now is top equal to now 5 minus 1, that is 4. Yes, that is top is equal to 4, and that is we cannot insert element here. The stack is full right now. The stack is full right now. Stack is full. Okay, so that should show overflow. We cannot insert this new element now because there is no space inside the stack. So the right condition will be n minus 1 only. The right condition will be n minus 1. Actually, again, this for this scenario that will be n minus 1 only. Okay, for that will be n minus. Otherwise, you can little modify the code maybe, and maybe your array starting. Maybe if you want to set the top equal to 0 only, from 0 you want to start. So in that case that can modified. Okay, otherwise right now, okay, let's keep it easy. Let's keep it easy. So this will be n minus 1. This will be n minus 1. Okay, Mukesh. Any doubt in this, please ask. So this will be n minus 1. So if and no doubt, please tell me about the pop operation. Let's discuss this thing also. Let's discuss this thing. Okay. Now I want to delete the elements. Okay. Important point here is that you please keep replying. So we want to delete the element. We want to pop the element. So if there is no element inside the stack, then I will show that underflow. I will show that there is no element in the stack. I will show the underflow. I will print the underflow. Okay. So you people need to share the underflow condition. What will be the value of top so that we can show that underflow. There is no element inside the stack. So please think over that. So let's move on. So here is a practice question for you people. Please try this question and write the option in the chat box. Please try this. So let me read the question for you people otherwise. Which of the following permutations can be obtained in the output in the same order using a stack assuming that the input sequence is this? Means the question is saying that you are inserting 1, then you're inserting 2, then you're inserting 3, then you're inserting 4, then you're inserting 5 inside the stack. Okay. So what can be the possible permutation or sequence of output? How you can take the element out? What can be the possible output sequence possible while inserting these elements in the stack? What can be the possible output sequence? Yes, this is the question. Let me move on and let's see. B is the right answer. Yes, B is the right answer. And how he's getting B? How Mukesh is getting B? He know that he's having a stack, and he is inserting these element inside the stack like 1 and 2. He's saying B is the option. Let's check out how B can be the option. So he maybe inserted 3. He inserted 3 elements and he wants 3 in the output. So he deleted the 3. Okay, now he have 1 and 2 in the stack. Now after that can insert 4 and 5. So insert 4 inside the stack. Yes, he can insert 4 on the top. And after inserting 4, actually he wants 4 in the output. Yes, he can get 4 in the output by popping this element. This we can pop 4 also because pop 4 is at the top. Okay, and after that he must have inserted 5 inside the top. And again this is on the top actually of the stack. So we can delete this element and insert show to the output. So 5 is also deleted and shown to the output. And then we can delete 2 and 1 also. So 2 and 1 also we can delete. And so this can be one possible sequence of output. Okay, so this is what they are asking, what can be the possible sequence of output here. So B is the right answer. B is the one possible sequence. Other cannot be possible actually. If we want to get 3, yes, we can get 3 after inserting 1, 2, 3. We can get 3. We can get 4 also. We can insert 4 and get 4 also. We can get 5 also. After inserting 5 we can get 5 also, but after this actually I cannot get 1 before 2, because I'm inserting 1 first, then I'm inserting 2, so I cannot get 1 before 2 actually. So here also that's why this fail actually. I cannot get 1 even before I cannot get 1 here in this case. Okay, we can insert 1. In the case of C, we can insert 1, we can delete it. Okay, we can delete it, and after that we can insert, we need to insert 2 now. Okay, so we need to insert 2, 3, 4, and 5, all elements, because I want to get 5 now. So I want to need to insert all the elements. So I will get 5 also, but after that I can get only 4. I can get only 4, but they saying we need to get 2. So this is also fail, this is also fail. And what about this? Here the same thing is happening. I cannot get 1 before 2, because I am inserting 1 first, then I am inserting 2. Okay, so how I can delete 2? Because 2 will always be at the top rather than 1. Okay, okay, so that's why this is also fail. And B is the right answer here. B is the right answer. So we have lots of questions with us. We have lots of questions with us. We will doing practice over that. So this is GATE 2004 question. You people please try it and write the answer in the chat box. Please try it and write the answer in chat box. Everyone please try it and write the answer in chat box. I'm waiting for your reply. So what is the best data structure to check whether an arithmetic expression has balanced parentheses or not? So if you want to find out, okay, balanced parentheses, which data structure out of these will be is the nice one out of these? So we have already seen this even in the applications. So this is, I think we have seen this. Yes, if we want to match the parentheses, if we want to match the parentheses, like parentheses, like if I have one opening bracket, then must have closing bracket also. Okay, if I have one opening bracket, then I have must closing bracket also. If somebody asks that, okay, these braces are balanced or not? Yes, they are balanced. Okay, because for every opening bracket we have closing bracket. Okay, so we can do this with the help of the stack. We can perform this operation with the help of the stack. Maybe we can keep storing the opening one in the stack, and whenever the closing one come, we will keep deleting the opening one. When closing one come, we will keep deleting the opening one, and when we will be left with 0 parentheses in the stack, then we can say that, okay, the parentheses are balanced, they are balanced. So we can use the stack data structure to find out if the parentheses are balanced or not. So B is the right answer here. Otherwise, we are studying the stack, okay, and that should be the answer. We can think. You can as you can look check out this answer directly even. But yes, we use the stack to check. We can use the stack to check the parentheses are balanced or not. Okay, check out this question. This is again GATE 2004 question. So believe me, you have enough information with you now. You have enough information with you. You can solve all these questions. So if you know how the push and pop operations are happening, then see, these are the GATE questions. These are not my questions. So they are asking the question from those areas only, which I have already asked you. What are those 4 conditions like that? So please keep trying till the end of the lecture. You will be very comfortable with the stack. Okay, but important part is that you people please keep trying. So if you want me to explain the question, so they are simply asking that, okay, we are using an array, one array as a 2 stack, as a two stack implementation we are using, means like one stack is growing from the left, one stack is growing from the right side. If I want to store the element in stack 1, I will store from the left side, keep storing the elements from left, then move to the right. And if I want to store element from the stack in stack 2, I will move to the this side, okay, left side. So like this we will keep storing the element. He is asking that, okay, what will be the condition for stack is full in this case? What will be the condition for to find out, okay, when the stack is full? So we are using one array to store data in two stacks. For these two stacks, which is one is growing from the you can say start, one is growing from the back side. So when will be the this array will be full? We can, they're asking like this. So what will be the condition? Like for full of the stack, you already tell me, like if top equal to n minus 1, if we are using one stack, so this will be the overflow condition. But in this case, what will be the overflow condition? So see, it's not like that. See, we are using this array efficiently. Maybe there remains one element in stack 1, and I keep inserting the element in stack 2. So like that, like I inserted Q here, S here, maybe P here, R here. I don't know, maybe B here. So these all elements may belong to stack 2. These all elements may belong to stack 2, and stack 1 have only one element. This can also happen. This is not compulsory that we are dividing here the stack in half elements I'm using for stack 1 and half element we are using for stack 2. Then this will not be efficient use of this array actually if I'm dividing it, because maybe I don't want more element in stack 1, but I want to store more element in stack 2. So I'm not dividing in half. So Ravish and Divyanshu is saying that D, and that is the right answer actually. So if you can check out here, if top one means top one is pointing to the stack one top, and top two is pointing to stack two top. So you can see here that top one is equal to top two minus one. So if top one is one less than top two minus one, then that can be the condition. Okay, here you are dividing half element to the to first element, half elements to the you are saying that, okay, out of total size you are saying that, okay, half of the element you are giving to the second one. Okay, maybe you are moving from this side and moving to this location, but this is not the case. It's not compulsory that we are dividing in half and half. Okay, so that's why this is not the right option. And this is also not the right option. This cannot be the right option actually. And because maybe top one is at zeroth position and top two is at one position, so 0 plus 1 is not max. 0 plus 1 is not max, so this is also not the right. And this is also not the right. This again dividing in top one is going to the half and top two is going to the max. So in that case actually every array will be empty, even this part will be empty. Okay, so this is also not right. So D is the right option here. D is the right option. So, okay, yes, let's move to the other question. Yes, D is the right option. So, the meaning, Mukesh is asking what is the meaning of space is to be used efficiently, means we need to use this array efficiently. Means it's not like that. If we are dividing this array in half and half, half for stack 1, half for stack 2, you are not using it efficiently. Efficiently means maybe your stack 1 don't need this n by 2 space, or stack 2 need max all of the space, means complete n space. So in that case that will not be efficient approach if I'm dividing in half and half, because one person, it's like, okay, it's like I have some common resources with me, and I says that, okay, I have two people to share with each other. Rather than dividing the complete property in half and half, It's better. It's like I can ask that these two people, I can ask, okay, rather than dividing it half and half, you will not enjoy it. It's better, uh, whoever need this resource, that can use it. Okay. Okay, maybe right now stack 2 need it more, maybe all the space, then you can use it. Later on, maybe now stack 2 don't need, then stack 1 can use it. So that is the efficient, means we need to use it efficiently. Okay, so it's like there are two brothers, if they dividing the property. So this is like if you are dividing in half and half, then they may not actually like enjoy that much as if they have the one complete big property with them. Now they both are owner of the same this much big property, so that is a more efficient use. Okay, so this is the right answer here. So let's move on. And okay, let's talk about now one application of stack. We can use the stack to convert infix expression into postfix expression. Okay, in infix, let me give you an example of infix. Like a, if I'm writing a plus b, this is the example of infix. If I'm writing a plus a b and plus, this is the example of postfix. Means here the operator is coming later and operand is coming earlier. Okay, so postfix means operand is coming late, operator is coming later. Okay, here infix, operator is coming in the middle, and if you are talking about prefix, then operator is coming before a and b. Okay, that is prefix, and this is infix, coming in between the operand. These are operands and this is operator. Plus is operator, a and b are operand. So here operand are coming earlier and operator is coming post. Okay, here operator is coming in the infix, here operator is coming prior, prefix. Okay, so we want to convert infix expression into postfix expression. First of all, why we want to convert infix into postfix is, actually, let me tell you, our computer find it easy to solve postfix expression. Okay, computer find it easy to solve the postfix expression, although humans like to read in the form of infix. If somebody say you, okay, what is a plus b into c divided by d, so this is much better for you to read, this is much easier for you, rather than if somebody is saying like this. If somebody is writing like this is difficult for you, although this thing is better for the computer, and this thing is better for the human. So we are using both of them. We are saying that, okay, human can write like this. Now we will convert it into this format in the form of postfix, and then we can solve this expression after converting in the form of, after converting the infix in the form of postfix. Okay, so it's easy means I'm saying it's easy to solve. What do you mean by that? Easy to solve, easy means this will take less time. Solving the postfix expression take less time as compared to infix. Solving the postfix expression, same expression, if I'm writing a plus b or if I'm writing a b plus, so this will take less time as compared to this in computer. Okay, if somebody asks you again how much less time that will take, then you can say that, sir, postfix expression, it's like that. Okay, for n input you can say that, okay, this will take order of n time. Means if you have n symbols a b 3, here n values 3. Okay, so if you have n elements, so this will take n time, and this will take actually order of n square time. This will take order of n square time. Okay, so if somebody, if it's like that. Okay, why that is taking n square time, you can see it directly here also. So maybe one expression is written like this. So computer actually, if that is solving the infix, then your algorithm will behave like this, that need to go through from start, then need to go through till the end. Now that will be able to find out, okay, which operator is having the highest precedence. We solve the operator that is having the higher precedence first. So here this is the power operator, we need to solve this first. After solving this, again we need to start from the starting, and we need to find out, okay, now which expression I need to solve the next. Okay, and after again, so this procedure actually take asymptotically n square time. Okay, but in postfix case, if something is written in postfix like this form, maybe, I don't know. So here you can just, computer will move one way, and that will keep solving the expressions, that will not go back and keep solving the expression actually. Okay, so that will not come back like this and again check out which is the next higher precedence operator. Okay, in the case of postfix, that do not need to find out the which is having the highest precedence, that can directly solve it. We will solve that. Right now I just tell you one important point, and this is again the interview question. Why we are converting in postfix itself, why we are not using infix, because this take less time in computer solving postfix rather than infix. How much this take n time, this infix take n square time. Okay, okay, now this is one of the application of stack. We can use this data structure to convert infix expression into postfix. We can use this data structure. Okay, so let's solve this problem. Okay, let's apply this. So I'm taking just any random infix expression, I don't know. So I'm taking, let's suppose I don't let me take in the form of digit, so that will become easy for us. Okay, maybe I'm taking a plus b, maybe I'm multiplying, okay, right now. Okay, c, and after that, so maybe divide. Okay, then d. Okay, and then I don't know, minus, and maybe we are using bracket also. Bracket is also there, and I'm writing, okay, e plus f. Okay, bracket close. That's it. Okay, so this is the expression we have. Now let's convert this expression in the form of postfix. So I'm applying the algorithm now. I'm not telling you the steps, I'm just applying that. Okay, I'm applying the algorithm, and I will show you the algorithm later on. Whatever steps I'm applying here, that are not my step, I just want to tell these steps are these are the steps of the algorithm which we use to convert infix into postfix. I will say, okay, so see how this algorithm works. So we are using a stack. One thing is confirmed. We are using this data structure to convert this infix expression into postfix. Okay, so what we need to do is, say, simple. Start reading from here. Okay, start reading from here. So whenever you get the operand, these alphabets are operand, and plus, multiply, these are operators. Plus, multiply, divide, these are operators. Okay, so whenever you find the operand, simply print that on the screen. So that is the part of postfix. So I'm putting that in, I'm saying that this is now part of postfix. Okay, so I get a first, I put in the output, and then I get plus. So when I get operator, I will put it into the stack. So this is how this will work. That's it. Okay, let me move on. So I get a, I put in output, I get operator, I put in stack. Keep moving on. I get now b is an operand, so I will put in the output. Output means postfix. Now this is the postfix expression I'm getting. Okay, and then I get operator. See, now I get multiply. Now we get multiply. So see, multiply we can insert into the stack. Okay, so there is a rule actually in the algorithm. What is the rule? uh, we know that in C compiler, plus have lower precedence, and star has high precedence. Okay, we know this precedence table. So plus have low precedence, and star have high precedence. Okay, so if some high precedence operator come, then that can sit over the low precedent operator. It's like that. Okay, this is just like okay, this is a slim person, okay, standing here, and then a fat person come and sit over that. Okay, so he cannot deny because he is very powerful. He can sit over this person. Okay, so this powerful operator, high precedence operator can sit on the low precedence operator. Okay, that is sure because he cannot deny. Okay, okay, now let's move on. So we get the operand. So operand will go here in the output. Okay, then we get the operator. See, we get the operator now. So operator will go into the stack. Okay, now divide and multiply actually is having the same precedence. So in the case of this, in this condition, we will insert inside the stack. Okay, but if both are of same, both we can say that, okay, both have the same weight, both have the same precedence. He multiply and divide have the same precedence actually. Okay, so in the case of that, we will pop the element. We will pop the operator if they are of same weight. In this case, we will push if we have heavy one and we have light one. So heavy one will sit on the light one. In that case, we'll push. If they are equal, then we will pop. First we will pop. Okay, then we can insert. Okay, then we can insert actually. Okay, then we, so okay, let me write it. So then the same, let me erase it and let me write it. So we have pop the star and we are inserting the divide now. Okay, okay, now we are at D operand. Same procedure I'm repeating actually. Same procedure I will keep repeating. D is here. I will put in the output. Okay, and then I get the minus. So that is operand that should go inside the stack. But see here, one more condition. So minus have the less precedence as compared to I don't know you are able to show this or not. So this is our minus and this is our divide, which is have higher precedence. Okay, so see, this person will not allow this. Okay, so this person will not allow this to sit over it because this is having heavy weight and this can deny this person. Okay, this have more power. So this will say that, okay, I will pop first, then you can get insert. So we will remove the divide. Okay, so let me complete this, then I will check out. Let me complete this. Okay, so we are at divide minus. Now we have covered all the conditions actually. So we know now the condition of algorithm. One is this, one is this, one is this. So now we have popped the divide. We have popped the divide. Popped the divide. Let me pop it, and we get the minus. So we know in the case of minus and plus have the same precedence. Minus and plus have the same precedence. If we have same precedence, again we pop. We know that if we have same weight, then again we pop. So we also pop the plus. Okay, and after that we can actually insert the minus. Actually, we can insert the minus. Okay, and after that what we get is we get the this opening bracket. We will insert the opening bracket. Opening bracket we can directly insert. Okay, opening bracket we can directly insert, and after that we get E, that is operand. We get operand, we will insert in the output, and after that we get plus. Plus is an operator. See, we can insert plus because opening bracket is here. See, after opening bracket, it's like a new start. It's like a new start. So we can insert plus, and after that f is come, we can insert f in the output, and after that closing bracket come. So whenever the closing bracket will come, we will keep pop all the elements. This is another condition. We will keep pop all the elements until unless we don't get the opening bracket. So until only opening bracket, I will pop all the operator here. Plus I have only plus here, so I remove plus also, and after that I take off the minus also. That's it. So this is how we convert the infix expression into postfix expression. Let me repeat this thing now. Okay, let me repeat this thing. So 2-3 points we are doing here. One is, First point is, if the operand is coming, we are putting it in the output. One thing is clear. If the high precedence operator is coming, if the high precedence operator will come, we will push that operator on the low precedence. Okay. If the same precedence is coming, we will pop in the case of same precedence, as well as in the case of, if low precedence is coming and high precedence is in the stacks, high precedence operator is in the stack, again we will pop. Okay. And one last thing we are doing is, we are inserting the opening bracket, and when we find out the closing bracket, whatever the operators comes in between, we will pop all of them. So this is what we are doing. That's it. This is what we are doing in while converting infix into postfix. Okay. So what we can do is, you people can try this. If you want to try one example from your side, you can write yes. If you want to proceed further, if you think that okay, no, we don't need to try an example, then please write no, or simply write proceed. If you want that, okay, you want to try one example, so I will give you one example, one easy one, so that we can try one more example. If you want, then write yes. If you want one more example from me also, write yes. If you don't want, write no. I will move according to you people, or if you have any doubt in this, you can ask. Okay, if you have any doubt in this, you can ask. So otherwise, this is the same algorithm to convert infix into postfix. What we have done, this is the algorithm. So okay, Divyanshu says no. So if you have an opening bracket, so let's check out, Divyanshu, let's check out this thing. If we have opening bracket, we will push it inside the stack. Yes, when we were finding the opening bracket, we were pushing inside the stack. If we have an operand like a, b and all, then we will append it in our postfix expression. Means we will output the operand. We are putting the operand in the output of postfix. Yes, we know this thing. And if we have the closing bracket, if we find out the closing bracket, then we will keep popping out the elements from the top of the stack and append them to the postfix expression until we encounter the opening parenthesis. So until, if we find out the closing bracket, then we will pop all the operator. I don't know what are the operators inside the stack at that time. So if I encounter the closing bracket, then I will pop all the operators until I find out the opening bracket. This is what this statement is saying, and we have done this also. And what other operations we were doing? If we encounter an operator, in case of operator, what we were doing, if we have high precedence operator, then we simply push it on the stack. If we find higher precedence operator, we the heavy person can sit on the lightweight person. Okay, it's like that. Okay, and but if you find out the lower precedence operator or equal precedence operator, then what you will do? You will pop. You will where it written? We will pop. We will keep popping. Okay, we will, if we find equal precedence and the lower precedence operator, if the operator is lower precedence, then one on the stop, then we will pop the element. Okay, so and when the last token of infix expression has scanned, then we pop the remaining. If all the infix expression has been scanned, then whatever will be the remaining, okay, whatever will be remaining elements, we will pop that also. Like in previous example, minus was remaining there, we pop that also. That's it. This is what we have done. These were the same thing we have done in that example. Okay. So that's it. And how much time this will take? This will, can you people tell me how much time this will take? Can you write in the chat box how much time this will take? This algorithm, anyone? So if you know, you can write, otherwise let me tell you. So here, see, we are simply, see, we are moving from one step to another. That's it. You're starting from here. You find operand, put in the output. If find the operator, we put in the stack. Keep moving, keep going, processing every time each symbol. We don't go back. We don't go back and process again like that. Okay, so we pick one element from the input and process it. We pick another element from the input and process it. Okay, so how much time this will take? So let's suppose total n characters are here. N is our input size. So we are processing one character one time. So n time, this will take order of n time. Okay, this will take order of n time to convert. So you can try this question now. You can try this GATE 1997 question. We are using operator stack. We are storing the operators. We were storing the operators in the stack. Okay, so we are using the operator stack. We are not storing the operand, and we are not storing and both of them. So we were storing, A is the right answer. So one is right. We were using the operator stack. Okay, so this we have already seen this algorithm. And let's move to the postfix expression now. How to evaluate the postfix? Before moving the postfix, if you don't understand even this thing, let me tell you a shortcut first. How you can convert. Let me write the same thing here. So I think this is the same thing I have written here, E plus F. So you what you can do is, if you directly want to convert this infix into postfix. Okay, let me make some space also. Oh, okay. So I want to convert this now in postfix. So first, which operation you will perform? We know that we will first solve the opening bracket. We know how to solve this expression in this expression. First we'll solve this, and after that, you know that after solving the opening bracket first, and then you will solve the high precedence operator. Star and divide, multiply and divide the high precedence, but they are same. Star and multiply and divide have the same precedence. Then you will check out the associativity, and multiply and divide have the left to right associative. These are left to right associative. So I will solve multiply first at the second place, and after that, whatever I will get from here, I will divide it with D, and after that I get with left with plus and minus. So plus and minus is having the same precedence, but associative, they are also left to right associative. So whatever will come to the left hand side, I will solve that first. So I will solve this plus first. See, one operand you will get after solving this expression, third whatever I have written here, and one is here. Then you will add both of them, and one you get from here, this side, one is here. Now you will minus this one from this one. So after this, you will perform this expression. That's it. This is how you are solving it. Okay. So what you need to do to convert it? Simple. Just write them in the form of postfix, means write the operator at the back, at the right hand side. So E operand will remain at the same position, E and F. Operator will come at the post of these two. Okay, so I solve this first, and after at second position we solve B, C, and multiply. Third position we solve the divide. So see, D will remain here, divide will come here. Okay, after that fourth one, so A will not change its position, plus will come at the end. Okay, and after that fifth one, so minus will come at this. after this and this actually. So this is the postfix. So if direct question come to convert, do not need to use this procedure. This procedure is required because they are asking question from the stack. What are the operators left in the stack like this? They are asking question. So this is the algorithm how that is working. Otherwise, if you need to directly convert, you can directly convert like this. If you want anything from my side, like any other example, you can ask me. Otherwise, I'm moving on. You are free to write anything on the chat box. If you want to repeat anything, please write that. And if you want one more example, I can write there. Otherwise, let's move to the postfix evaluation. So how do actually computer evaluate the postfix? Now if we are converting infix into postfix, we are providing that to the computer. Now after converting infix to the postfix, now how your computer actually evaluate the postfix expression, again that is using the stack data structure. So how that is evaluating using stack data structure, I will tell you that. Maybe we can take the same expression. I have not run that. A B C multiply D divide plus E F plus minus. Okay, so let's convert this now. The same expression I'm writing here. So the expression is A B C multiply D divide plus E F plus minus. Okay, so this is the postfix expression we have. We need to actually evaluate it. Evaluate means we need to find out its value. Okay, we are evaluating the value, so it's better to take these some integers. Okay, because we are performing evaluation. Okay, so we are not converting it into the infix. So it's better to take some integer in place of these alphabets. So let me write. Maybe we can write small one so that we can do easily. 2 1 maybe 3 multiply. So I'm just taking some uh, numbers here in place of these characters actually. So maybe I don't know, 2 divide by plus 3 2 plus minus, I don't know what will be the answer. So let's try it. So how computer solve it now? Let's see this using the stack. So here is our stack. So what's the algorithm? I'm sharing the algorithm now. So how this algorithm work is, computer start from here, algorithm start from here. If that find out the operand, that will be operand now will be inserted in the stack. In the case of postfix evaluation, operand will be inserted in stack. In case of infix to postfix conversion, operator will be inserted in the stack. Okay, so operand come, so I insert in stack, and again operand come, I insert in stack, again operand come, I insert in stack. Then operator come. If operator come, then what we will do, we will pop two elements and we will perform this operation. Okay, so I multiply 1 and 3, and whatever will come, so 1 into 3 is 3, I will again insert that on the stack. That's it, on the top of the stack. So top is at this position now, because we have already deleted 3 and 1. Now which element come next? 2. So 2 is a operand, so insert in the stack. Now divide comes, so I will pop two elements. So here now this will be 3 divided by 2 actually. So it's better to write 1 here. Okay, because that will come in points. Okay, so let me write 1 here so that this become easy for us. So 3 divided by 1 now. 3 divided by 1 is 3. So I deleted these two elements and make 3 divided by 1, and I get 3. Okay. Okay, after that we get plus. We are moving just to the right hand side, and if operand is coming, inserting in stack. If operator is coming, picking two elements and performing the operation. That's it. So plus is coming now. pick two elements from the stack, one is 3, one is 2, add them and store back the result. So 3 plus 2 is 5, I've stored back the result. And after that 3 comes, store in the top of the stack, 2 comes, 2 will come on the top of the stack, then plus come, I will again add these two elements, pop these two elements, 3 plus 2 is 5, and we add it and store in the stack, and after that we perform minus. So take two elements and minus and we get 0. So output of, so if we evaluate this expression, then we will get the 0 as output. We will get the 0 as the output. So this is how the computer is now evaluating. You can see here that start from here and keep moving character by character. This, that will keep moving like this. So this algorithm will take how much time? Order of n time. Postfix evaluation like how much time? Order of n time. Okay, so that do not need to check any precedence and associativity, nothing. Okay, so just storing the operand in stack and picking the elements, picking the operators. If operator is coming, deleting two elements from stack and performing that operation. That's it. That's it. Okay, any doubt you can ask, otherwise let me do it in one direct way also, without using this stack, how you can perform this operation. Let's see how you can evaluate. So this is the postfix expression we have. So it's like, okay, first you get this. Whenever you will get the first operator, you will perform that operator actually. So you will multiply 3 into 1, that is 3. Okay, and keep moving on. Now you get, actually you can mention like, okay, first you will perform this, then you get this, and you will perform divide on these two values, and after that you get plus. So you will add 2 and 2 here. I think we were adding, so we multiply 3 into 1, and then we divide 3 by 1, yes, and after that after that we add. So whatever value will come here, this is not 2, whatever value will come here, so we will perform at second position, and whatever value will come here, we will perform at third position. That's it. So don't confuse, I mean to say, 1 2 3 here, these are not value, this is the sequence in which you will performing this operation. Okay, after that you get one operand from here, and this is another operand, this is another operand, this is operator. So we'll perform operation here at fourth position, and after that you will perform this. That's it. So first you perform this, 3 into 1 is 3, and here you get 3, and after this here you get 3. After this you are you're performing 3 divided by 1. Okay, so again you will get 3. Let me write here itself, maybe here. So here you get 3, and at the second time we remove this, and 3 divided by 1 is 3, and now you get 3 here, and you have 2, you will add both of them. So third step you will get 5, and here you will get 3 plus 2 is 5, and after that 5 minus 5 is 0. So directly I want to just say that directly you can perform like this, otherwise with stack you can perform like this. Okay, and let me take one more, that will not take too much time. So maybe we can show it with this alphabetically, what I was doing here, because these were maybe little confusing due to this numbering 1 2 3, which was matching to our operand. Okay, so here now the number will not match with our operand, so that will be easy for us to understand. Simple. So whenever we are moving from left to right, whenever we find a operator, we pick two operand and perform that operation. First we will perform this, and again moving to the right, we'll find out divide. So one operand we will get from here, and another one is D. So we perform this at second position. After that we will perform, we get operator, we perform this operation, then we will perform this operation, and then we will perform this operation. So this is just the sequence in which I will perform the operations 1 2 3 4 5, and after that we perform the operations. That's it. So directly you can evaluate like this if you want to directly evaluate in fast way. But if the question they are using the stack, then with stack we perform like this way. Computer is performing in this way. Okay, computer is using the stack to evaluate the expression. Okay, okay, any doubt you can ask me, please write in the chat box if you have any doubt. Otherwise, let's solve some gate questions now. So you people please try this question, gate 2015 question now. You have enough information with you to solve now gate questions. So please try this one now. So here you can see, do not even need to use the stack. You can directly evaluate, like you can move from left to right and you can evaluate. Okay, see here we are moving from left to right. Okay, because postfix evaluation we're moving from left to right. So you people are right. C is the right answer, Varun. So maybe perform it like this also directly. You can perform like first you perform this operation. Let me write the number here so that I can identify, okay, first I need to perform this. Another operator I find divide. So I need two operand for that. I get two operand to the left hand side. I will perform this. Then I find multiply. So one operand I will get from 1 and one from 2, and I will evaluate this at that. I will evaluate this. So another one I will find the minus. So I will perform this now. So first one is 10 plus 5, that is you will get 15. The second one is 60 divided by 6, that is you will get 10. Third one is multiply, so you will get 150. After performing third one, multiply, and after the fourth one, 150 minus 8, that is 142. Try this question. GATE 2007 question. The following postfix expression with single digits. So they are saying that okay, these are all are single digits now. Okay, single digit operand, single digit operands evaluated using a stack. Now note that this is a exponential operator, and top two element of the stack after the star operation. What after the star operation? What will be the top two element? This we need to find out. So with stack we are performing evaluating this. So we know how to evaluate this. If operand come, we store in the stack. If operand come, we store in the stack. If operator come, then we pop two elements and we make it to the power. So this will be 2 power 3. So we will store 8 here. Then after that divide come, we pop two elements, and 8 divided by 8 is 1. So we store 1 at the top of the stack. And after that we get 2, then 3, and then we get multiply. So pop two element, and whatever comes we store at that or the top of the stack. That's it. You can stop here itself. We perform our first multiply operation here. So after performing multiply operation, now what is the, they are asking what is the two element on the top of the stack. They are 6 and 1. They are 6 and 1, and A is the right answer. A is the right answer. Yes. So you can try another one. Okay, so now let's discuss about the queue. So that's it about the stack now. So let's move to the queue part. So again, starting from very basics, what is queue? This is the definition. Queue is a linear data structure, means the elements are storing one after the another, not like a tree, which is non-linear. And so this is a linear data structure, and we can store the element in on the basis of first in first out principle. This is important. That's it. This should come in our mind whenever we are talking about the queue. First in first out should come in our mind. Okay, this is important. Okay, so and another point here is that, so in queue we can we insert from the rear, we insert element from the rear, and we delete the element from the front. Okay,
we delete element from the front and insert element from the rear. And insert operation is given a special name here in queue, that is NQ operation, and delete operation is given a special name, that is DQ operation. So this is just like any queue, every queue is behaved in this way only. If the people are standing in a queue, who is standing in the front, that will be processed first, that will be deleted first. And if the new person is coming, that will stand behind the line. Okay, that will not allowed to stand in middle, in the middle, or in the front, actually anywhere. That can only stand at the rear. So insertion is NQ operation is done at the rear, and deletion operation DQ is done at the front in the queue. Okay, so now we know this thing. I'm not going to implement the simple queue. So rather than, let's implement the queue with circular array. Actually, we will use the circular array. Means we are having the array only actually, but we are thinking that in our array, if our array finished, then we can insert again starting from 0th position. Okay, so we are using a circular array to implement the queue. Okay, so let's implement the queue using circular array. We can implement with simple array also, but in that case, even though there will be a space in queue, we will not able to insert in that case. Okay, so there is a drawbacks in simple array, so that's why we are using the circular array. And what is the drawback? Let's suppose I have this array, and I was inserting the elements in this now, like 2 4 5. Now the rear is here at 5. Okay, and front is at here, the rear is here, and again I insert, let's suppose one more element, 6. So now rear is here. Okay, so if I want to delete like 2 4, I delete 2 element, now front is here. So now I want to insert one more element. Okay, but I cannot insert one more element even though these two spaces are empty. I have deleted these two elements, so these two spaces are empty, but I cannot insert. But if I'm using the circular array, then we can use, come back here and insert the elements here. So now we are implementing the queue using circular array. Okay, we are implementing the queue using circular array. So this will help us to overcome this drawback, wastage of space. So that is, let me show you. So some important condition. One is, you can tell it yourself also, what will be the underflow condition when the, if we are using the circular array. So what will be the underflow condition when you can say that, okay, the array don't have any element. So if we can set again the front and rear to -1. Initially we can set front and rear to -1. So front is pointing to the index of front element, and rear is pointing to the last element. So if initially we can set to -1, so means there is no element in the queue. So if this value is -1, front and rear, that means is underflow. So it's like this. In the diagram you can see. So if we want to insert the element, let's suppose I want to insert any element. Can you tell me, okay, let's suppose I want to insert 10. If I insert 10 in this queue, and queue means we are inserting. So can you tell me what will be the position of front and rear? Actually, if you will answer these questions, some of the questions I will ask you here, this is the algorithm only I'm talking about. Okay, this is the condition you will be requiring while writing the algorithm. Again, while performing NQ operation, there will be one condition. If you know, after inserting one element here, after this position, can you tell me what will be the position of front and rear? If you can tell me, then writing the algorithm will be easy for you. Can anybody share what will be the, if I want to insert one element, let's suppose 10 here, can you tell me what will be the front and rear position? Right now the front and rear are at -1. They are pointing to -1. They are pointing to -1. There is no element in our queue, and I have inserted one element now. Can you tell me
I inserted and one element. Can you tell me what will be the position of front and rear? Front and rear are actually storing the index of the array, and front always points to the first element, and rear always points to the last element in the queue. So front points to the, listen to my statement, front points to the first element in the queue, rear points to the last element in the queue. So I'm making this statement. I have inserted one element now. What should be the value of front and rear? Front and rear are storing the index. Initially their value is -1. I'm again repeating. So now I'm repeating, front will point to the first element and rear will point to the last element. And actually Mukesh have corrected this. That's great to see. And both will point to 0. Both will now point to 0 actually. Okay. So you can see here, I have inserted one here, one this value. Okay, I inserted one this value here. Now front and rear both are actually, pointing to 0. Front will point to the first element. Actually, I have one element only. That is my front, that is my last element. It's like only we have one student in class. That is first, that is last. Okay, we have more questions. Actually, these questions will help us to design the algorithm to perform the NQ and DQ operations. And again, I will ask you the question there also. And these are the only, they are using these questions only to make the question in exam. So, okay, NQ operation I want to perform. Let's suppose I want to insert some other element. I don't know. Let's suppose another element I want to insert. NQ means inserting the element. So what will be the position of front and rear now? Can you tell me? So after inserting one more NQ operation, after this, if I'm performing one more NQ operation, let's suppose I am inserting one more other element in this, what will be the position of front and rear? Please keep sharing that. Whatever you know, keep sharing. Okay. Right or wrong will not matter. Important part is you people are sharing. So front is 0 and the rear is 1. Yes, Mukesh, front is 0, rear is 1. Now rear move on. So this is our rear, this is our front. Okay, front is pointing to the first element, starting element, and rear is pointing to the last element. Okay, we know this thing. If we perform some more operations we perform. Okay, and rear we inserted. Okay, 3, 4, and 5 also. We NQ 3, 4, and 5. Now rear is here, front is here. Okay. Okay, now again the question is for you people. Can you people tell me again? I'm asking question after this condition. Now rear is here and front is here. We deleted two elements. So first of all, we do not need to tell which element, because you know if I'm asking to delete one element, from where you will delete. Okay, so I'm saying please delete two elements. You cannot ask me which element. Okay, so we will delete two elements. So you can use F and R rather than writing complete statement. We want to delete two elements from this queue. What will be the value of front and rear? So Mukesh says that front will be 2, and let's check out. Yes, front is at the second position and rear is at the fourth position. Yes, that is right. You are right, Mukesh. Okay. So again, if we want to insert one element, let's suppose after 5 we want to insert 6 now. If we want to insert 6 now, what will be the value of front and rear? Actually, what I'm trying to do is I'm trying to cover all the important conditions which can occur while performing NQ and DQ operations on the queue. So we are doing that with the help of this diagram, so that become easy for us to understand from coding point of view. So I want to insert one more element. We are using circular array here. We are using circular array to implement the queue. And I want to insert this element now, 6, inside the queue. The queue looks like this now. Any other answer? Any other answer than overflow? So overflow is a wrong answer. Overflow is wrong answer here. We are using the circular array. Anybody can tell me? So Ravi says that front will be 2 and rear will be 0. Let's check out. Yes, Ravish is right. So we can insert, see these two positions are empty now, and we are using the circular array. So after this, rear can insert at 0th position. Okay, so rear will be here, front will be here. Okay, okay, that's great. That's great. So rear is here, front is here. Let's move to some more possible conditions. Now I want to delete the elements. So I know I will delete from the front. From the front, I will delete from here now. Okay, front is here at the second position. So okay, that have inserted the element actually. Okay, so we have performed, let's suppose, NQ operation. NQ, this is not we have done here. We have performed NQ7. So we inserted 7 now. Now rear is here, front is here. Okay, so rear is here, front is here. Now our queue is full. Now our queue is full. We know that this thing. There is no more space from 0 to max element 0 to 4. Our array size is actually 5 here. Number of elements we can store is 5. Indexing is from 0 to 4. Rear is here, front is here. The queue is full. Can you people tell me the condition for overflow? What should be the condition for overflow? Can you tell me what should be the condition for overflow? Can you relate somehow front and rear? Can you relate this rear and front, and can you tell me what should be the condition for front and rear? Can you relate them somehow and tell me, okay, what will be the position of them so that queue should be full, and that condition should always be true in any case. So this is the last question I'm asking to you in the queue. After that, we are using all these concepts only to work on the queue algorithm. Okay, how queue is working. Anyone can tell me what should be the relation between rear and front to so that overflow occur, so that we can say that the queue is full? What should be the relation between rear and front? What condition I can write? Can I don't know, can you tell that? So can I write like this? Like front is here and rear is here. I can write that, okay, front, when front equal to rear plus 1, when front is equal to rear plus 1, like front is 2 and rear is 1, so 1 plus 1 2. So if front equal to rear plus 1, can I use this condition? Yes or no? Yes or no? Can I use this condition? Can I use this condition to check the overflow? Is this condition working fine or not? Rear equal to front equal to rear plus 1. If this condition is occurring, then I can say that, okay, queue is full. Front and rear are actually storing the index values. They are storing the index value. Okay, so let me tell you. So we can actually write it, but with little modifications, little more things we need to add. Why? See, this condition will satisfy for here, for in this scenario, this is satisfying. If front is equal to rear plus 1, then this will satisfy. Okay, but what will happen if our front is here? Let me erase again everything. What will happen if, let's suppose, front is here and rear is here? So in this case, I was using front equal to rear plus 1. So rear is now 4 plus 1 and front is actually right now is at 0. So this condition is not true. Then although the queue is full, okay, so this is the exception actually. This is the exception. For this we will do something, otherwise this condition will work. Okay, for this, to make this condition satisfied, we will make little modification in this, and otherwise this condition is working fine. We will use this condition only, but by using little modification, because this condition is not satisfying if our front is here in this, if q is full and front is pointing to the 0th position and rear is pointing here. Okay, in that condition this condition will fail. So for that we will modify it. Okay, otherwise this is working fine. Otherwise this is working fine. Okay, so let me recap whatever we have done, because this is the most important part actually in q. Same thing we will repeat in questions also. You will see in the gate question same thing they are asking, and in algorithm also of q, of nq and dq, this is the only thing they are doing. So you need to know the underflow condition, you need to know the overflow condition. Whenever you want to delete the element and element is not there, you need to check the underflow condition. You know the underflow condition, and if overflow is occurring, then you need to check the overflow condition. If you want to insert the element and there is no more space, you need to check the overflow condition. And you know how front and rear should move when you are inserting the elements, and whenever you are deleting the elements, dq the elements. Okay, okay, so now let's move to the algorithm. Before moving to the algorithm, okay, so I just shared with you the overflow condition, this. Okay, but for circular queue actually, but for circular queue I said you we will modify it little bit, because that was not satisfying this condition when the queue was full like this, and front was here and rear was here. For this condition, what we need to do, how we can check, can you think over it, how we need to check? 0 1 2 3 4 5, how we need to check? N is equal to 6 here. So how you can now compare f and r for this particular condition? When f is at the 0th position, we know that f is at the 0th position and r is at the 5. 5 is nothing, just you can say n minus 1, and f is itself 0 only actually here. N is the total number of elements, so total number of elements is 6, 6 minus 1 is 5. So can you relate f and r now? So I can write, maybe we can write like this. What we can do is, okay, let me write the complete statement now. So what we can do is, we can take the mode, we can take the mode, we can take the, so we know that front is equal to rear plus 1, we know this thing. Okay, we know this thing, front is equal to rear plus 1, but we are adding this thing extra, we are adding this thing extra. What we are doing, what is the maximum size of the array? Maximum size, let's suppose n here. Okay, so we are taking mode of this value with maximum size. Okay, let me take one example. So let's suppose here in this case rear is at 5. So let me write here rear plus 1 mode, in this case n is equal to front. So rear is actually 5 plus 1 mode, and rear n value is 6, total number of elements max is 6, and is that equal to 0? So here you can say that this is 6 mod 6, so the remainder will be 0 in this case. Yes, this condition is true. So if we are taking mode with the max value, with the n value, with the size of the array, size of this queue, then we can consider, we can check out this condition also. Otherwise we are doing the same thing. See, we are checking what we are doing, we are checking front is equal to rear plus 1, same condition we are checking, front equal to rear plus 1, but we just add here, we just take the mode by n, mode by n, that's it. This is what we have done. Why we are taking mode? Because by maximum value, because the After 5 there should be 0. After 5 that should move, r should move to the 0 position. After 5 r should move to the 0 position. If we are taking the mode with the size of this array, then definitely uh, what you will get 0 only. Okay, because after 5 6 will come, and 6 is the size of the array, and 6 mod 6 will be 0. So now actually this rear will approach to the 0th position. Okay, so any doubt you please ask me in this. This is the most important point actually here in queue itself. If you are able to understand this, and believe me, uh, the queue will be almost finished actually. This is the most important point, because we are going to use this statement at many places in the code. If any doubt you can ask, otherwise let me ask you some questions. You can write your doubt in the chat box. Meanwhile, let me share the code of NQ operation. So this is the same thing now. This is the same thing what we have done already. We know this thing. We know this code. Whenever you are inserting the element, if this is the in the initially, if front and rear to -1, you are going to insert the first element. You are inserting the first element. So you know when you insert the first element, you set the front and rear both equal to 0. You do not left the front to -1. Okay, you set the value of both front and rear to 0. Initially front and rear will be -1. Whenever you insert the first element, you will increment both. You will set both, because now there will be one element in the queue, and that element actually will be our front as well as will be our rear. Okay, so we insert the element in the queue. Okay, so at 0th position you inserted the element. So this is the case for first, if you are inserting the first element. Otherwise if you want to insert the element, what you need to do, actually you need to increment the rear. This is what you need to do. Okay, this is what you need to do. You need to increment the rear. Okay, so before inserting the element, actually before inserting the element, you need to check the overflow. We need to check the overflow. Okay, this was hiding this statement. Now the statement is already visible. So this is the condition for overflow. We know what should be the condition for overflow. This condition. So what is the condition? Front is equal to rear plus 1. You can remember with this. But because this is circular array, so we need to come again at 0th position. So we need to take mode with n, so that we can again come back to 0th position. That's why we are taking this mode. Otherwise this condition is working fine. Okay, for simple array this will work fine. For circular array you need to add this mode n. N is the maximum size of the array. So if this condition is occurring, we say that overflow. Otherwise what we are doing, we are incrementing the rear and we are storing the value. We are incrementing this. Here we are incrementing the rear. The condition should be this again. The condition should be this for incrementing the rear. Rear equal to rear plus 1. But again I am taking mode, because maybe the condition can happen that the rear is at the last position and front is somewhere here. Now after the last element, now rear should insert at 0th position actually. To get the 0 position, again I need to take the mode with the max. This max is the size of the array. Okay, so rather than writing simple rear equal to rear plus 1, this will work fine. Every time this will work fine. From here to here, if we are moving, from here to here we are moving, here to here we are moving. But to move from here to here, from last position to 0th position, we need to take the mode. And this condition will work for other people also. Like if I have rear at 1 position, then rear 1 plus 1 mode, I suppose 5 will be 2 mode 5 will be 2 only. So from 1 I move to 2. Okay, so this will all give the same thing as 1 plus 1. Okay, this will give the same thing as r plus 1. R plus 1 mod 5 will give same thing as this for all of the other positions. But this will also give the right answer if we are rear is at the end, and you want to now insert at the 0th position, you are checking the 0th position to insert. Okay, if there is no element, if there is an element, if front is there, then there will be overflow, otherwise you can insert the element. So this is the NQ operation we can perform in the Q, and let's check out the DQ. Okay, you people write this statement for the underflow, then only I will discuss this DQ operation. Please write first what should be the underflow condition in DQ. If you are trying, keep trying. Okay, meanwhile let me also share the underflow. We know that underflow, when the underflow will occur, when front and rear is equal to -1. Initially the condition of front and rear was -1. Initially the front and rear were at the -1. That's it. So when front and rear will be at -1, that's it. That is underflow. But one of the student is asking me, sir, let's suppose we have some element in this. Okay, like 5, 6, 7, 8. Okay, and my front was here and rear was here, so I inserted the element. After that I deleted the element, so front is keep moving, I delete this also. Now all the element deleted, I have deleted all the elements. So now my front and rear are not at -1. So although the stack, this queue is empty, so what will happen in this case? So in this case, actually, if you are, whenever you will delete the last element, you will again set the front and rear to -1. When you will delete the last element, then you will set the front and rear both to the -1. And this is we are doing here actually. Okay. Otherwise, for underflow, this is the condition: front and rear equal to -1. If front and rear is somebody can ask you interview like this: if front and rear both are equal, what do you mean by that? What do you mean by that? If front and rear in the queue is equal, so what do you mean by that? What that means is, if front and rear both are equal, that means queue is having how many elements? Q is having one element. Q is having only one element. If front and rear is equal to, if both are equal, one element. Yes, Ravish, means one element will be in the Q. One element is there in the Q. Okay. But front and rear can also be equal when they are having -1 value, but we have already covered this condition. Okay, we will not reach up to here because we already set this condition. Okay, after this condition, whenever front and rear will be equal to 1, there will be one element in the queue, and we delete the element. Deleting the elements means we print the element, and we set front and rear both to -1. Otherwise, on all other cases, simply take the element and simply take the front element, increment the front. Okay, now increment the front means front equal to front plus 1. Front equal to front plus 1. Why we are doing this again? Because again that can happen that my front is at the end. My front is at the end. Okay, I deleted this also. After deleting this, I will come back to 0th position. I need to come back to the 0th position. So front can maybe, this is rotating, we are circulating, we are in a circle actually. Okay, so for that we need to again take the mode. That's why I say that, okay, this mode part is important, because we are using this C to check overflow while incrementing the rear. We again take the mode max while incrementing the front. Again we use the mode max, because we are using we are using the array as a circular array. We need to move from the n-1 position to the 0th position, and that can be done only when we are taking the mode with n. Okay, then only we can reach to the front. So that's why we are taking mode. Okay. Okay, so this is all about NQ and DQ operation. I hope yes, that's it about Q itself. Now please keep answering the questions. Okay, keep trying the questions. These are the real questions on which you need to work in exam. So this is GATE 2021 question, not that much old one. So this will be easy for you people if you understand. the concept, that will be easy. So we are performing one, we have a empty stack and we are performing push operation. Then we are inserting 52 push operation. Then we are performing pop. So we will delete 52. Then again we insert 55. Then we insert push operation 62. Then we pop the elements, that will be 62. So we store 62 inside the S. Okay, and now we have an empty queue, and we are performing these operations. We are in our queue actually. So first we inserted the 21, then we inserted 24, then we delete one element. We know we will delete 21. Then we insert one another element, inserting from rear, and insert another element 32, and then dq one element, that will be 24. So q will be storing value 24. So they're asking what is the s plus q, that is 62 plus 24, that is 6 and 8. Yes, and Ravish is right. A is the right answer. Yes, let's move on. So can you try this one? Suppose a circular queue of capacity n minus 1 elements is implemented with an array of n elements. Assume that insertion and deletion operations are carried out using rear and front as the array index variable. So we are inserting at rear and deleting at front. Okay. Initially, the front and rear is set to 0. Okay. Initially, they are set to 0. What is the condition to detect the queue is full and queue is empty? What should be the condition to detect queue is full and queue is empty? Now we cannot say that okay, uh, front and rear equal to -1 for queue is empty, because they have said that initially the front and rear value is 0. Okay, and not one more point, we are using circular queue. When the queue is empty, when will be the queue will be empty? In this case actually they said that okay, initially this will be the condition. Initially this will be the condition, rear and front equal to 0. Okay, so if rear and front equal to 0, now they little modify the code. They are saying that okay, in this queue initially the rear and front and rear are pointing to 0th element, and there is no element in this actually. Okay, so this is how we need to move is, when we will insert the element, we will insert the element. Let's suppose we insert a here, then we increment the rear. Okay, we need to move like that. Okay, we need to behave like this in this. Okay, so at least we can tell one thing, when the queue will be empty. So this is the condition of they have already given, when the queue will be empty, when rear equal to front, when rear equal to front. So when the rear will be equal to front, then the queue will be empty. And for queue will be full, the condition will be same, but we have already covered. Okay, because this is a circular queue, and the condition will be same. And what was the condition? Front equal to rear plus 1 mod n. So you can check out these two conditions. One is for empty, the condition is if front equal to rear. For full, the condition should be this. So you can see that here A is the right answer. This is matching for full, and this is matching for empty. So you need to think over it. See, important point here is that you need to think. Maybe I'm not giving the sufficient time to you people right now, but you need to think over it and you need to answer these questions. Okay, yes, A is the right answer. You can think over it again otherwise. So this is another question. You can try. So let me explain the question. We are implementing a queue using circular linked list. So you can see in this diagram, or what is this happening? So we are using a circular queue here, and we are inserting a we are using this linked list as a queue. We know that we can use any data structure. We can use linked list as a queue also. Okay, the important point is here is that we will point one node as a front and one node as a rear. Whenever we will insert, we will insert at the rear. Okay, so here in this case, in this diagram, front is this, rear is this. So if I want to insert, I will insert here one new node like that. Okay, and then that will circularly point to the front. So they are asking, a circular linked list is used to represent a queue. A single variable p is used to access the queue, to which node this p point shows that both the operation of nq and dq can be performed in constant time. We have a p pointer. P should point to which node so that nq and dq operation can be performed in constant time. So if we point P here, you people are right. So if I want to insert one node, I can insert one node here. That will take constant time. And I know the address of this node that is here. I can store it here. This will take constant time. Generating a node take constant time, and adding this node after this take constant time, because I know the address of this node. P is pointing here. But what about deleting? We know that we delete from the front, so we can access, we know the address of this node also. Okay, we know the address of this node also, so we can delete the we can access the address is here for this node, so we can delete this also, and we can point out here. So both will take constant time. Yes, you are right, is the right answer. You can try this question, you can try it yourself later on, is the right answer. And this is the GATE 2022 question. This is interesting question actually. This is interesting question. Let me explain the question, and this will be your homework. You need to share the answer in the comment section. Okay, you need to solve it yourself. You can take the snapshot. So meanwhile, let me explain the question. So simply they see, they consider the q1. We have a q1 and having four elements like 1 2 3 4, and q2 contain none. So we have q2 also. These are two q's. So q1 have four elements 1 2 3 4. Q2 is empty, that have none, nothing, as shown in the picture and shown in this picture. The only operation allowed on the two q's are nq and dq. We can perform only nq and dq operation on these q's. Okay, the minimum number of nq operations, the minimum number, this is the question, the minimum number of nq operations on q1 required to place the elements from q1 to q2 in reverse order, okay, without using any additional storage is. So this is the question is what I'm repeating again. uh, the question is that we are provided two queues, q1 and q2. q1 have four elements and q2 have nothing. We want to shift q1 element into q2. We want to shift these element here like this, as shown in this diagram. In this diagram we want to shift these element, but in reverse order. Like these were here 1 2 3 4, and now these are in reverse order 4 3 2 1. Okay, we want to shift these elements from here to here. So they're asking what is the minimum number of NQ operation, insertion operation, that you need to perform on Q1. On Q1, what, how many minimum number of NQ operations you can perform while transferring this element, placing this element from Q1 to Q2. so you can think over it. So let me wait for some 1 minute, so that if you want to answer it right now, you can answer it right now also. Otherwise, you can try it at home. So I let me wait for 1 minute for you people. After that, I will wind up this session. So today we cover actually stack and queue. There remains the two main operations actually. In stack, the push and pop, and we also learn about infix to postfix valuation, and infix to postfix conversion, and postfix evaluation. And after that, in queue, we implemented the queue actually circular in using circular array. That is important. With simple, you all that will be very trivial actually. It's a simple array. Without circular array, that will be very trivial. So with circular array, we implemented that, and these are some of the questions we solve. So this information is, believe me, enough to solve these questions. Although, see, that information is required, but you need to think again on these questions. But that information is enough. What I want to say is that that information is enough to work on these questions. I know you may be finding difficulty to solve these questions, but the only solution is practice. Okay, one thing is, one thing I can ensure only from this lecture is, that's why we solve so many questions. I want to ensure you that you have already taken enough information about stack and queue. Now you can solve the gate question. You can directly jump to the gate question, and you can work on that. Okay, you have enough information with you. You have all the information with you. Okay, so that is sure. After that, you need to practice, because these are apti questions actually. These are not only about stack and queue. This is the apti test actually. Gate exam is checking your reasoning skills actually, with how you will solve with that knowledge, with the knowledge of queue and stack. How the queue, first you need to know how queue and stack works. After that, you need to apply that. Okay, that's it from my side. Please share the answer uh, in the comment section. Otherwise, the answer is here also. Explanation is here also. I'm not going to explain that. If you will check out, you will understand easily, but I'm not going to explain now. Please don't take the help of this solution. Please try it yourself. That's it for today. Thank you everyone. Thank you Ravish, Mukesh, Varun, and everyone actually, for Divyanshu and everyone, to being with me for more than 2 hours, 2.5 hours. Thank you everyone. Tomorrow we will come with very important topic, searching and sorting, and we will cover lots of interview questions also, and lots of gate questions. Okay, and that will be on smartboard, so you will enjoy more. I believe you will enjoy there more. I will come with more energy. Okay, bye bye. Hello everyone. Welcome to the Gate Crash course offered by Geeks for Geeks. My name is Puneet Kansal. I am mentor at Geeks for Geeks. In this session, we will discuss about the tree. Tree is one of the most important topic in programming and data structure. We will try to cover the most important concepts related to tree in this session, and I hope that will be useful for your in your gate preparation, and also that will be useful if you are preparing for DSA. Then also that this session will be useful for you people. So let me share my screen with you people. If you are new here, let me tell you. So we are actually, this tree session is the part of this gate crash course. Okay, this is the one part of the gate crash course. In gate crash course, actually we are covering the five most important topic from every subject actually. Okay, and if you want to if you think that, okay, you are new to gate and you just want to clear the gate exam, then this course can be helpful for you, because here we are covering the five most important topics. So after taking this gate crash course, one thing is assured, that at least you will be able to clear the gate exam. And if you are already preparing for the GATE exam seriously, then this series of GATE crash course can help you to revise the five most important topics from every subject. Okay, the subjects which comes in the GATE exam. Okay, and about this particular session, so in this session we are going to cover this tree topic, which is one of the most important topic. Okay, thank you Avintika for replying. Thank you Mukesh, welcome back. So in this session, we will try to cover as much as possible about the trees. Okay, but still I will start with binary tree and binary search tree. I think they are also vast topics, so I hope they will be finished in this session. And if you are not preparing for GATE exam, still this session will be helpful for you. If you are just want to improve the DSA, if you just want to improve the DSA itself, then still this session is going to very helpful for you. Okay, because here we are going to cover the very important concepts related to tree. Okay, so let me start this session now. uh, so we will cover introduction to tree. As we know that in every session we start from basics. I don't expect anything you know in advance. And so prerequisite for the session is nil, but we will go in very advanced. We will go up to the gate level. We will start from basics, but we'll go to the gate level. Okay, so we will cover the binary tree and binary search tree in detail, and then we will take the gate previous year questions from these topics. Okay, first we will cover the introduction to tree. Okay, so let's start with the introduction to tree. Starting from very basics, like definition of the tree. So tree is a non-linear hierarchical data structure. Non-linear means, okay, the data is not stored one after the another. It's not like that. Just like in data store, array is linear data structure, and linked list is a linear, means data is storing one after the another. But here that is not storing one after the another, so that is non-linear data structure. Okay, and consisting of collection of nodes such that each node of the tree stores a value. So each node of the tree, this is the one node of the tree which is storing a value. A is the value here, and a list of reference to the nodes, and this is also storing the reference to the other nodes. For example, this part is having the address of left node reference, and this part of the node is having the right node reference. Okay, so simple one thing. Linear tree is a non-linear data structure in which every node is having some data. We are using the data structures to store the data. One thing is clear, data must be there. Okay, and some more information is also there in each node. Means like this node is having the left, uh, store the address of left subtree and right subtree. That's it. So every node is doing like that. And if we don't have the right subtree, like, then we store the null. We store null. Okay, so this is the definition of the tree. And what are the different applications of the tree? Like in file system, we have application files. Our file system is actually, we have folder inside folders, and so there, that is spreaded just like a tree only. Okay, so binary search tree is one of the important data structure we use in searching. Heap tree are one of the most important, from not only from GATE point of view. Actually, these are also important uh, from company's point of view. B tree and B plus tree in database, if you want to store the data. Spanning tree, if you want to span all the nodes in a graph, then spanning trees are there. Organizational charts. So like there is a manager, then sub managers, like that, and then further employees. So they are also, organization chart is also in the form of trees. Syntax tree are in compiler, you know, compiler design actually. So there are many type of trees we are using in different areas actually. And that's it. Now we can solve one question. Okay, now we can solve one question from the gate from the gate. So simple, let me read the statement. Consider the following nested representation of binary tree. So we are given this representation. They are saying that okay, we have some binary tree representation like x, y, and z, where y and z are left and right subtrees. Y and y and z, y and z are left and right subtree. Actually, that should be x and z. That should be like x and z. X and z are left and right subtrees, left and right subtree, and actually of the okay. And y is storing the data. Y is storing the data. Or okay, so just like we are storing the data in a node. So this is the representation of binary. This is representation of a binary tree. Okay, so this is showing the left tree, this is showing the right tree, and this is showing the data actually. Okay, uh, maybe this data is been printed in wrong way. This should be y. Okay, so they have mentioned a y and z to be null. Okay, so rather than x y z, let me rectify this thing. This should be, so this should be x in the middle and y here and z here. That's it. Okay. So let me try this question because there is a this statement I have changed it. So consider the following nested representation of binary tree. So this is the representation. This indicates that and z, y and z are left and right subtrees, left and right subtrees. So the y is representing left and z is representing right subtree respectively of node x, Note that y and z may be null. Y and z may be null. Okay, y and z may be null. Or further nested, they can be further nested. Y and z may be further nested actually. Okay. Which of the following representation is a valid binary tree? Which is the following representation is a valid binary tree here? Okay, so let's see in this representation you can see this is not the valid representation. A is not the valid representation. Why? Because in the representation we have like y, x, and z. Okay, we have y, x, and z. So we have three elements in the brackets, but here we have four. These don't have any meaning. Four elements in the bracket don't have the meaning defined in this definition. Okay, four elements. I don't know which one will be the root, which one will be the left child, which one will be the right child. Okay, maybe in this case, okay, 5 may be the root, maybe 6 may be the root. I cannot decide if four elements are there. Okay, so this type of representation is not given here in this definition, so I cannot predict in this. What about this, the b1? Actually in b1 if you will see that uh, this is also not the valid representation according to this definition, because here the opening brackets are 2 and closing brackets are 3. Okay, so this is also not valid representation. C is the right answer. Here we have three elements in this. We know that we understand this definition. Again we have three elements, we understand this thing. And further in the outer brackets, further we have three elements. Okay, one will be one will come from here and one will come from here. Okay, so this is valid representation. Further, this is D is also not valid representation. Why? Because they don't tell us that okay uh, about the two elements. This is valid, 2 3 and null is valid because they tell us okay z can be null, this can be null, no problem, but they don't represent the null here. Okay, if they have written 4 5 null, then this could be the right representation, this could be the right representation. But in this case this is not the right representation according to this definition. Okay, okay, so C is the right answer here. Okay,
So I think I have taken a little bit tough question in the starting. So it's okay. Still the answer is getting, we are getting C. Let's move on. So answer is C here. Let's move to another question. This question you people may try. This is GATE 2015 question. So you just need to know about the tree structure. If you know about the structure of binary tree, if you know about the structure of binary tree, means in binary tree, we every node is having either 0 child, 1 child, or 2 child. And you can try this question actually. So they are telling us that, okay, this is the definition. This is the definition of the height. The height of a tree is the length from longest root to leaf path. This is the definition of a tree. Height of a tree. So if somebody asks me what is the height of this tree, I will say 1. The longest path from root to the leaf. So somebody asked me what is the height of this tree. So longest path is now this. So height is now 2. 0, 1, 2. Somebody asked me what is the height of this tree. So now 3, 1, 2. This is the longest path from a leaf to the root. Okay, they provide us this definition. Okay, they're asking the maximum and minimum number of nodes in a binary tree of height 5. Can you tell me maximum and minimum number of nodes of a tree which is having height 5? Can you answer this question? If the binary tree is having height 5, then what can be the minimum number of nodes? So maybe you can draw the tree like this. You can directly draw the tree like height 1, 2, 3, 4, 5. So how many nodes are there? How many nodes are there? So here you can see, yes, Dream Gamer says that that is 6. That is 6. So minimum number, you tell me 6. Can you tell me what will be the maximum number of nodes that can be possible? Okay. So if the height is, let's suppose height is 1. If the height is 1, here root at the root we have height 0, so we are getting many information also from here. If the height at the root is 0, then height, then next node, next level is 1, and so on. Okay, so if the height is 1, number of nodes are 3. If the height is, let me, maximum nodes I'm trying to make in binary tree. Okay, so if the height is now 2, okay, so let me make it. So if the height is 1, the number of nodes are 3. If the height is 2, the number of nodes are 7. If the height is 0, you can say, okay, only root node you have. Let me draw it here, 0. Then number of nodes are 1. And so we are getting the answer A. Everybody is saying A. So can you share the formula for journal formula for finding the number of nodes, maximum number of nodes if height is given? Actually, there are many questions related to this. There are many questions. I have taken one from here so that we can cover the minimum part also or maximum part also. Can you share how, if rather than 5, 15 is there, then we cannot draw up to 15, a tree of height 15 actually. So somehow you are getting this 63. Yes, you people are right. You are getting 63. How you are getting that? So Ravi says that if we are making the 2 power h plus 1 minus 1, this formula is telling us maximum number of nodes in height h binary tree. So let's try to find out, okay, this is working or not. So for 2 height, let's see. So 2 height, 2 power 2 plus 1 minus 1. So 2 power 3 minus 1. Yes, this is working. 8 minus 1, that is 7. Okay, let's verify for this tree also. So 2 power h plus 1 minus 1. So that is actually 2 power 1 plus 1 minus 1. So that is actually 4 minus 1, that is 3. That is still working. Okay, so for 2 power,
Now if height is 5, that will be 2 power 5 plus 1 minus 1. So that is 2 power 6. 2 power 6 is 64 minus 1, that is 63. Yes. So important point here is that if you want to find out, important point, let me summarize now. From this question, what we find out from this question, two important information we get. Uh, One is what can be the maximum number of nodes in a binary tree and what can be the minimum number of node. So you already given me the formula for maximum number of nodes. So that is 2 power h plus 1 minus 1. Can you give me the formula for minimum number of nodes also? Can you give me the formula for minimum number of nodes? So can you anyone give me the formula for minimum number of nodes? So you already tell me the answer is this 6 and 63. So dreamer says that h plus 1, height plus 1, height plus 1. So this is for minimum and this is for maximum. You people are right. So A is the right answer here. A is the right answer here. Okay. This is actually gate based question also, but this is also asked in Google company. They ask to write the code actually, but I'm not asking you to write the code. They give the question to write this code. Can you tell me what is the output of this code? So this is a gate question also, but this is a programming question also. So can you please tell me what will be the function of the given binary tree based code? This is the binary tree based code. What this binary tree based code is doing, what we are doing here, can you please find out this thing? So if you are preparing for company, product based company, still that will help you. And this is related to gate also, this question, so that's why I pick it here. So can you tell me what is the function of this code? So no doubt, see, I will ask more question from you rather than I will explain the things. I will definitely explain the things, but my approach will always remain that you people think over the problem and you people answers that. Okay, I know it's evening and you may be tired, maybe that things happens actually, but still I'm asking from you people. So we get one answer from Ravish. Count the number of nodes. Ravish says that this is counting the number of nodes. Any other answer from anyone? So okay, yeah, actually that is right. What we are doing here is we are counting the number of nodes in a binary tree here. Actually, for every time we are calling the function, every time we are calling this function, we are adding one. We are adding one. Every time you are calling the function for a node, so you are adding one here. Okay. And when you get null, actually when you are calling for null, you're adding 0. Okay. When there is no node, you are calling, you're adding 0. But for every node, actually you are adding 1. So this is the recursively you are calling the same function for every node, for left and right node, for all the nodes you are calling the recursively calling this function. And for every node now we are adding 1, recursively you are adding 1 actually. Okay, so from here we will get 1 and 1 plus 1, this will be 2, and here we will get 1, here we will get from this node 1. So 1 plus 1 2 plus this node 3 and 2 plus 3 5 and plus this one 6. So every node 1 and previous additions you will also get in the recursion. Okay, okay, you can try this one also. So what is the function of given binary tree based code? What is the function of this code? You can try almost similar code, but little changes are here. Little changes are here. This condition is added and I remove the plus one from here. So can you tell me, okay, what this function is doing? Please think over it. These are the important questions which are asked in product based companies also, and from gate point of view also these are important. That's why I give it to you people. So if you will try it, that will be, if you will try it yourself, then there will be more learning rather than just I will tell the answer to you people. So just try it, either getting answer or not, that will not matter actually, because the moment you will try, you will get the learning will happen. The moment you try, the learning will happen. Please answer in chat box. What will be the function of given binary tree based code? So somewhat related to previous one also. You can think over it and answer it. So this is actually returning one when a node left side, when a node left side, and when the node right side, both are null. Both are null. For those nodes we are adding one. For those nodes whose left and right both are null, then we are adding one. Otherwise, for null, further if we will call function for this null, actually this will return 0. Okay, for this node, this type of node, this will return 1. Otherwise, this is not adding anything else for anyone, just recursively calling the function for left tree and right subtree. Left subtree and right subtree, calling the same function again, okay, recursively. This is adding 1, this is returning 1 for those nodes, which have left child as null, right child as null. So Avantika says the answer is A. I don't have given options here, Avantika. So this code is what that is doing. That is returning 1 for this type of node, in which left and right both are null. So what this function is actually trying to return, that trying to do. So Mukesh says that is counting leaf nodes. Yes, Mukesh, that is counting the leaf nodes, because we know that leaf node don't have any child, either left or right. So this is counting these nodes. This is returning 1 for all the nodes which is having left and right both are null. So this will kind, for this particular diagram, this will return 3. Even you have one child, one left child, this will not count 1 for it. This will not return 1 for it. This will not return 1 for it. Okay. This will return 1 for only for those nodes which is having left and right both are null, which is both are null. So this is actually counting the number of leaf nodes, in the binary tree. That's it. This code is counting number of leaf nodes in the binary tree. I have one more question related to the same. Now, can you modify the same code? Can you modify the same code and count the number of non-leaf nodes? Can you think over that? I want to count the non-leaf nodes. What the change I have to make in the previous code? What the change I have to make to count the non-leaf node? Now you know two important things. One important thing is that you already counted number of nodes in the binary tree. Okay, you already counted here. You already counted number of nodes. You counted number of nodes in the binary tree. You know this code now. Okay, you know this code now. You know also about this code. The second one. The second code says that you know how to count the number of leaf nodes. So this is the code for counting number of leaf nodes. Now the third question is can you modify a little bit this code to count number of non-leaf node, number of non-leaf node. So Mega is asking, is this class conducted daily? Mega, actually this class is the part of we are covering five most important topic in programming and five most important topics from algorithm part. So total there will be 10 important topics we are covering from DSA. So if you are interested in DSA, then this class actually happens on Saturday, Sunday, and this is the part of GATE crash course, and you can find the detail in the description. Previous recorded lectures you can find out there on the GATE channel, also on Geeks4Geeks GATE channel, or in the description you can find out all the detail. So Dreamer actually replied for this thing. Dreamer says that if left side is not null or right side is not null, if left side is not null, he says that I will make, okay, if left side is not null, or he write or here, he write or here, and he says that okay, right side is not null. If any of them is not null, then still that is an internal node. Maybe both are not null. Uh, maybe both are not null. That can also happen, or maybe one is not null. So this is the internal node. When one child is there, another child is not there, or maybe we have both the child, that is also allowed. Okay, so if we modify this thing, yes, we are able to count the non-leaf node. You are right, actually. One way is that what is shared by the dream gamer. Another solution is shared by here by me. That can be also okay. If I'm saying that okay, if both are null, then I will not count this. I'm just picking it from different end. Like you were counting this, you are taking one for that. That is also fine. That is also fine. And another one is that in this code, actually in this code, I'm saying that I will not count this. I will not count this node. If both are null, I will not count. If both are null, I will not count. Okay. Otherwise, I will count for every node. Otherwise, I will count for every node. So this is another solution. So we get two solutions. One is from Dream Gamer, who give in the chat box. That is also right. And another solution is this. In this solution, we are saying that simply we will return 0 for leaf nodes and 1 for all other nodes. Another solution by Dreamer says that he is saying that I will add 1 for only non-leaf nodes. So he simply write that not equal to null, and make it or also, so that if both are not equal to null, like this node or this node, which are in both are not null actually here, so that will be counted and that is returning 1. So that can be another solution. So we get two solutions for this problem. One more problem which is also asked in so many product based company, and GATE also, related to GATE also. Can you tell me the function of this binary tree based code? Believe me, if somebody will ask the question from binary tree in either in after GATE exam or maybe in company, they will definitely ask out of these five problems which I shared with you, definitely that will ask one of the question. One thing is ensure, if they are talking about the binary tree and they want to ask something good from you people, something logical and really uh, good level question from you people, then definitely they will ask from these five problems. These are the one of the five related problems and five important problems from binary tree. So please let me know what is the function of binary tree based code. Thank you, Shikhar, for the appreciation. So you can find out my other sessions also. uh, you can go in the description and you can find out over there the other session from DSA. If you want to find out, or from other subjects, you can find out there. So meanwhile, please let me know what is the function of this binary tree based code. Little again, we make the little modification only. So see,
In this, I'm saying that if null is there, for example, this node I'm talking about, which is completely null, so I'm returning 0. And see, if left and right both, and if left and right both are null, again I'm counting that 0. I'm returning 0 for that. So for this type of node I will return 0. Like, means for leaf, see, for leaf we are returning 0. Okay, but here what we are doing, we are adding 1 also, but here I'm taking max of left subtree or right subtree. Actually, this is my left subtree and this is my right subtree. Okay, so for lefts, you're calling from the starting from the root, and then this left subtree you will pass it through this. Actually, you will pass this node, actually address of this node which was here, and this right subtree will be passed on in this area, and they're counting something max out of left subtree and right subtree, and adding 1 in that. So what that is trying to do, this is not counting height of the tree plus 1, this is counting the height of the tree, that is counting the height of the tree. What this one is doing, see, what this one is doing, let's try to find out how this is counting the height of the tree. Ravi says this is counting the height of the tree. How? See, for every, we started from the root node. Okay, if we started from the root node is not null, its left child and right child both are not null, these are not null. Okay, then we call, what we do, we add 1 for that. We says that, okay, this is contributing in the height, this node is contributing in the height, so we say that, okay, 1, we add 1 for this node, and then we take max of left subtree and right subtree. So here we will find the height of left subtree. Again we will call the same function. Okay, again we will call the same function for left subtree and for right subtree, whichever will give me the maximum height. In this case both are giving the same height, both are giving 1 and 1, both are giving 1 2 2, this is also giving 2, this is also giving 2. But let's suppose I have one more node here, so in this case that this tree will give 3 height, and out of 2 and 3 we will take the maximum and we will add 1 for this node. So what we are getting here is, we are getting the height of the tree, we are getting the height. What is the height of a tree? So height of a tree we already know, from root node to the farthest leaf, actually farthest leaf, whatever is the distance, longest path, that is the height of the tree, and which is we are finding out here. Okay, according to this actually code, we are actually finding the, I have to say level, number of levels even. Okay, not height, number of levels, because for this node I'm counting 1, for this node also, for this node also. Okay, so this is return, this will return 3 actually. Okay, although the height will be, 2. So I think that's why Ravish reply that height of the tree plus 1. Ravish, you are right actually. So this is returning the number of levels, this code is returning the number of levels, and we know that level is actually height plus 1. Level of a binary tree is height plus 1. So this is returning number of levels, so this is returning height plus 1. You are more accurate, actually you are more accurate. Okay, so these were the some important points. So we covered from company point of view and from GATE point of view also. Now let's talk about the tree traversals. So we want to traverse all the nodes in the tree, we want to traverse all the nodes in the tree. So we have 3 methods to traverse. One is pre-order traversal, one is in-order traversal, one is post-order traversal. So in pre-order traversal, we traverse the root node first, then left child, then right child. In in-order traversal, we traverse left child first, then root node, then right child. In post-order traversal, we traverse left child first, then right child, then root node,
Good evening, Sandeep. So I'm little bit, I'm assuming that now, okay, you people know about this thing. Even you don't know, don't worry, I will tell you. But I'm giving you people a chance that, okay, can you please let me know what will be the, okay, can you tell me the pre-order traversal of this tree? Can you tell me the pre-order traversal? In pre-order traversal, please write in the chat box. See, I can also directly try answer these all things with you. I'm asking the question from you people is that, why I'm asking the question from you people is that, if people will answer the question, if you people will think, then you will learn more. If I will tell the answer, believe me, that will not contribute that much. Actually, that is the reality. You can say that that is harsh reality, but that is the reality. That's why with every slide I'm asking to you people, can you people tell me the pre-order traversal of this tree? Then I will also tell you, I will also explain one easy way, one easy shortcut trick to find out all this in one go. So can you tell me, so pre-order traversal how works? That first visit the root node like 50, that will traverse first, and after that left child like 17, and then right child like that actually, first root, then left, then right. This is how pre-order traversal works. Traverse, we want to traverse all the nodes in this tree. Can you give me a pre-order traversal of this tree? Pre-order traversal, can you write in the chat box please? Can you try it? Right or wrong doesn't matter, you just try it. The moment you will try, you will get you will the learning will happen, the moment you will try. Please answer, please try to find out the pre-order traversal. You just need to know one thing. First uh, root node will be traversed, then left child, then right child, every time. Like we start with 50, then first we traverse 50, and then we will move to the left child. So here also in this subtree again we will check out first root, which is the root 17. So then we will traverse 17, like that way, so on. Can you give me the complete sequence? Can you please write the complete sequence? If you will try, then more learning will happen as compared to I will tell you directly the answer. Node left, right, left node, right. Node means root node I'm talking about. So left, right node, root node. If you will try, then you can ask for many other questions will also come in your mind. Okay, so we get one solution. Let's check out if that is right or wrong. Otherwise you can try for other also. Dream gamer, you can try for other also. Meanwhile, let me try at my end. If you are trying, please keep trying. That is more important than if I am trying. Okay. Okay, so one way is that you go through like that, first root node, then left, after coming to left again root node, then left again, coming to 9 again, then root node, then left, there is no left, then you will move to the right. Okay, like that you can find out. And one shortcut way is that, okay, just make some dummy nodes here. So every node, make it just like every node must have two child by adding some dummy nodes. So this is having now left child also. These 50 is already having left and right child, 17 is already having, 9 don't have left child, so 14 I don't have right child. I'm just adding some dummy nodes. So this will help me to find out easily in fast way, to find out these to make find out all these traversals. Okay, some of you may be already knowing this. So if you don't know, you can check out this thing. Otherwise, if you already know, you can answer the questions of in order and post order. Okay. Okay, so how you need to find the traversal? We are going to traverse all the nodes. Okay, the important, what we are doing, we are traversing all the nodes. Okay, so you need to start from the root node. Okay, so you need to start from the root node. So if you are finding the node first time, you will, every time you will find the node, either you will find a node three times actually. You will find the node while traversing, you will reach to the node three times. Okay, If we are reaching the node first time first time you are reaching the node, first time you are finding that node, traversing that node, then you can add that node in the pre-order traversal. If we are finding that node second time, means you already visited it first time, now you are visiting it second time. If you are visiting a node second time, then you can add it in the in order traversal. If you are visiting the node, if you are traversing the node third time, the same node you are visiting third time, so you can add that into the post order traversal. So I'm saying you're visiting every node 3 times. So start from here 50. So I'm traversing it first time, so I will add in pre-order traversal. Let me write here pre-order traversal, in order traversal, and post order. Okay, so in pre-order I will write 50 because first time I'm traversing it. Then I move to, after this I move to 17. First time I traverse the 17, I add in pre-order. After that I move to 9. First time I visited 9, so I here from left to right I need to go through complete tree and come back to the root. Okay, that's it. Now after this I reach to the 9 second time. First time here and second time here. Okay, second time if I get, I will add it into the in order. I will add it into the in order. So 9 will be added here. And after that I visited 14. 14 I visited first time. Okay, so 14 I visited first time. I will add in the pre-order. First time I visited the 12, so I will add into the pre-order. After this, second time I visited the 12, so I will add it into the in order. Now third time I'm visiting the 12. Third time I visited. So I visited that 12 from first from here, then after that from here, and then from here. Okay, third time you are visiting, so you will add third time you will add into the post order traversal. Okay, I will tell you actually what is the intuition behind that. I will tell you that or intuition also, why we are directly getting the solution all this traversal by this method. I will tell you that thing also, but let's first find out. So second time I'm traversing it. First time I traverse it 14 here, and now second time I'm traversing here. So second time if you are traversing, I will add into the in order. And now third time I'm visiting 14, so I will add into the post order. Now I'm at the 9, which is third time I'm visiting 9. Already visited one and second time, and this is third time. Third time I will add in the post order. Now I'm at 17. So second time I visited it. First time already visited here. Second time here. So second time visiting though. So I will add into the in order. And then I move to the 23. First time I'm visiting 23. Okay, first time. So add into the pre-order. Now first time I'm visiting 19 also, add into the pre-order. First time pre-order, second time in order, third time post order, that's it. So now after this I find out 19 again. So second time I visited it, so add in order. Third time I get it, visited it, so add it into post order. Second time 23. So let me finish it fast now. Third time 23. Third time 17, second time 50, first time 76, first time 54, second time 54, first time 72, first time 67, second time 67, third time 67, second time 72, third time 72, third time 54, second time 76, third time 76, and third time 50. So this is the pre-order traversal. This is the in-order traversal of this tree, and this is the post-order traversal. Actually, let me now give you the intuition how we are getting these answers also. So let me give you the intuition. We say that pre-order traversal, we visit the node first, root node, then left child and right child. Here we are visiting left child, then root node, then right child. Here left child, right child, then root node. Okay. So here you can see that every time we are visiting the root node, here we are visiting the root node at first place. Here we are visiting the root node at second place. Here we are visiting the root node at third place. Okay. So whenever if you will write the recursive program for that also, in recursive program also you will print the node, you will print the root node only. Okay, you will print the root node only. So first time is telling that first time if you will visit this node, immediately you will print that node. Immediately you will say that okay, I visited that node. Every time with the root node you will say that okay, I'm visiting that, I have visited that node. So we are traversing, we are visiting all the nodes. Okay, here I'm visiting the root node in the starting in the first place, here I'm visiting at the second place, and here I'm visiting at third place. So that's why that trick is working. Means if we are finding this node first time, then actually that will be printed in the case of pre-order. If we are finding it in the second time, then you can print that in the case of in order. And if you are finding it third time actually again, then actually you have means covered left and right, all of them you have already covered. Left and right you have already covered, and now you can print this node into the post order traversal. Okay, so that's why actually this shortcut is working, and you can apply this one. And if you have any doubt, you can ask me in this. So if that is clear, then you can try this gate question yourself. This is gate 2014 question, so please try to answer it yourself. And if you have any doubt from any slide, from previous any slide, please ask me that question. Okay, you can write in the chat box. Otherwise, please try to answer it yourself. I do not share this thing with you people, but still I'm sharing. Actually, we as a humans actually in the morning actually we are full of energy. Okay, but in the evening we don't left with that much energy actually. And we so after the complete whole day, means sometimes we don't feel happy, and so after the whole incidents of the complete day, uh, we may not feel that much good. Okay, so this time may not be the best time for study, but still I'm saying that okay, you have to work on that, work on these problems. And that is one of the reason that actually you will see the beggars are only comes in the morning, because they think that the people will be happy in the morning more as compared to in the evening. So but still okay, I'm we need to work, we need to study. Please try, please try. Let's give this time fully to this topic so that we can fully understand this concept. So these are gate questions. If you are preparing for gate, ultimately you need to solve these level of questions. So let me write. Okay, meanwhile you are trying, I will also busy with you people. So SQPTR WUV, this is first option. The B option is SQPTUR WV, and the C option is SQPTWUVR, and the D option is SQPTRUWV. Okay, so again you can means make the dummy nodes and try to find it directly. So second time if you will visit the node second time, so you visit the S first, and second time. So this is also you're wasting second time now, third time, second time, first time, second time, third time, second time, first time, okay, second time. So this is also now second time u, and after that, okay, the r is now actually r you are wasting. This is not binary actually. This is ternary tree. So r is wasting now actually third time. No need to bother about that now. First time, second time, and this is third time, fourth time, and even this is third time. Okay. So which is the answer is matching here? SQPT RW UV. Option A is matching here. Option A is matching here. SQPT PT RW RW actually. SQPT RWV. Option A is matching. Option A is the right answer. Any doubt in this, Mukesh? So simply the node you are visiting second time, you will write the sequence in that way. So okay, okay. So A is the right answer here. It's okay. We have another problems with us. So this is GATE 2015 problem. You can try this one. Everybody, please try it, because DSA is not only about GATE. DSA is all about computer engineering. So that is going to help you everywhere. Either you're preparing for company or you are preparing for GATE, that doesn't matter. DSA is going to help you everywhere. DSA concepts are going to help you. You can try it. So you can find out the in-order traversal sequence for a binary search tree. They don't provide us the binary search tree. Still they are asking what can be the possible, in-order traversal of a binary search tree out of these four. Let's see how many people can answer it. You can answer it directly, immediately. You can answer this question. So immediately you can answer this question, and this question is actually I put the question so that you get some other information also. Like in this question you are getting some important information. If you know that, then you can answer it very easily. If you don't know, you cannot answer. That is sure. If you know that information. So Ravi says the answer is A. Ravi says that okay, first and fourth options are the can be the in-order traversal of the sequence, and Mukesh is also saying A actually, and the reason can be you people must be knowing, I know, otherwise you cannot answer the right answer. They are just checking you know that thing or not. What is that thing? The in-order traversal of binary search tree will always be elements in sorted order. So here you find out the elements in sorted order: 3, 5, 7, 8, 15, 19, 25. In fourth option also you must have find out the elements in increasing order. Yes, 4, 6, 7, 9, 18, 20, 25. These are in sorted order. Elements are in increasing order, sorted order. So the in order traversal of every binary search tree will provide us the elements in increasing order, and this should not be in increasing order, second and third. So 5, 8, 9, 12, 10. See, after 10, after 12, 10 is coming, not in increasing order. 2, 7, 10, 8. Okay. So after 10, 8 is coming, not in increasing order. So these cannot be in order traversal. Second and third cannot be in order traversal. And these can be the in order traversal of a binary search tree, because every binary search tree in order traversal is, you will find out the elements in increasing order. You must be knowing that thing. That's why you are replying the answer. So this is one important point also. So please try this question now. Can you tell me the post order traversal for the given tree? Can you give me the post order traversal for the given tree? Please try for this. Okay. So don't look at the answer. I believe on you people. So you can try it yourself first. Please try it yourself and then answer. Okay, we already get the answer from Mukesh and Ree. I hope you have tried it yourself. And C is the right answer, yes. So directly, easily you can find out, okay, you can add the dummy nodes, and rather than just move little bit, if you want to move fast, then the third node, the mode, if you are visiting third time, just simply you will print that third time, that's it. Find it in fast way. Third time, immediately you can print in post order. So third time, second, first, second, third, second, third. So this must be the GCD, BF, EA. Yes, C is the right answer. You all are right actually. Okay, so we have covered now, till now we have covered some, let me revise what we have covered till now. We have covered height of the tree through the questions. We have covered the basic introduction of the tree, height of the tree, binary tree actually we are talking about, and we have gone through various traversals. Okay, now let's try to construct the unique binary search tree. Unique binary tree. Let's try to construct. So we can construct unique binary tree if somebody provide us in order and post order traversal, or in order or pre-order traversal, in order or pre-order traversal, or in order or post-order traversal. If these two traversal are provided to us, these two or either these two, then we can uniquely we can find out the binary tree. We can construct the binary tree then. Okay, we can construct the binary tree. But if somebody provide us pre-order and post-order traversal, these are different traversal: pre-order, in order, post-order. So somebody provide us these two traversal, pre-order and post-order, then we cannot construct, or we have to more accurately say may or may not, we may or may not construct unique. I'm talking about unique. See, we can construct the binary tree with pre-order and post-order also, but we cannot uniquely, means only one tree. If somebody asks you to construct only one fixed tree, unique tree, if you want to construct, then you cannot construct with this. Sometimes you may, sometimes you may not. Okay, but in the case of in order and post order traversal, if they provide in order and post order, or in order and pre order, then you can construct unique binary tree. Unique binary tree we can construct. Okay, and you already know now this thing. In order traversal of binary search tree is actually sorted list. You already know this thing. Okay, let's now to construct the binary tree using in order and pre order, and in order and post order. Okay, so let's try to construct it with in order and pre-order first. Okay, in order, and so they provide us pre-order and in order traversal of the tree, and we need to construct the binary tree for that. How we will construct that? Very easy. So actually we know that pre-order traversal, actually in the pre-order traversal, node, root node come first, then left child, then right child. This is what happens in the pre-order. And in order, left child, then root node, then right child come. Okay, so one thing we can find out from pre-order traversal is which is the root node. Root node will be in the starting. So A will be the root node. Okay, and in order will help us. Okay, if we know the root node, root node will be tell by the pre-order traversal which will be the left child, left children and right children. What will be the left subtree and right subtree? So for example, here in this sequence, if A is the root node, which we get information from pre-order, now DBE will be the left child and FCG will be the right child. So A will be the root node, one thing is confirmed, and this DBE will be the left child. Okay, let me draw it. D, D, E will be in the left somewhere, and F, C, G will be in the right somewhere. Okay. Okay. Now, out of these three elements, which will be the root node? Which will be the root node? Again, we will ask to the pre-order traversal. He will say that, okay, next element is B. So B will be the root node here. And one thing is sure, D will come to the left, and E will come to the right. Okay. Again, we will ask, okay, next, which will be the root node? Pre-order is telling us about the root, because here root is coming to the left side. Okay, left, then the left child and right child. So D is the, actually one element is left, that will itself be the root. And for E also one element is left, that itself will be the root. And in this case, I don't know which will be the root. I will ask again here. So this pre-order says that C will be the root. C will be the root. It's not like that middle element will be the root. For this example, this is working. For other example, that may not work. Now F will come to the left, G will come to the right, because F is to the left of C and G is to the right of C. So F will come here, G will come here, and they are single element. Even you do not need to check. So we have constructed the unique binary tree now here. Let me erase this. We constructed the unique binary tree from pre-order and in order. Okay, if any doubt you can ask in this, otherwise I'm moving on. So let's construct the in order and post order. If you have any doubt in previous one, that will be clear from here also. Okay, if somebody provide you post order traversal and in order traversal, how to construct the tree? See, in post order traversal, we know that we first visit left child, then right child, then root node. So root node will be the always to the right hand side. So here A will be the root. Here in post order, we are checking from the right side. In pre order, we are checking from the left side. So once we get the root, pre-order will tell us, okay, which will be the left children to A and which will be the right children. So in this case, I will make A to the root, and D, B, and E will be somewhere to the left side of A, and F, C, G will be somewhere to the right side. Okay, and now next root is C here. So next root is C. So I will make C the root, and F will come to the left and G will go to the right. Okay, next one is G. G is a single element, so do not need to check. We were having confusion here. Which can be the root? Anyone can be the root. Or maybe in the starting also, which can be the root? Anyone can be the root. So that confusion is solved by pre-order or post-order. Okay, next one is F. Okay, next one is B. Okay, let me make B root here out of D, B, E, and then D will come to the left and E will come to the right. So E will be the root here and D will be the root. Okay, that's it. So we again constructed the unique binary tree using post order and in order. Okay, okay. Now here is the GATE question for you people. This is GATE 2020 question. You can try this. So pre-order traversal of binary search tree is this. They provide us the pre-order traversal. Then they are asking which one of the following is the post-order traversal. They only provide us pre-order traversal. Okay, first of all, can we find out? They just provide us the pre-order traversal in this question. They don't provide us in-order traversal. And I just tell you that we need in-order plus pre-order to construct the unique binary tree. Okay, either we require this or either we require in order plus post order to construct the binary tree. But here they provide only the pre-order. They don't provide us the in order. Can we construct, yes or no? Can you first tell me yes or no? We can construct the tree or not, first of all here. Unique tree or not? Yes or no? They don't provide us in order. And already I have committed you that, okay, we can construct the unique tree only when these two things are given. either these two or either these two. Actually, we can construct in this case. We can construct here. How we can construct here? How we can construct? They provide us pre-order. Okay, they provide us pre-order. We just need in order also. They provide one more information. They provide us that your the pre-order of binary search tree. This is the pre-order of binary search tree. So these are the these are the elements of binary search tree. Can you tell me what will be the in order? In order here, even though they don't mention, can you find out the in order traversal? In order traversal from here. You already know this thing. You already answered this question. You tell me that, sir, the in order traversal of a binary search tree, BST I'm talking about, of every binary search tree, in order traversal of every binary search tree is the elements in increasing order. Elements in increasing order. So just I'm putting all the elements in increasing order. So like let me put it here, 10, 12, I hope 10, okay, 12, 11 is there. After that 12, after that 15, I think, yes. After that 16, after that 18, after that 19, and after that 20. Okay, so we can find out the in order now. We have in order with us, we have pre-order with us, and we can construct the tree, and after constructing the tree we can find out the post order also. We can find out the post order also. So what was the important point here? So they just want to know whether you know two things or not. One thing, you need pre-order plus in order to construct the tree. After constructing the tree, you can find out the post order. Okay, so they are checking three things actually: whether you know how to find the post order traversal or not. Second thing, how to construct the tree using pre-order and in order. Third thing, how to find out the in order for a binary search tree. For a binary search tree, the elements should be in increasing order. You can simply arrange the elements in increasing order and you will find out the in order for that. Now you have in order with you, you have pre-order with you can construct the tree, and after constructing the tree you can find the post order also. You can find the post order also. Three things they are checking actually, you know or not, that's it. So I'm not going to solve this. You can try it yourself and write the answer in the comment box, because you know how to construct the tree. If you want me to solve it, you can write that in the chat box. I can try it. If you don't want, just don't write anything. If you want me to try this question, then I can try it for you. Otherwise, first you need to find the in order traversal, which is the increasing order elements. Then you need to draw the tree for in order and pre-order. After drawing the tree, you need to find out the post order traversal. That's it. Okay. So the answer for this question otherwise is B. You can verify it. And if you are getting the right answer, please write in the comment section, confirm over there. So that was all about now we covered the construction of unique binary tree using pre-order and in order and post order and in order. Okay. And even though they are not providing us the in order traversal for binary search tree, we can find out that easily, because in order traversal of binary search tree is actually elements are in increasing order. Okay, so we get all the important information about that construction of the unique binary tree. Okay, now let's move to the binary search tree itself. Let's move to this topic itself. So in binary search tree, what is the so binary search tree is a binary tree. First of all, binary search tree is a binary tree, you already know. Means either that have 0 child or 1 child or maximum 2 child. So here in this tree also you can see either we have 0 child. For this node we have 0 child, for this node we have 2 child, for this node 14 we have 1 child. Okay, so this is a binary tree. One thing is clear. Another property we are adding in is that in binary search tree, the left subtree, the the values at left subtree will be smaller than the root node, and the values at the right subtree will be greater than or equal to, will be greater than equal to parent node or root node. Here you can see 10 is greater than 8, 14 is greater than 8, 13 is greater than 8. 3 is less than left subtree. All elements should be less than 8. 3 is less than 8, 1 is less than 8, 6 is less than 8, 4 is less than 8, 7 is less than 8. Even you can check out in any subtree here also. Here in this subtree. So here 4 is less than 6, but 7 is greater than 7. 7 is greater than 6. You can check out in any subtree actually. This condition should satisfy all around for every node. Okay, you can pick any node. Let me pick this tree. Here these nodes are at the right side of 10, so this must be greater than 10. Yes, 14 and 13 are greater than 10. 13 is at the left hand side of 14, so that should be less than 14. Yes, that is less than 14. So this is the property of the binary search tree. We know this thing. Now, can you people tell me? Now, we use the binary search tree is actually one of the very important data structure we use for searching the elements. So can you tell me what is the best case? Best case. Okay, first of all, best case. What is the best case complexity of searching an element in binary search tree? What is the best case? So what is the best case complexity of searching an element in the binary search tree? Please write in the chat box. I want to search any element. Okay, what will be the best case complexity to search an element in binary search tree? We know the structure of the binary search tree. So how we search in the binary search tree? Let's suppose I want to search, I don't know, I want to search 7. Then how I will search? I will compare 7 with the root node because 7 is less than 8. So I will look in the left subtree. I will look in the left subtree because 7 must be in the left subtree. That cannot be in the right subtree because right subtree having all the elements greater than 8. So again I compare with 3. 7 is actually greater than 3. So I will check out in the right subtree now. So 7 is 6 greater than 6. I will check in the right subtree. I find out the 7. So this is how we are searching in the binary search tree. Now, can you tell me what will the best case complexity? Anyone? What is the best case complexity to search an element in a binary search tree? I want to search an element in the binary search tree. So Dream says that is order of 1, and Dreamer is actually right here. That is order of 1. Best case we are talking about. So in best case actually you are actually okay. You are taking order of 1 time. Maybe you find the element at the root itself. Maybe I'm searching for 8 and I find the element at the root itself. Okay, so you both are right, Mukesh and Dream, you both are right actually. That is order of 1. And what is the complexity to insert one element? When we insert the element, so okay, actually this will be again that will be order of 1 for best case. Let me make it average case because this is going to be order of 1. Maybe you're inserting at the root node itself and deleting from the root node itself. That will be order of 1 if you're inserting at root node and deleting at root node. But let me write it average case. So for average case, searching an element will take log n time, insertion will also take log n time, and deletion will also take log n time. This question is important. This is GATE question and interview question also. This question you people need to tell me. After that, I will tell you this and these two. Okay. You please tell me this thing. What is the worst case? Worst case complexity to search an element in binary search tree. In binary search tree, we every time we are actually the maximum element we are searching is that depend upon the height of the tree. Height of the tree. Okay. For example, if I'm searching for 7, then I will compare 7 with 8. Then I will compare with 7 with 3, then 7 with 6, and then 7 with 7. So you can see that I compared how many times? 1, 2, 3, and 4. And that is 4 is the height of this tree. 1, actually, if we are counting the level, okay, 4. So that we can say, okay, that depend height or level. Asymptotically, both are same. Asymptotically, both are same. So level is height plus 1. Okay. So how many comparisons I make? That number of levels, that depend number of levels. So I make 4 comparison: 1, 2, 3, 4. Or you can say that, okay, one more than height, one more than height. So that depend upon height or level, you can say. Okay, height or level. More accurately, you can say, okay, height, level. Otherwise, asymptotically, approximately, that is number of, that depend upon the height of the tree. This much number of comparisons you are making. Again, I'm asking the same question. Again, I'm asking the same question, and that is the most important question actually. What is the search time for an element in worst case in binary search tree? What is the search time for an element in binary search tree? So if we depend upon the height, actually the height of complete binary tree, actually is log n. Okay, that is log n. That's why we are getting log n here all around. But that is in the case of complete binary tree, or we can say almost complete binary tree, or we can say that balanced 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 binary tree. So complete binary tree is actually every child have 2 nodes. Almost complete binary tree means actually uh, maybe you don't have some child at the right hand side, but you have child at the left hand side. So like in the heap use the complete binary tree, heap data structure. Balanced binary tree, there can be the difference of height 1, maximum height 1, between one level and another level. Okay, there can be more, there cannot be more difference between the left subtree and right subtree more than 1. There cannot be difference of height between left subtree and right subtree of more than 1 in balanced binary tree. Again, same question I'm asking, which is another very important question from company point of view and from GATE point of view. What is the worst case of searching an element in the binary search tree? So let me give the answer. We already get the answer also. Ravi says that that is order of n, and Ravi is right. And but right now I'm saying that that depend upon the height of the tree, and height I'm telling is for complete binary tree or almost complete binary tree is log n. Then why Ravish is saying that still the complexity is n? Because your tree can be actually skewed like left skewed. Your tree may grow like this, or your tree may grow like this. So maybe, for example, you have 10, then 20, then 30, then 40, then 50, like this. This is also binary search tree. This is also satisfying the property of binary search tree, because right side elements are greater than left side element. Everywhere you can find out. But the tree is growing in the form of right skewed tree. Okay. So if I want to search 50, then I need to go through all n nodes. Okay. So in this, the height of, again the tree, again this depend upon the height of the tree, but here the height of the tree, here the height of this type of tree will be equal to the number of nodes. That will be equal to number of nodes. H will be n. So height will be equal to approximately n. That will be approximately number of nodes. Okay, so in that case, if your tree is growing either left skewed or right skewed form, that can grow, that can happen in binary search tree, then the worst case complexity will be order of n. Okay, and insertion also in that case. Okay, if you want to insert one element, you need to come all the way here. You need to insert here. Maybe you want to delete one element, you need to come again all the way here. Again, that will be order of n. Okay, so these are the important point, and from this point I think we have questions also. So let's try this question. Can you people please try this question, GATE 2015 question? So ultimately, these type of questions you need to try in the exam. So please try it yourself first. So B is the right answer. That's right. Okay, let's move on. So let's see how to find out the predecessor and successor of a binary search tree. Actually, that is required if we want to delete one element from binary search tree. So while deleting one element, okay, let's talk about first deletion itself. So there can be case that, okay, you want to delete the leaf. If you want to delete the leaf, you can directly delete that. You do not need to do anything. Just simply delete from let's suppose from this node. Simply mark it nil at the left side. Mark it nil. That's it. If the node is the leaf node, if the node is the leaf node, directly delete that. But if node is non-leaf node and that is having one child, for example, we are checking out, okay, deletion in the binary search tree. So if somebody asks you delete 4, I can directly delete that. Okay, simply in the node, in this node I'm talking about, you can mark null here. That's it. This node will be deleted. That's it. But if we want to delete non-leaf node which is having one child, for example, I want to delete 14. Okay, if I want to delete 14, then what I will do? So for the I want to delete, okay, I want to delete here 14, okay, which is having one child. Then what I will do here? So I simply attach this node with this node. That's it. At the same place, at the right place, I will attach to the, actually I will attach the, you can say that, okay, I have only child, I have one child only. I will simply attach that node with the grandparent. That's it. Okay, so let's suppose 10 is this. So earlier 14 was attached here, 14 node was attached here. So address of 14, let's suppose 2000 was here. And first what I will do, I will see the address of this 13. Let's suppose the 13 address is 1000. So I will replace it with 1000. That's it. This will be deleted. That's it. Now this will start pointing to this node. Very easy. Okay, deleting of a node which is having one child, Okay. Okay, and now deleting of a node which is having two child. Now for example, I want to delete 8 itself. So to delete 8, I cannot replace 8 with 3 and 10. 3 or 10 I cannot replace. Actually, if I will replace with 3, then this will violate the binary search tree property. If I replace with 3, then you can see here the left side elements like 6 and 7 are greater than 3. Okay, and if I replace 8 with 10, then you can see here if I replace it with 10, actually in that case also, let's suppose maybe I have one more node here. Let's suppose 12. No, sorry, 12 cannot be here. That should be smaller than 10. 9 is here. So if I'm replacing it with 10, then the smaller elements are to the right hand side. Smaller element to the right hand side of 10. That is not allowed in binary search tree. So one thing is that is not that much easy to replace the immediate child with that node. If we have two child, if I want to delete a node with two child, then we cannot replace immediately with the children. Here that was possible. Here directly we are deleting. But what we will do here, we will find out the predecessor or successor. We can replace the 8 with predecessor or successor of 8. So what will be the predecessor here? Predecessor means in its left subtree, the rightmost element. The rightmost element in the left subtree. So this is the left subtree here, and the rightmost element, just move to the right, and you will find out the predecessor. So 7 is the predecessor. I can replace it with 7. I can delete this, I can replace it with 7. Okay, or you can replace it with successor. What is successor? In the right subtree, the leftmost element. Okay, so in the left subtree, actually in this case, actually 10 is the uh, 10 is the 10. We need to replace it with 10 actually, because if you will go in the right subtree, you are going to the left, but you are not finding anything. So you will replace it with 10. Now you are not going to the right. Okay, you are going to the left. So if 9 is here, then I will replace it with 9. If 9 is here, I will replace it with 9. Okay, in the right subtree, I'm going to the left. Okay, top left, rightmost left. Okay, leftmost left. Okay, so let's check out it in more detailed way. So we need to find out pre-order and post-order. One thing is sure. Pre-order, we need to find out predecessor or successor. To replace the children, replace to delete the node, to replace the node which we want to delete, which is having two children. Okay, we need to find out its predecessor or successor. Okay, so this is what we are going to find out here. The same thing we were finding out here. So one thing is clear. This is the predecessor of 8. This is the successor of 8. And if somebody asks that, okay, I want to delete 3, so what will be the predecessor? So in the left subtree, there is one node only, that will be the predecessor. And what will be the successor? The rightmost element here, 7, will be the successor actually. What will be the successor here? In the right subtree, find out the leftmost element, which will be the 4. So 4 is the successor. For 3, 4 is the successor, 1 is the predecessor. For any element we can find out. Let's try for one last more element. I'm not going to write the code here. So maybe I don't know. So you can add some more nodes here. So maybe for in this part, if we want to delete 10, then predecessor will be 9 and successor will be in the right subtree, leftmost node, which is 13. 13 is the predecessor here. So okay, we need to, so important point here is that, let me recap these important points. If you want to delete the leaf node, directly delete that. Nobody is going to bother about that. If you want to delete a node, non-leaf node, which is having one child, simply replace, let's suppose this is the one child, this is having one child, right child only. Simply, I want to delete this, so simply point out this to this. That's it. Okay. Okay. And if we have two child, then we need to find out predecessor or successor. Okay. We need to find out predecessor or successor. Replace that node with predecessor or successor. Okay, and finding out the predecessor and successor, actually that take actually order of h time. H is the height of the tree. So deletion of the element in average case, that take actually order of h time, or that take order of h time actually. Okay, deletion of an element, insertion of an element, that take order of h time. Finding predecessor and successor in worst case, that also take order of h time. Order of h time. H is the height of the tree. That's it from my side actually. So now it's your turn to solve these questions. You have enough information with you now to solve the gate questions. You have enough information. Please solve this gate 2015 questions. So what are the worst case complexity for insertion and deletion of elements in binary search tree? Please keep answering the questions. I will keep changing them now. You have enough information with you to answer these questions. If you have any doubt, you can write in the chat box. Otherwise, you can try these questions. So we get B answer from here. You said that in worst case, that will take order of n time. And that is right. That will take order of n time. Please try this GATE 2004 question. Keep trying. Ultimately, you need to solve this question if you are preparing for the GATE exam. I'm not telling you that, okay, I'm covering all the questions. That is not possible actually in one session to cover all the questions.
what I'm trying to cover in one session is I'm covering the important points about the topic. All the important points I'm covering, and from that important point is enough to solve these questions which I'm sharing with you. Sometimes these questions also give you some extra information, and sometimes these check you, okay, whatever you have studied, you know that thing or not, okay. But still, one thing is sure, I don't want to lie you people. You need after, even after this, you need to practice more questions. But one thing is sure, now you know about the topic and you have already solved many questions. Now you need to practice, that's it. Okay, you need to practice, you need to go and practice. That's it, that is required. But if you are solving these questions, means you are, yeah, these are not my questions, okay, you are solving gate level question itself. Please answer this one. Actually, they are providing the definition of the height, because some books says that some books count the height of the tree starting from 1, and some books actually count the height starting from 0. Okay, that's why many questions you will find out that they will provide the definition of the height itself. Okay, so here also they provide the definition of the height. Corman book provide this definition starting from 0. Corman is the Bible for data structure and algorithm actually. So that's why I'm considering this one. And you can remember this. If height is starting from 0, level is starting from 1. How you can remember? How I remember is, I just think that, okay, if I'm going to enter into a building, so the floor in the first floor is the ground floor, having which is having height 0, and then height 1. First floor is having height 1, second floor is having height 2. So height always start with 0, but level can start with 1. Level can start with 1, but height always start with 0. If we are trying to enter into a building, so initially the height will be 0, then height 1. This way you can remember this thing. Some books also write height starting on 1. So that's why they maximum time they mention the height definition in the question itself. But this is the one of the this is taken in the Corman book, which is the one of the most important book for DSA. So we will consider this thing only. Answer from you people for this question. The following numbers are inserted in empty binary search tree in the given order. What is the height of binary search tree? They're asking about the height of binary search tree, and they give the definition also. So is this B is the new B? Don't know. Yes, I think you have already given the answer, you people. So B is the right answer here. You can try it yourself. I'm not going to try it. Let's move to next question. Can you try this GATE 2005 question? Some numbers in the sequence 1, 2, 3 up to n are inserted in binary search tree in some order. The resulting tree, the right subtree of the root contains p nodes. The right subtree of root, let's suppose this is the root, and the right subtree here contains p nodes. The first number to be inserted in the tree must be, so what should be the number we have to insert here at the root? I think there that is asking. So the number 1 to n are inserted in binary search tree in some order. In the resulting tree, the right subtree root, okay, right subtree root contains a right subtree of root contains p node. So this is having p nodes here. Yes. What will be the first number to be inserted in the tree? What will be the first number that is talking about? What should be that number? So Varun says C, Dream says C. So let's check out the answer first. And C is the right answer here, n minus p. So we know one thing that, okay, the elements here, these p nodes actually will be greater than this number. One thing is sure. and the nodes are actually in the sequence 1 to n. The one node is having value 1, another node is having value 2, 3, 4 up to n. Okay, and p nodes actually is having are at this side. So this side actually, so if let's suppose we have n value 10, and here p is actually, let's suppose, 6, then these 6 elements should be like mm, these 6 elements should be like 10, 9, 8, 7, 6, 5. These 6 elements should be this. If n value is p value is 6, if p nodes are there, let's suppose 6 nodes are there, and these should be this. Okay, and that is asking about the what is the value here, what will be the value here. So you people are saying that should be n minus p, so that should be 10 minus 6, that should be 4. Yes, that should be 4 here, because this should be 4. Then only the elements here, according to this example, will be from 5 to 10, and the elements here will be from 1 to 3, and this element must be smaller, this element must be greater. So the value of this root node must be n minus p, and you people are right. C is the right answer. And this is for your homework, or you can try it here also if you want. So let's you can try it at home, and I'm not sharing the solution for this problem. This is also the nice problem. So they provide us actually, suppose we have a binary search tree with 1000 distinct elements, 1000 distinct elements we have, and that is a complete binary tree. We have a complete binary tree. Okay, means we have 2 children for every node. We have 2 children. The tree is stored in the array representation of binary heap tree. Assume that array index start with 0. The third largest element in the tree stored at which index? The third largest element, can you tell me, is stored at which index? So this is the tree with 1000 distinct elements, and you have to find out the third largest element that will stored at which index. That's it for this session. Thank you everyone for keep joining and staying with me. And this is about our GATE series, GATE test series. If you are appearing for the GATE exam and if you want to appear for GATE test series at very low prices, you can find out the GeeksforGeeks GATE test series actually, and which is having so many features. You can check out. All the detail is given in the description also, and you can check out for this GATE test series. And you can enroll for, if you are preparing for GATE 2024, then again you can check out our complete course. Or if you are looking for some free course, then we are providing this GATE crash course, which is completely free, and you can find out the detail of this complete GATE crash course in the description. And if you are preparing for GATE 2024 and you want completely everything free, then again you can check out our YouTube channel. On YouTube, our GATE YouTube channel, actually you will find out lots of videos for almost the videos for every subject. Okay, but if you want to get the material in well-mannered way, and all the recorded sessions with very best quality, then for that you need to pay something, little bit amount. Otherwise, many material is free on our YouTube channel, and you can check out this test series. Thank you everyone. So I'm ending this session now. Thank you once again for keep joining. Bye bye. Take care. Good night.
Hello everyone, my name is Puneet Kansal. I am mentor at GeeksforGeeks. This is actually, we are continuing with the series of GATE crash course, which is offered by GeeksforGeeks. In this session, we will discuss about the graph. Graph is one of the most important topic in data structure and algorithm. So this is not only important from GATE point of view, but if you are preparing for DSA, from that point of view also, graph is very important. So in this class, we will cover start from very basics in graph, and we will go to the GATE level, and everything will be clear in graph actually. And so let me share my screen, and let's start with the graph today. This session is the part of the actually GATE crash course, and in GATE crash course is actually we are covering the 5 most important topic from every subject. So this is the 5th topic actually we are covering from programming and data structure. We already covered the trees and array pointers and stack queue. These important topics we have already covered. So you can check out their video that is available on our channel. And so if you are preparing for the GATE exam, then definitely this series will help you. If you are completely new to the GATE, then this GATE crash course series actually, which is free of cost, you can check out the detail in the description. You will find out this series very helpful for you. Means at least you will be able to clear the GATE exam. And if you are already seriously preparing already, you're preparing already for the GATE exam, then you can use this series for revising the most important topics. Okay, so let me tell you people, you do not need any prerequisite for this session. We will start from basics and go to the GATE level. Even you are not preparing for GATE, it's okay. This is one of the most important topic in DSA graph. All the concepts related to graph will be clear to you. We will discuss very, very important points about the graph. So, okay, let me start now. Let's start discussing about the graph. In graph, we will, as I have told you, we will start from the introduction to graph, and we'll see the differences between graph and tree. We'll see, okay, BFS and DFS, traversal of the graph, and then we will apply various last year, previous year GATE questions we will solve actually. So let's start from the basic introduction to graph. So very basic, I'm starting, and we will go to the GATE level. You people will solve the GATE questions yourself. I will just provide you the information and you will be able to solve the GATE question. That's it. So here's the definition of graph. Graph is composed of set of vertices V, represented with V, denoted with V, and set of edges denoted with E. Okay, so graph is actually denoted by G in bracket E comma V. E is the set of edges, and V is the set of vertices. That's it. And G is the name of the graph. That's it. So this is how we denote the graph. And this is the definition. Means graph is just made up of vertices and edges. That's it. So there are various type of graph. For example, there is a null graph. So let's make this session more interactive and more beneficial for you people. So for that, you need to reply to the questions before I tell you something. Okay, I can ask you some good questions actually, like what do you think? What is a null graph? Anything you know about the null graph? What is a null graph? Like, let me give you one example. For example, let me write. In null graph, there is no edges. Okay, that is confirmed. There is no edges. The graph which don't have any edge, that is a null graph. This is right. Okay, one more thing I'm adding in this. That have edges, that have vertices, but no edges. That have vertices but no edges is a null graph. Okay, so GATE aspirants say that no edges in null graph. Here there is no edges. Yes, there is no edges. Now the point is here, do we have the vertices or not? Means, for example, this is a null graph or not? So I have here, let's suppose four vertices. This is one vertex, this is another, this is another. So these are 4 vertices. So this is a null graph. Okay, we know this thing because we have already mentioned we don't have any edge. If a graph don't have any edge, then that is a null graph. Okay, fine. What about this one? So just to cover about, okay, in here, um, I have one vertex. So this is also null graph. I have one vertex. I have one vertex. Okay, one last question I want to ask from here. So I am removing, I'm erasing this one vertex also. Is this is a null graph or not? Means, is this is a null graph or not? This is a null graph or no? Null graph or not? Means no vertices, no edges. Null graph or not? Yes or no? Yes or no? Please reply. Just think over and just give your guess. Okay. Right and wrong answers are allowed here because even you are giving wrong answer, learning is happening. That's it. So we get one answer no. Okay. Actually, Himanshu say okay. Answers must be there, wrong or right will not matter. Okay, because the moment you will type the answer, learning will happen, and that's why we are here. We are here for learning only, for learning the concepts. So this is a null graph. This is also a null graph. This is also a null graph. Okay, this is so. What should be the definition of null graph? Let me write the definition once again. Let me write once again. Okay, erase everything. Let me write the definition of null graph. So there should not be edges. That is confirmed. There should not be even a single edge. That is confirmed. Plus, there may or may not. There may or may not vertices. That says this is the definition of the null graph. Vertex can be there. Vertex cannot be there. It's okay. If vertex is there and vertex is not there, but edges should not be there. That is confirmed. Okay. So even I don't have any vertex, I don't have any edge, that is still a null graph. That is still a null graph. Okay. Okay. So these are actually I'm covering this point so that you can, if somebody want to trick you in interview, you can trick them. Okay. Okay. So what is connected graph? Connected graph. So in which connected graph are those graph in which every vertex is connected directly or indirectly with each other. So this is a connected graph. This is also connected. This is still connected, still connected, still connected, still connected, still connected. Now this is disconnected graph. So this graph, this is one graph. This is one graph. This graph has two components. One is this component. This is known as the component of the graph. This is one component. This is another component. This is a, if you're talking about this single one, this is a connected graph. Okay, but if you are talking that, okay, this complete one, this complete one, this is disconnected graph. This is disconnected graph. Means this component is not connected with another component with any edge anywhere. Okay. Okay, so we know about the connected graph. We know about disconnected graph also. What is complete graph? Okay, let me erase this and okay, let me erase it. So what is complete graph? In complete graph, there is a direct edge. Let me write even direct edge between every vertex. That's it. So this is a complete graph. Yes, this is complete graph. What about this one? This is also complete. What about this one? What about this one? Yes, this is also complete. Every vertex is directly connected with every other vertex. Every vertex is connected directly with every other vertex. That is complete graph. So here this is connected with this with direct edge. Direct edge. Every vertex I'm talking about. You can check out here also. This vertex is connected with all other n minus 1 vertices directly they are connected. This is also connected directly. They are only two vertices, they are connected directly with each other. These are complete graph, we know about them. Okay, what about dense graph? In dense graph we have this is the definition. Very easy, very easy. More edges, and less vertices. If in a graph we have more edges, less vertices, that is known as dense graph. That's it. Let me draw it. So maybe this is a dense graph. This is itself a dense graph, and even this is also dense graph. Here number of edges are 1 2 3 4 5 6 7. 7 number of edges are there. Vertices are how much? 5. Okay, vertices are 5. Okay, so edges are more. So this graph is a dense graph. This graph is a dense graph. Otherwise there is no such thing that okay, you are comparing these two things. You just see that okay, number of edges are more as compared to vertices. Just you simply say that okay, this is a dense graph. That's it. So otherwise you can check, okay, number of edges are more, number of vertices are less. So this is a dense graph. More edges, less vertices, dense graph. And reverse of this is what? Sparse graph. More vertices and less edges. So maybe okay, I can call this. So this is a sparse graph. This is a sparse graph. How many edges? 1, 2, 3, 4. 4 edges are here. How many vertices? 1, 2, 3, 4, 5. 5 vertices. Vertices are more, edges are less. So this must be a sparse graph. Okay. So now I have a question for you people. I have a question for you. Can you tell me? Okay. We know about the complete graph. This is one complete graph. Okay, complete graph is a dense graph. What about the, can you give me okay, let me ask another question. So you say yes or no. Okay, you people say yes or no. Null graph or sparse graph? Null graph or sparse graph? Yes or no? Null graph or sparse graph? We know about null graph. Null graph is in which no edge at all, but vertices may or may not be there. May or may not. Okay. So GATE aspirants say yes. Himanshu say yes. You all people please reply. Okay. Then you will enjoy more this session. So dense. So this is one example actually. Complete graph is one example of dense graph. But make sure not every dense graph is a complete graph. Not every dense graph is a complete graph. For example, this is a dense graph, but this is not complete graph, because from this vertex there is no direct edge to this vertex and this vertex. So this is the dense graph, but this is not the complete graph. So I'm making a statement now. All the complete graph are dense graph. Yes. All complete graph are dense graph. Yes. But not every dense graph is a complete graph. But no, not every dense graph is a complete graph. Okay. So this is one statement. Let me make another statement now. So another statement is null graph is a sparse graph. Yes. Null graph is a sparse graph. Yes. Now, all these sparse graph is a null graph. This statement is right or wrong? Yes or no? Yes or no? Every sparse graph is a null graph. Every sparse graph is a null graph. This is right or wrong? Every sparse graph is a null graph. Yes or no? Every sparse graph. Manish say wrong, and that is wrong. Himanshu say wrong. Yes. No. Havya say no. Okay, no. I get explanation. No. You people are right actually. Not every sparse graph is a complete graph. This is also a sparse graph. This is also a sparse graph, but this is not the null graph, because null graph don't have the edges, even a single edge. There is no edge. So these are the different type of graph we have studied now. Let's move on. We are covering the basics. We are building our basics. If base are strong, then I will take the GATE questions. You people will solve the GATE question yourself. Okay, so let's move on the next topic, that is tree and graph. Difference between tree and graph, that is very important actually. From interview point of view, must. Difference between tree and graph. Tree always undirected. Tree always undirected, and that is wrong. That is wrong. Tree are always directed. So that is reverse is right actually. Tree are always directed. Graph may or may not be directed. Graph may be directed or may be undirected. Graph can be of both type. Okay. But tree are always directed. Even you don't mention, even I am drawing a tree here. You say, sir, you do not mention the direction here. If I don't mention the direction, we will assume that they have, this is equivalent to this actually. See, I don't mention any direction here on the edges, but still this is same as this one. We always assume that there is a direction from root to the children, root to the children. There is a path from root to the children. Otherwise, how we will access the children's? Otherwise, how we will access the children? If somebody make this tree, then we will assume that we can access it, and we access that. In lots of problem, you will see that they will not tell you, okay, there is a path from root to the children. They simply give you the root of the tree, and they will start asking the question. And you cannot ask them what is the direction. You cannot ask them, because by default the direction is, even they don't mention, is this. So that's why tree are always directed. Tree are always directed. Graph may or may not be directed. Okay, so graph may or may not. Okay, tree are actually subset of graph. Okay, means tree are actually also graph. Tree are also graph, but graph is may or may not be tree. Graph may or may not be tree, but tree are always a graph. Tree are always a graph. This is also a graph. This tree is also a graph, but a graph may or may not be a tree. Okay, so you are saying that tree are hierarchical and graph is not hierarchical. But I say that this is a graph. You are calling it tree. I am calling it graph, and we both are right, because tree are subset of graph. So I can say graph is also hierarchical. Okay, so let's move to the next point. Manish says something. That's the very nice point actually I was looking for. A cycle can be formed in graph. Yes, Manish, you are right actually. I was looking for this point. Graph may or may not have cycle. Again, may or may not. Okay, because graph can be tree. A tree is also a graph. Okay, so I need to use the word may or may not. So graph may or may not have the cycle, but one thing is sure. One thing is sure. What is that? Tree will not be having any cycle. Tree will not be having any cycle. Okay, it's not bicycle. It's the cycle. Means from one node I am coming back to same node again. I start from 1, then move to 2, then 3, then 4, come back to 1 again. So this is a cycle here. So this cannot be a tree. This is a graph. Graph may or may not have cycle, but tree, that's sure, don't have cycle. That's very important point actually. Varun already shared this thing. Okay, so we get so many points now. Let me summarize the differences. So let's see the differences. So a tree, first point is that tree is a graph, yes, but graph may or may not be a tree. Graph may or may not be a tree, but every tree is a graph, yes. Second point, graph can have, this is very important. This is very important actually. I will cover it later on. So third point, graph can be directed or undirected, yes, but every tree is directed. Every tree is directed. We assume that there's a direction from root to the children. This point is, fourth point is already shared by you people. A cycle can be formed in graph, not in glass, no, in graph actually. Okay, so a cycle can be formed in graph. So there may be cycle, there may not be, but there is no cycle. We are dead sure there is no cycle in the tree. Okay, so this is the application. of graph, like finding single shortest path, maybe finding the shortest path in networking graph. And application of tree is gaming tree, decision tree. So these are the various tree we can use actually. Maybe B tree, binary search tree are also applications of tree. Okay. Okay, and what about this important point? Let me hide this and ask you a question. Let me hide this and this information. Now let me ask you a question. So what is the how, every tree have maximum how many number of edges? So the question is, a tree, let's suppose a tree have v vertices. Let's suppose a tree have v vertices, v number of vertices, v number of vertices. How many edges? Maximum number I'm talking about. Max number of edges a tree can have, which is have v vertices. I'm asking about the edges, and I'm providing you the vertices, that is v. So in the context of v, how can you relate number of edges with v somehow? In the case of tree, can you reply please? Anyone, any idea? This is one of the most important point here on this slide. So number of vertices are v. How many edges will be there? Maximum I'm talking about. Maximum. Or you can reply for minimum also. If you know about the minimum, write min this much, max this much. And if you know about both of them, then you can write both of them. Some people may be rewinding the video itself, this video itself. Maybe they are checking this hidden solution. That's not fair. So I'm waiting for you people. Anyone? Okay. So this is for the tree actually. This question is for tree. So maybe someone is writing, I don't know. So another question can be, let me tell you the another question, then I will come give the answer to this one. So another question can be, what is the, if we have v number of vertices, if vertices are v, then how many edges will be there? How many edges will be there? Now in the case of, how many maximum edges will be there? How many minimum edges will be there in the case of graph? In the case of graph. So we get the answer for actually tree. In tree, GATE aspirants say that that is v minus 1. And you are right. You are right. V minus 1. Maximum and minimum both are actually same. Every tree have v minus 1 edges only. Every tree have v minus 1 edges. You can make any tree. You can make any tree and you can check out. See? So if we have one vertex, we have 0, v minus 1 edge means 0 edge. If we have two vertex, we have 1 edge. If we have three vertex, we have 2 edges. Let me add one more vertex. We have three edges here. How many vertices are there? 1, 2, 3, 4. You can add any number of. So this is another tree. Number of edges 1, 2, 3, 4. And edges, vertices 1, 2, 3, 4, 5. So v minus 1. Every tree is having v minus 1 number of edges. That is sure. Minimum or maximum both. Every tree have fixed v minus 1 number of edges. That's sure. Okay. So that is clear to us. So let me erase this answer now. Now we are talking about the graph. So we get one more answer from GATE aspirant. Let's check out that. So in graph, max v number of edges as cycle can be formed. So first of all, let's talk about the minimum number of edges in graph. So see, null graph is also a graph. Null graph is a graph or not? Null graph is also a graph. Null graph is also a graph. that don't have any edge. So minimum number of edges can be, minimum number of edges can be 0. I don't know. I have 100 vertex. I have 1000 vertex. I have 1 lakh vertex. This doesn't matter if I have null graph. In null graph is also a graph. Okay. So I'm talking in the context of, if you can give me any example with anything. So minimum number of edges can be 0, for example, in null graph. And what can be the maximum number of edges? So maximum number of edges, actually, this is very important. Maximum number of edges can be actually in the complete graph. Maximum number of edges can be actually in the complete graph. Okay. So if we have a complete graph, for example, this is a complete graph. Let me erase everything and make some space and then write. So we know that maximum number of edges in a graph can be that will be a graph of type complete graph. That be a graph of type complete graph. Okay. And so this is a complete graph. This is also a complete graph. This is also a complete graph. So all these are complete graph. Okay, this is having 2 vertices, this is having 3, this is have 4. So we get one answer also from Varun. Varun says that maximum number of edges will be n into n minus 1 divided by 2. So that is right actually. How he is getting that? Let's check out. How he is getting this solution. Let's check out. Very easy actually. See, we know that maximum number of edges will be in complete graph. This is an incomplete graph. For example, taking this example, from one vertex there is a direct edge to every other vertex. Okay, so iske andar, okay, in this actually, so from, if we have number of vertices, we have 4. Okay, so there will be a direct edge, from one vertex to every other vertex. Okay, this is the property of complete graph. From every vertex there is a direct edge to every other vertex. Okay, so number of, let me write here, number of vertices are v, and every vertex, for one vertex, let me write, for one vertex is actually contributing how many edges here? 3. One vertex is contributing 3 edges. Okay, number of vertices are 4. Okay, so how many 4 vertices will contribute? 4 vertices will contribute 3 into 4, 12 actually. Every vertex is contributing 3 edges, because for every vertex we have 3 edges. Okay, and for 4 vertices that there should be 3 into 4, but Varun is dividing it with 2. Varun says that please divide it with 2, because you are counting every edge 2 times. One for this vertex, one for this vertex. Like this edge, if I'm talking about, I'm counting this edge, one for this vertex, one for this vertex. You're counting every edge 2 times. So please divide this number by 2. So we get number of edges 6 here, and here we have 6 edges. You can see 1, 2, 3, 4, 5, 6. So let's check out his formula, how this formula is working. Simple actually. We have n number of vertices. Every vertex is contributing how many edges? N minus 1 edges, because there is a direct edge to every other vertex. Total number of vertices are n, and we are going to n minus 1 vertices. So total edges will be n into n minus 1. Why dividing with 2? Because every edge is contributed, every edge is counted 2 times. One from one vertex, one is from other vertex. क्योंकि ये एक आपकी एक एज 2 वर्टेक्स से अटैच है ना, तो सिंपल है, वो यहाँ इससे यहाँ से भी आप काउंट कर ले रहे हो, उसको यहाँ से भी काउंट कर ले रहे हो. ओके, दो जगह से थोड़ी काउंट कर पाओगे एक चीज को. अब ये बॉडी बोल सकते हो ये स्टेयर से यहाँ से ऊपर, नीचे से ऊपर जा रही है, तो आप ये स्टेयर नीचे से ऊपर जा रही है, यही स्टेयर ऊपर से नीचे जा रही है, तो ये 2 स्टेयर थोड़ी हो गई है, स्टेयर तो एक ही है ना. आप यहाँ से भी काउंट कर रहे हो, यहाँ से भी काउंट कर रहे हो. ओके, ऐसे ही यहाँ पे करना है अपने को. एक एज को एक ही बार काउंट करो ना, 2 बार क्यों कर रहे हो. और टोटल कितनी होंगी? n into n minus 1, क्योंकि एक वर्टेक्स n minus 1 से अटैच है, तो n वर्टेक्स n into n minus 1 से अटैच होगा. इतनी एजेस होंगी टोटल, उसको डिवाइड बाय 2 कर दिया, तो टोटल कितना आ गया? n into n minus 1 divided by 2. That's it. And you are right, Varun. So these are the differences, important differences between tree and graph. If any doubt, please keep writing. Keep asking the question. That is very important. If you will ask the question, then that will help other people also actually. So I think GATE aspirant is trying to ask something. So if you have any doubt, you people can ask. Don't take any doubt with you from here. You should not take. Okay. So you can type the doubt here. Meanwhile, I'm moving to next slide. So let's see now how to represent the graph in computer. अभी अपने को ये तो पता है ये ग्राफ है. Is there anyone who is not feeling comfortable in Hindi? I can totally use in English now. Okay, so ये तो अपने को पता है ये ग्राफ है. ये तो मैंने हाथ से ड्रॉ कर दिया इसको. पर ये कंप्यूटर में कैसे स्टोर होगा? कंप्यूटर में कैसे स्टोर करेंगे इसको ग्राफ को? How to represent the graph in computer? So there are two methods. One is adjacency matrix. Another one is adjacency list. So let's talk about the adjacency matrix first. How we store the graph in computer. So we store the graph in the form of 2D matrix. That's it. We store the graph in the form of 2D matrix. तो अभी इस ग्राफ को अपने को स्टोर करना है. कैसे करोगे? सिंपल है. कितने वर्टेक्स है यहाँ पे? 4 वर्टेक्स है. 0 1 2 3. सो 4x4 की एक मैट्रिक्स बना लो. 2D एरे ले लो 4x4 का. ओके. और अगर 0 से 1 के बीच में एज है तो 1 मार्क कर दो. नहीं है तो 0 मार्क कर दो. दैट्स इट. तो देखो 0 से 1 के बीच में 0 से 1 के बीच में एज थी तो हमने 1 मार्क कर दिया. देखो 1 से 3 के बीच में नहीं है. 1 से 3 के बीच में नहीं है ना, एज तो नहीं है यहाँ पर, तो हमने 0 मार्क कर दिया. बस सभी जगह ऐसे ही करना है. टोटल मैट्रिक्स ऐसे ही बना डालो. तो 2 से एक और एग्जांपल लेते हैं. 2 से 1 के बीच में एज है हमारे पास, ये वाली एज है ना, तो 1 मार्क कर दिया. और देखो 0 से 3 के बीच में कोई एज नहीं है तो 0 से, मैं इसको इरेज कर लेता हूँ थोड़ा सा. 0 से 3 के बीच में नहीं है ना, तो देख लो 0 से 3 के बीच में 0 लिखा है हमने. और 3 से 0 के बीच में भी 0 मिलेगा आपको. वही बात है, यहाँ से जो रास्ता यहाँ पे जा रहा है वही यहाँ से यहाँ पे भी आ रहा है. तो यहाँ से यहाँ थोड़ी रास्ता बन गया जब यहाँ से यहाँ रास्ता नहीं था. तो ओके, सो दिस इज हाउ वी रिप्रेजेंट द ग्राफ इन द फॉर्म ऑफ एडजेसेंसी मैट्रिक्स. दैट्स इट, वेरी सिंपल. ओके. और अगर यहाँ पे वेट हो गया, तो अगर ये वेटेड ग्राफ हो गया, लेट्स सपोज मैंने 5 लिख दिया यहाँ पे, इस एज का वेट, इसका 6 लिख दिया, इसका 9, इसका 10. तो यहाँ पे 1, जहां पे 1 लिखा है ना, उसका वेट लिख दो एज का. 0 से 1 के बीच में अब 5 लिखना पड़ेगा. 1 नहीं. तो अनवेटेड ग्राफ में 1 और 0 चलेगा. वेटेड ग्राफ में उसका वेट लिख देना है. तो एक और एग्जांपल ले लेता हूँ. 2 से 3 के बीच में ना 1 की बजाय ना 10 लिख दो. यहाँ पर वेट लिख दो उसका. बस ये वेटेड ग्राफ के लिए हो गया. तो in the form of matrix C, we store the graph in computer. One is in the form of matrix, one is in the form of adjacency list. What is this adjacency list? Let's check out that thing. So this is how we represent the adjacency list in the graph in the form of adjacency list. यहाँ पे देखो क्या कुछ नहीं है. यहाँ पे हमने एक लिस्ट, हमने ना एक एरे ले लेंगे हम. ये एरे हो गया हमारा, ये एरे हो गया. इस एरे का साइज कितना होगा? जितने वर्टेक्स होंगे. 1 2 3 4 वर्टेक्स हो गए. 1 2 3 4 0 1 2 3 0 1 2 3. ओके. अभी जो हमारा 0 वर्टेक्स है ना, इससे कौन कौन सी एजेस अटैच हैं? एक तो 0 से 1 पे जा रही है, एक 0 से 2 पे जा रही है. तो 0 से 1 पे, 0 से 2 पे, तो एक लिस्ट, ये लिस्ट क्रिएट हो जाएगी. मैं एक और अटैच कर देता हूँ यहाँ पे 0 से 4 पे. तो एक और आप यहाँ पे अटैच कर दोगे 0 से 4 पे. एक और कर देते हैं 0 से 5 पे. तो यहाँ पे लिस्ट ये बड़ी होती चली जाएगी. ठीक है. तो ऐसी सभी वर्टेक्स का हमें एडजेसेंट वर्टेक्स जो है उनकी लिस्ट बनाते जाना है. ओके. सो इंपॉर्टेंट पॉइंट हियर इज दैट इज वेरी सिंपल एक्चुअली. फॉर एवरी वर्टेक्स, check out its adjacent vertex and make the list of that. That's it. So for example, the adjacent of 2 is 0 1 and 3. Adjacent means who are immediately connected with this, directly connected with 2. So directly connected with 2 is 0 1 and 3. 0, 1, and 3 are directly connected with 2. So make the list of them. That's it. And the address of that list we can store in one array actually. So this is having the starting address of this location is having the starting address of this list. This location is having the starting address of this list. This location is having starting address of this list. And we will, if I want to store some more element, like I want to attach one more node here, let's suppose 4. So this list will grow. That's it. And if I want to delete, then delete from here. That's it. Okay, so this is how we store the graph in the form of adjacency list. Okay, so this is in the form of adjacency matrix. Okay, so now I'm going to ask you some good questions based upon adjacency matrix and adjacency list. Let me ruin your life. So these are some of the questions in the case, in the context of the complexity. So you need to tell me, okay, so you know about now adjacency matrix and adjacency list. So can you tell me, let's talk about adjacency matrix first. Can you tell me, I want to add a new edge. I want to add a new edge here. Let's suppose this edge I want to add. So how much time that will take to add a new edge in adjacency matrix? How much time complexity can you mention? It's new year. Let me ruin your starting days of the year. So we get one answer. Anyone else? So GATE aspirants say that in constant time, sir, you can ruin our life. How? How in constant time we can add this edge actually? Simple. What I need to do, I need to make one modification in this matrix, one modification only. Himanshu also say order of 1. So from 0 to 3, 0 to 3, earlier there was 0, I will make it 1. And one more modification actually, from 3 to 0, 0 was there, I make it to 1 because ये जो सीढ़ियाँ यहाँ से यहाँ जा रही है ना, वो वही सीढ़ियाँ यहाँ से यहाँ पे भी आ रही है ना, तो जो ये एज यहाँ से यहाँ जा रही है वो यहीं से यहाँ यहाँ भी आ रही है, तो ये दो जगह पे आपको मॉडिफिकेशन करना पड़ेगा. और एरे के अंदर टू एक्सेस द एरे, टू एक्सेस वन लोकेशन ऑफ द एरे, to access one location of the array, either that is 1D array, either that is 2D array, either that is ND array, any D array, that will take constant time. That will take constant time to access one element inside any type of array. Okay, so यहाँ तो हम दो ही element access कर रहे हैं, तो 2 time लगेगा. 2 is a constant, so you people are right. That will take constant time. Yes. What about the adjacency list? If I want to add a new edge here, what I need to do? See, what I need to do, from 0, I need to add 3 here because 3 become the adjacent of 0. And in 3 list also, I need to add 0. So these two things I need to add. How much time this will take? Can you tell me how much time this will take? We are talking in the context of worst case. We are talking in the context of worst case. So we get one answer from GATE aspirant. He's saying that order of n for traversing, that is order of n. If you need to traverse, he is traversing till here actually. Any other answer? Okay. But what I can do is I can add the element here in the starting itself. Why not? Why not in the starting of the list? Why I'm adding in the end? I can add the element in the starting itself. I can add the element in the starting. And how much time this take to add the element in the starting of a linked list? How much time this take to add the element in the starting of the linked list? Why I have to add it at the end? Cannot I add in the starting? Yes, I can add in the starting. This thing is just telling me what are the adjacent vertices of 2. So their order doesn't matter. So yes, that reduced to 1. Now. I do not need to store at the end. I can store it in the starting of the linked list. Okay. So if I'm storing in the starting, then that will take constant time. That will take Constant time. Okay, so let's talk about removing an edge. Removing an edge. I want to remove an edge. How much time? Please keep replying. How much time this will take to remove an edge? I want to remove this edge from adjacency list. How many changes I need to make? Again, 2. From 2 to 1, I will make it 0. And from 1 to 2, 1 to 2, again I will make to 0. बात कर चुके हैं ना, एरे को एक्सेस करने के लिए कांस्टेंट टाइम लगने वाला है. एक एलिमेंट को एक्सेस करोगे ना तो कांस्टेंट टाइम लगेगा. दो एलिमेंट को करोगे तो 2 into 1, 50 को कर लो, 100 को कर लो, 100 into कांस्टेंट. ओके, तो एक हम यहाँ पे क्या कर रहे हैं, एलिमेंट को एक्सेस कर रहे हो, उसको एज को रिमूव कर रहे हो आप, तो कांस्टेंट टाइम ही लगने वाला है अपने को यहाँ पर. ओके, कांस्टेंट टाइम ही लगने वाला है. दो एलिमेंट को खाली चेंज किया है. एडजेंसी लिस्ट में क्या होगा? I want to remove this edge. I want to remove this edge. I want to remove this edge. कैसे करेंगे बताओ? इसको रिमूव करेंगे ना तो 2 से 1 पे ये वाला अपने को हटाना पड़ेगा. ये अपने को नोड हटाना पड़ेगा. यहां से 2 का एडजेसेंट था ना 1, तो हटाना पड़ेगा. अब नहीं है ना, तो ऐसे ही 1 का एडजेसेंट 2 था तो ये भी हटाना पड़ेगा. ये दो नोड हटाने पड़ेंगे. इन दोनों को हटाने में, लिंक लिस्ट से इन दो नोड को हटाने में कितना टाइम लगेगा बताओ? यस, इन दिस केस ट्रैवलिंग इज रिक्वायर्ड. अभी अपने को डिलीट करना पड़ेगा ना, तो अपने को ट्रैवल करके पहुंचना पड़ेगा. आई डोंट नो वो नोड कहाँ पे है, मे बी लास्ट नोड हो सकती है. ओके, तो ट्रैवल करके अपने को वहां तक पहुंचना पड़ेगा. ओके, उस केस में अपने को क्या लग रहा है, अभी कितना टाइम लग रहा है? ऑर्डर ऑफ v टाइम, because these are vertices. Okay, so worst case में कितना टाइम लग रहा है अपने को? order of v टाइम लग रहा है अपने को. Okay, now adding a new vertex. So if I want to add a new vertex here, let's suppose 4, then actually in that case, if I'm adding a new vertex here, okay, maybe adding 1 or 2 edges also, adding a new vertex I'm talking about. Okay, adding a new vertex here 4. In this case actually two cases can happen. If I can extend this array, if this is a dynamic array, like vectors in C++, okay, or array list in Java, or list in Python, if we can extend the same array, okay, then we can easily add the vertex. We can add 0, 0 actually. Even we do not need to add anything here. Okay, we can add, okay, the distance from 4 to every other vertex. There is no edge actually. Okay, so we can say that will take actually v time. How much time? V time, because number of elements in a row is v, and number of elements in column is also v. So v plus v, that is 2v time that will take. So again that is actually v time, order of v time, 2v time take. ये उस केस में होगा जब हम डायनेमिक एरे का यूज कर रहे हैं. ठीक है, अगर डायनेमिक एरे नहीं है, लाइक सी के अंदर, अगर हम सी की बात करें, सी में डायनेमिक एरे नहीं है हमारे पास, तो अपने को इस एरे को एक नए एरे में कॉपी करना पड़ेगा, जिसका साइज कितना होगा? उस एरे का साइज होगा 0 से लेके 4 तक, 0 से लेके 4 तक, और इन सभी एलिमेंट को इधर ट्रांसफर करना पड़ेगा. सभी एलिमेंट्स को ट्रांसफर करना पड़ेगा. ओके, तो कितना टाइम लगेगा? v इंटू वी. कितने एलिमेंट्स हैं? v इंटू वी, तो v स्क्वायर टाइम लगेगा. तो दो आंसर हमने डिस्कस किए हैं, एक तो v स्क्वायर, और दूसरा जो आंसर है ऑर्डर ऑफ v. ऑर्डर ऑफ v कब लग रहा है? जब आप डायनेमिक एरे यूज कर रहे हो. और v स्क्वायर कब लग रहा है? जब आप स्टैटिक एरे यूज कर रहे हो. लाइक अगर आप सी में काम कर रहे हो तो ये कर सकते हो, अगर आप वेक्टर्स का यूज कर रहे हो तो इसमें ही काम चल जाएगा ऑर्डर ऑफ v में. ओके, एडजेंसी लिस्ट के अंदर क्या होगा? अगर हमें एक नया वर्टेक्स ऐड करना पड़ गया, तो यहाँ पे एक नया वर्टेक्स ऐड करना पड़ गया तो क्या होगा? कितना टाइम लगेगा? इसमें लगेगा अपने को कांस्टेंट टाइम. यहाँ पे खाली मेंशन करना है कि भाई एक नया एलिमेंट आ गया है, कोई इसमें कुछ नहीं ऐड करना, और यहीं पे खाली मेंशन करना है ओके कि भाई एक नया एलिमेंट आ गया, कांस्टेंट टाइम लगेगा. ठीक है, ओके. और क्वेरिंग, ओके, चलो इसको मैं वाइंड अप कर देता हूँ. क्वेरिंग डिग्री ऑफ अ नोड. व्हाट इज द डिग्री ऑफ अ नोड? डिग्री, तो मैं बोलूं तो इस वाले वर्टेक्स की डिग्री होगी 2. कितने इसके एडजेसेंट वर्टेक्स हैं? या कितनी एडजेसेंट एजेस हैं, वो उसकी डिग्री होगी। ओके, तो कोई पूछे तो डिग्री 2 की डिग्री कितनी है, 3 होगी डिग्री 2 की, और 3 की 1, 2 की 2, सॉरी 1 की 2, तो अपने को डिग्री पता है। अभी इसमें पूछ रहा है कि भाई एडजेसेंसी मैट्रिक्स में अगर पूछे कि भाई व्हाट इज द डिग्री ऑफ लेट्स सपोज 2, to find the degree of 2 you need to scan this complete row, you need to scan this complete row, how many ones will be there, how many ones will be there in this row, that will be the degree, because these ones are showing how many adjacent edges are there। okay, तो डिग्री के लिए अपने को सभी इन सभी को चेक करना पड़ेगा सभी को। तो ये कितने एलिमेंट्स हैं, ये v एलिमेंट्स हैं, तो कितना टाइम लगा, v टाइम लगा एडजेसेंसी मैट्रिक्स में। और एडजेसेंसी लिस्ट में डिग्री फाइंड आउट करना है, जैसे कि मेरे को पूछना है भैया 2 की डिग्री कितनी है, तो मेरे को ये देखना पड़ेगा इसमें कितने नोड्स हैं, कितने नोड्स हैं, तो ये मैक्सिमम नोड्स कितने हो सकते हैं, ये v हो सकते हैं। मे बी आपका ग्राफ ऐसा कुछ ऐसा हो स्टार की तरह, और आप इसकी डिग्री पूछ रहे हो, इस वाले बीच वाले नोड की डिग्री पूछ रहे हो, तो ये जो एडजेसेंसी लिस्ट है ना, वो ऐसी बनेगी कुछ, जो बीच वाला नोड ये होगा और इससे सभी के सभी अटैच होंगे। ओके, तो इस केस में आपको ये काउंट कर रहे हैं ना, तो ये लिस्ट पूरी ट्रेवर्स करनी पड़ेगी आपको। ठीक है, तो कितना टाइम लगेगा, ऑर्डर ऑफ वी टाइम लगेगा। वर्स्ट केस की बात कर रहे हैं, वर्स्ट केस में मे बी वी नीड टू ट्रेवर्स दैट लिंक्ड लिस्ट, दैट्स इट, सो दैट रिक्वायर्ड ऑर्डर ऑफ वी टाइम। हाउ मच स्पेस, ये आप लोग बताओ, हाउ मच स्पेस इज रिक्वायर्ड हियर एंड हियर। फर्स्ट ऑफ ऑल फॉर द एडजेसेंसी मैट्रिक्स, for storing the graph in the form of adjacency matrix, how much space is required? Anyone? Okay, otherwise yes, we get one answer from gate aspirant, that is n square, that is v square, that is v square, v number of columns are there, v number of edges are there, कितने एलिमेंट्स होंगे, v into v एलिमेंट्स होंगे, so v square space is required to store the graph in the form of adjacency matrix। And how much space is required for adjacency list? For adjacency list, actually we require v plus 2e space. How much? V plus 2e. V space is required for this. This array is actually taking v space, and if you will count this, actually it will be equal to 2e. This will be equal to 2e. Let me count it actually. 1 2 3 4 5 6 7 8. So these are 8 nodes here, so number of nodes are 8 here, let me write, and edges 1 2 3 4, edges are 4, so 2 into 4 is 8, yes, so this is how much space is required, v for the maintaining this array which is storing the starting address of every list. Okay, and 2e is required for storing these vertices. Why this is taking 2e? Because every edge you can see here, every edge is actually is information regarding every edge is stored 2 times। जैसे कि 0 से 1, 1 is adjacent of 0, जैसे 0 1 का adjacent है, 1 0 का भी तो adjacent है। तो जैसे कि राहुल मेरा फ्रेंड है, तो राहुल का मैं भी तो फ्रेंड हो गया ना, तो ऐसे ये 0 का जो है ना 1 फ्रेंड है, ऐसे ही 1 का 0 भी तो हो गया ना। तो ये एक एज के लिए आप 2 इंफॉर्मेशन स्टोर कर रहे हो, एक एज के लिए 2 इंफॉर्मेशन स्टोर कर रहे हो, तो टोटल नंबर ऑफ इंफॉर्मेशन कितनी स्टोर करोगे, 2 into e इंफॉर्मेशन स्टोर करोगे, एंड दिस इज द इंफॉर्मेशन रिगार्डिंग द edges actually। okay, so the space required is v plus 2e। any doubt you can write in the comment section, I will come back to the same slide, otherwise I will moving on। now let's talk about another subtopic, that is graph traversal। so there are 2 methods to traverse the graph, one is breadth first traversal, another one is depth first traversal। okay, so let's cover them one by one। so breadth first traversal or BFS is also known as level order traversal। तो इसमें हम लेवल बाय लेवल ट्रेवर्स करते हैं ट्री को, जैसे कि ये ट्री है हमारा, जैसे कि ये वाला ट्री है। ओके ओके, Gate aspirants asking a doubt. I will come to you that doubt. So let me cover this thing first. Okay, gate aspirant. Then I will come to your doubt. Okay. Okay. Let me finish this thing first. तो इसको बीएफएस को ना इसको इसको ध्यान से सुनो, उसको भूल जाओ अभी 2 मिनट के लिए। बीएफएस को ना हम लेवल ऑर्डर ट्रेवर्सल भी बोलते हैं, लेवल बाय लेवल ट्रेवर्स करते चले जाएंगे इसको। देखो हम लेट्स सपोज यहां से मैं स्टार्ट कर रहा हूं, देखो यहां से जीरो से हम स्टार्ट कर रहे हैं, जीरो से हम स्टार्ट कर रहे हैं, ठीक है। अब अच्छा आप बता सकते हो मेरे को, अगर हम जीरो से स्टार्ट कर रहे हैं तो नेक्स्ट लेवल पे कौन कौन सी नोड है? देखो नेक्स्ट लेवल पे ये 2 नोड्स हैं, ये 2 नोड है नेक्स्ट लेवल पे, क्योंकि यही 2 इमीडिएटली कनेक्टेड है जीरो से, ठीक है। उससे नेक्स्ट लेवल पे कौन कौन सी है? उससे नेक्स्ट लेवल पे आप बोल सकते हो जो जो नोड इससे कनेक्टेड हो या फिर इससे कनेक्टेड हो, ठीक है। तो एक्चुअली इसके बाद तो ये सभी आ गई। और अगर हम यहां से देखें 3 से, तो अगर हम 3 से देखें तो नेक्स्ट लेवल ये हो गया, अगर हम 1 से देखें तो नेक्स्ट लेवल इधर हो गया। ओके, so I think I can take even one better example than this. So maybe this is a graph I have, one maybe A, I'm making a graph B, C, maybe I think D, okay, and E, F and G। अभी अपने पास ना ये ग्राफ है, ठीक है, इसको अपने को ट्रेवर्स करना है। इस वाले को देखते हैं, ये इससे ज्यादा क्लैरिटी आएगी अपने को कि ये लेवल ऑर्डर ट्रेवर्सल का कैसे कर रहा है, मतलब बीएफएस कैसे काम करता है। देखो ए से स्टार्ट किया, उसके बाद क्या है, ये पहला लेवल है, ठीक है, ये पहला लेवल, पहले हमने ये ट्रेवर्स कर दिया, ए को ट्रेवर्स कर दिया। उसके बाद कौन सी नोड ट्रेवर्स होंगी, हम अभी बीएफएस में अप्लाई नहीं कर रहा हूं, फिर भी मैं बता रहा हूं। देखो लेवल, दिस इज लेवल ऑर्डर ट्रेवर्सल। उसके बाद ना कंफर्म है ये तीनों नोड ट्रेवर्स होंगी, और उसके बाद ये ई एंड एफ ट्रेवर्स होगा, और उसके बाद जी ट्रेवर्स होगा। तो पहले फर्स्ट लेवल की नोड ट्रेवर्स होंगी, फिर सेकंड लेवल की, फिर थर्ड लेवल की, फोर्थ लेवल की। फोर्थ वाली थर्ड वाले से पहले नहीं हो सकती, थर्ड वाली सेकंड वाले से पहले नहीं हो सकती, सेकंड वाली फर्स्ट वाले से पहले नहीं हो सकती। ओके, तो इसको चेक कर लेते हैं एक बार, क्या ये बीएफएस इसके ऊपर अप्लाई कर लेते हैं और चेक कर लेते हैं क्या ये लेवल ऑर्डर ट्रेवर्सल कर रहा है क्या बीएफएस। और ये इसका नाम वैसे ही फोर्सफुली हमने पुट कर दिया। तो देख लेते हैं इसको यहां से स्टार्ट करते हैं, ए से स्टार्ट करते हैं। तो ए से अगर हम स्टार्ट करेंगे, क्यू के अंदर बीएफएस के अंदर ना हम बीएफएस अप्लाई करते टाइम एक डेटा स्ट्रक्चर का यूज करते हो आप लोग। इस एल्गोरिथम में एक डेटा स्ट्रक्चर का यूज करते हो, बता सकते हो क्या? बता सकते हो आप लोग कौन से डेटा स्ट्रक्चर का यूज करते हैं हम बीएफएस के लिए? बीएफएस के लिए कौन से डेटा स्ट्रक्चर का यूज करते हो? इस एल्गोरिथम को अप्लाई करते टाइम एक डेटा स्ट्रक्चर का यूज करते हो। डीएफएस के लिए एक डेटा स्ट्रक्चर का यूज करते हो। Stack we use for DFS, we use stack for DFS, and we use Q data structure for BFS. Okay, so अभी देखो हम Q का यूज करेंगे, इस वाले ग्राफ पे काम करते हैं, तो इससे भी चेक हो जाएगा कि ये लेवल ऑर्डर ट्रेवर्सल कर रहा है कि नहीं कर रहा है। मतलब पहले फर्स्ट लेवल पे जो नोड है वो ट्रेवर्स करे, फिर सेकंड पे, फिर थर्ड पे, फिर फोर्थ पे। ओके, तो क्या करना है अपने को, Q ले लेनी है। देखो कैसे काम करता है BFS, बहुत ईजी है। हम ए से स्टार्ट कर रहे हैं तो इसको क्यू में डाल दो, इस भाई को क्यू में डाल दो, ए को, और क्यू, फिर देखो इसकी एडजेसेंट वर्टेक्स कौन से हैं, एडजेसेंट कौन से हैं, बी, डी एंड सी। तो इसको क्यू से निकालो और इसके एडजेसेंट को क्यू में डाल दो, बी, डी एंड सी। ओके, अभी हमने क्या कर लिया, हमने ए को ट्रेवर्स कर लिया। तो जैसे जैसे क्यू से बाहर आते रहेंगे हम बोलते रहेंगे हमने उनको ट्रेवर्स कर दिया। किस सीक्वेंस में किया, तो वो मैं सीक्वेंस यहाँ नीचे लिखता रहूंगा, ठीक है। तो ए को ट्रेवर्स किया, उसके बाद फिर हमने बी, डी और सी को हमने क्यू में डाल दिया, ठीक है। उसके बाद अपने को क्यू में हम कैसे एक्सेस करते हैं, फर्स्ट इन फर्स्ट आउट। तो पहले बी को इंसर्ट किया, तो अपने को पता है जो क्यू है ना वो फर्स्ट इन फर्स्ट आउट प्रिंसिपल पे काम करती है। तो ये फ्रंट है, ये रियर है, इसका रियर से इंसर्ट करते हैं, फ्रंट से रिमूव करते हैं। ओके, तो अभी जो एलिमेंट है हमारे पास कौन सा है, वो बी है। कौन सा एलिमेंट है, बी। अब बी को रिमूव करो, बस एक ही स्टेप है इसमें, एक ही स्टेप है, एलिमेंट को रिमूव करो, उसके जितने भी एडजेसेंट हो ना उसको क्यू में डाल दो, बस यही करना है बार बार। एलिमेंट को रिमूव करो, उसके जितने भी एडजेसेंट है उसको क्यू में डाल दो, दैट्स इट, दिस इज बीएफएस। सो बी को रिमूव किया, उसके एडजेसेंट कौन से थे, उसके एडजेसेंट ई था, ए भी है पर ए को हम ऑलरेडी प्रोसेस कर चुके हैं, जो ऑलरेडी प्रोसेस कर चुके हैं उसको नहीं डालेंगे। ई हमने प्रोसेस नहीं किया था, ई को हमने डाल दिया, ठीक है। तो हमने बी भी प्रोसेस कर दिया, जो जो निकालते रहेंगे हमको लिखते रहेंगे हमने इस सीक्वेंस में प्रोसेस किया है। उसके बाद डी को प्रोसेस करना है, डी लिख देते हैं यहाँ पे। डी के एडजेसेंट कौन से हैं? डी का एडजेसेंट कोई नहीं है, ए ही है, ए तो ऑलरेडी प्रोसेस हो चुका है। उसके बाद सी को निकाल दो, सी को प्रोसेस कर दिया, तो सी का एडजेसेंट कौन सा है? एफ, एफ को भी डालो क्यू में। उसके बाद ई आया, ई को प्रोसेस करो, ई के एडजेसेंट कौन से है? जी, तो जी को क्यू में डालो। ओके, जी को क्यू में डालते हैं यहाँ पे, ये डाल दिया। और उसके बाद फिर एफ को प्रोसेस किया, एफ यहाँ पे लिख दिया, यहाँ पे जी नहीं लिखना था। ई के बाद हमने क्या किया था? एफ। ई के बाद हमने क्या प्रोसेस किया? एफ। तो एफ को प्रोसेस किया, एफ का एडजेसेंट कौन है? जी, जी तो ऑलरेडी हमने क्यू में डाल चुके हैं। और उसके बाद लास्ट बचा हमारा जी, जी को भी हमने प्रोसेस कर दिया। बस सिंपल एक ही स्टेप है। स्टार्ट करो एक नोड से, वो आपको गिवन होगा, वो आपको गिवन होगा, उस नोड से आप स्टार्ट करो और उसको क्यू में डाल दो। क्यू में डाल के ये दिखाओ भाई हमने उसको प्रोसेस करना है, प्रोसेस कर दिया हमने उसको। और क्यू से निकालते टाइम क्या करो, उसके जितने भी एडजेसेंट हैं, जो मतलब इमीडिएटली कनेक्टेड वर्टेक्स हैं, उनको क्यू में डाल दो, ठीक है। फिर जो भी फ्रंट पे एलिमेंट हो उसको डिलीट करो, उसके एडजेसेंट को क्यू में पीछे डाल दो, रियर पे, ठीक है। ऐसे करते रहो सभी एलिमेंट्स के साथ। और दिस इज द वन सीक्वेंस यू हैव ट्रैवर्स द नोड्स। फर्स्ट यू ट्रैवर्स ए, देन यू गो टू बी, then you traverse actually D, then E, C, E, F, and G. Okay, so one thing we can ensure that first we traverse the A, okay, then we traverse B, D, and C, then we traverse the node at next level B, D, and C, then we traverse E and F, which is at next level node, and then we traverse G, which is last level node. Yes, this is level order traversal. BFS is level order traversal. Okay, this is all about the BFS. That's it. One more point you can note here is that you can add B, D, and C in any order. Maybe means you can add C first, then D, then B. You can add these three in any order. देखो ये जो ये तीनों थी ना, ये एक ही एडजेसेंट थी, तो इनको किस ऑर्डर में डालना है? क्यू में, किसी भी ऑर्डर में डालो, जो भी कॉम्बिनेशन आपसे बनता है वो बना लो। पहले डी डालना है, डी डाल दो, फिर बी सी डाल दो, पहले सी डाल लो, फिर डी सी डी बी डाल दो, जो भी कॉम्बिनेशन आपको बनाना है वो बना के आप डाल सकते हो। सो दैट्स मीन्स देयर आर मैनी सॉल्यूशन पॉसिबल, मैनी breadth first traversals are possible for the same graph. Yes, that is possible. Okay, so एक पॉइंट और अपने को पता लग गया। तो मैं इसको समराइज कर देता हूं, इसको, इस स्लाइड को। बीएफएस में क्या करना है? कुछ नहीं, एक नोड को उठाना है, क्यू में डालना है और उसको प्रोसेस करना है। प्रोसेस करने के बाद उसके जितने भी एडजेसेंट नोड को फिर उनको क्यू में डालना है, किसी भी ऑर्डर में डाल सकते हो, कोई मैटर नहीं करता। और फिर इसी प्रोसेस को रिपीट करते रहना है जब तक सभी नोड्स प्रोसेस नहीं हो जाते। दैट्स इट। और हमने ये भी नोट कर लिया, यहाँ पे ये भी फाइंड आउट किया, ये लेवल ऑर्डर ट्रैवर्सल है, लेवल बाय लेवल ही एलिमेंट्स को प्रोसेस कर रहा है, ट्रैवर्स कर रहा है, तो इसका नाम सही दिया गया है, एक नया नाम, लेवल ऑर्डर ट्रैवर्सल। ओके, और एक ग्राफ के काफी सारे बीएफएस बीएफटी ब्रेथ फर्स्ट ट्रैवर्सल हो सकते हैं, क्योंकि हम जैसे कि यहाँ पर बी डी सी को किसी भी सीक्वेंस में अरेंज कर सकते हैं। तो अगर हम बी सी बी डी लिखें तो ये एक अलग ट्रैवर्सल बन जाएगा, बट सो देयर कैन बी मेनी BFT for the same graph. That is also true. Okay, so there is no backtracking in BFS. Yes, you are right, aspirant. There is no backtracking. There is backtracking in DFS. There is backtracking in DFS. Yes, you are right for that. So इसको अभी इसकी कॉम्प्लेक्सिटी देख लेते हैं. What is the complexity of BFS? Let's drive the complexity of BFS. Can you write the time complexity of BFS? Anyone know time complexity of BFS? Otherwise, I will make it very easy. You will understand in next 2 minutes. That will be very clear. Okay, let me share. You people, please help me in this. I need your help actually. आप लोग मेरे को बताओ. तो ये पहली लूप क्या कर रही है? For each vertex which belongs to the graph, ये जो लूप है ना, ये सभी वर्टेक्स के लिए एक एक बार चल रही है, ठीक है। ये एल्गोरिथम में ना, इसने, मैं आपको बता दूं, आइडिया दे दूं, ये कर क्या रहा है एल्गोरिथम में। इसने क्या किया है एक्चुअली, ओके, इसने क्या किया है, ये जो एल्गोरिथम है ना, ये थोड़ा दूसरे तरीके से काम कर रहा है। काम वही कर रहा है जो हमने पिछले लास्ट स्लाइड में डिस्कस किया है, पर मैंने आपको बिल्कुल शॉर्टकट वे में बता दिया। ये थोड़ा घुमा के पकड़ रहा है, क्योंकि ये कैसे कर रहा है बता देता हूँ आप लोगों को। ये ऐसे ही है, जैसे कि एग्जांपल लेते हैं, जैसे क्लासरूम का एग्जांपल लेते हैं, क्लासरूम का। ओके, मैं क्लास में खड़ा हूँ, और in that class actually I have many students, actually I have many students in the class, and I just want to traverse each and every student one time. So every student have their queries with them, but I want to take one query, only one query from one student, because I need to cover all the students. So I want to take one query from one student. I will not take two query. Means I will not visit a node twice. I will visit a node once only. Okay. तो उसके लिए इसने क्या किया है, इसने ना थोड़ा सा कलरिंग का खेल किया है। What he is doing, that what we can do in that class is, actually, initially I can, what I can do is, I can mark a white symbol at the back of every student. Okay, I can mark the white symbol, so that okay, I can know that, okay, I have not visited that. I have not visited any of the student who have the white mark. So initially I will white mark all my 60 students. Okay, white mark all the 60 students. After that, when they will come to the podium, okay, when they will come to the podium for their taking the answer to their query, means they are coming to the queue. The node is coming to the queue right now. Okay, so at that time I will mark, I will paint them gray from the back. I will paint them gray from the back, so that I can see that, okay, their query is under processing. Their query is under processing. Just to know that thing, if the node is in the queue, we will mark it as a gray. Okay, and the last thing what I will do is, when their query will be resolved, then I will mark black. I will mark the black, actually. So black means show that, black will show that, okay, I have taken the query, means node is now, vertex is now out of the queue. If vertex is out of the queue, I will mark it as a black. That's it. So ये एग्जांपल में ना, ये बस ये कलरिंग यूज कर रहा है। इन कलर का यूज करके ये इस बीएफएस को अप्लाई कर रहा है। देखो कैसे कर रहा है। तो ये पहली जो लूप है आपकी, ये सभी वर्टेक्स को कलर कर रहा है, व्हाइट कलर कर दे रहा है सभी वर्टेक्स को, सभी वर्टेक्स को व्हाइट कलर कर दे रहा है। सो ऑलरेडी व्हाइट ही है ये, ठीक है। और दो चीजें और ऐड कर रहा है ये एक्चुअली। एक तो उसका डिस्टेंस, ओके, सोर्स नोड से, लेट्स सपोज सोर्स नोड ये है, एक सोर्स नोड आपको गिवन होगी, देखो यहाँ पे एस दिया हुआ है सोर्स नोड, जी स्टैंड फॉर ग्राफ। तो ये ग्राफ दिया है जिसके ऊपर बीएफएस अप्लाई करना है, और सोर्स नोड जहां से स्टार्ट करना है। तो ये एरो से मार्क कर दिया हमने सोर्स नोड। और यहाँ पे दो इंफॉर्मेशन और स्टोर कर रहा है हर वर्टेक्स के साथ। एक तो इस वर्टेक्स का, लेट्स सपोज ये वर्टेक्स जो है ना, इसका नाम दे देते हैं ए बी सी डी ई एफ जी एच। ओके, तो इस वर्टेक्स में ना, जो इस वर्टेक्स का ए डॉट, आई कैन से डिस्टेंस, पेरेंट से स्टार्ट करते हैं। ओके, बी डॉट डिस्टेंस, इनिशियली ये सभी का जो डिस्टेंस है ना, वो इनफाइनाइट कर दे रहा है। वो क्या कर दे रहा है, इनफाइनाइट कर दे रहा है सभी का। मैं लिख देता हूं यहाँ पे, सी डॉट डिस्टेंस फ्रॉम पेरेंट नोड, फ्रॉम वेयर, फ्रॉम दिस बी नोड, फ्रॉम दिस स्टार्टिंग नोड द डिस्टेंस इज इनफाइनाइट। क्योंकि अपने को नहीं पता ना, अभी स्टार्टिंग में नहीं पता यहां से यहां का डिस्टेंस कितना है। ओके, सो डी डॉट डी इज इनफाइनाइट, एच डॉट डी डिस्टेंस इज इनफाइनाइट, जी डॉट डी इज इनफाइनाइट, एफ डॉट डी इज इनफाइनाइट। अभी आप मेरे से ये भी पूछ सकते हो, सर आप ये डिस्टेंस निकालने में कहाँ लग गए, हमें तो खाली ट्रेवर्स करना था, डिस्टेंस क्यों निकाल रहे हो। एक्चुअली BFS is one of the best. You can mark this point. This is actually very important point about the BFS. BFS is one of the best algorithm to find out the single source shortest path for unweighted graph, for unweighted graph. तो व्हाट इज सिंगल सोर्स शॉर्टेस्ट पाथ, मतलब सोर्स नोड से बाकी सभी नोड का जो शॉर्टेस्ट डिस्टेंस है, बी से ए का शॉर्टेस्ट डिस्टेंस, बी से ई का शॉर्टेस्ट डिस्टेंस, बी से एफ का शॉर्टेस्ट डिस्टेंस, तो सभी नोड का शॉर्टेस्ट जो डिस्टेंस है वो फाइंड आउट करने के लिए बीएफएस जो है ना वो बेस्ट एल्गोरिथम है। ऑल्दो और भी एल्गोरिथम्स हैं, और कौन कौन से हैं, जैसे कि डाइकास्ट्रा हो गया और एक बेलमैन फोर्ड हो गया, पर इनसे भी बेटर कौन सा है, बीएफएस। पर इसमें बस कंडीशन ये है, ये जो बीएफएस है ना वो अनवेटेड ग्राफ पे काम करता है, और ये जो है ना दोनों डाइकास्ट्रा और बेलमैन फोर्ड, ये वेटेड पे भी काम करते हैं, अनवेटेड पे भी काम करते हैं। पर अगर आपके पास इनपुट में अनवेटेड ग्राफ हो ना, जैसे कि ये वाला ग्राफ जो अनवेटेड है, एजिस के ऊपर वेट नहीं है, एजिस के ऊपर वेट नहीं है, तो इसके ऊपर हम, इसके अंदर हम अगर सिंगल सोर्स शॉर्टेस्ट पाथ फाइंड आउट करना है तो बीएफएस बेस्ट एल्गोरिथम है। ये क्वेश्चन भी है गेट में आप लोगों का। ओके, वहां पे ऑप्शंस दिए गए हैं, आउट ऑफ डाइकास्ट्रा, बेलमैन फोर्ड, बीएफएस, डीएफएस, व्हिच इज द बेस्ट एल्गोरिथम टू फाइंड द सिंगल सोर्स शॉर्टेस्ट पाथ फॉर अनवेटेड ग्राफ, बीएफएस इज द बेस्ट एल्गोरिथम। ओके, तो इसलिए यहाँ पे ना ये डिस्टेंस भी कैलकुलेट करके दिखा रहा है आपको, क्योंकि ये डिस्टेंस उसी में काम आ रहा है अपना। दूसरी इंफॉर्मेशन क्या थी, पेरेंट की इंफॉर्मेशन। स्टार्टिंग में मेरे को नहीं पता बी का पेरेंट कौन है, पेरेंट को ये पाई से रिप्रेजेंट कर रहा है, बी डॉट पाई आई डोंट नो, नील, a dot pi is also nil, c dot pi is also nil, d dot pi is also nil, every one parent is nil, n for nil, h dot pi is nil, g dot pi is nil, f dot pi is nil, e dot pi is nil. Okay, तो पेरेंट सबका नील है, क्योंकि मेरे को नहीं पता कौन सा नोड किससे कनेक्ट होगा जाके फ्यूचर में। अभी स्टार्टिंग में सबका पेरेंट हमने नील कर दिया, सबका डिस्टेंस इनफाइनाइट कर दिया, सबको व्हाइट कलर मार्क कर दिया, सबके फेस पे व्हाइट कलर कर दिया, जिससे हमें पता लगे हमने उसको विजिट किया ही नहीं अभी तक। ठीक है, तो ये 4 लाइन में यही हो रहा है। आप लोग मेरे को बताओ इन फर्स्ट 4 लाइन का में कितना टाइम लगेगा, वो टाइम आप शेयर कर सकते हो, कितना टाइम लगेगा ये फर्स्ट 4 लाइन को एग्जीक्यूट करने में, आप बता सकते हो। ये जो लूप है 1 to 4 एग्जीक्यूट हो रही है, इसमें कितना टाइम लगेगा, थिंक ओवर इट एंड रिप्लाई। सो इफ यू विल पार्टिसिपेट देन आवर सेशन विल गो मोर इंटरेस्टिंग। मीनवाइल यू कैन थिंक ओवर इट। मीनवाइल अब ये क्या कर रहा है, सोर्स नोड को एक्चुअली ये क्यू में डाल देगा। देखो क्यू इज स्टैंड फॉर क्यू, दिस इज क्यू, ये वाली क्यू। ओके, तो जो ये क्यू है वो क्यू है। ओके, अभी ये क्या करेगा, सोर्स नोड को उसने क्या कर दिया, एन क्यू कर दिया, किसके अंदर, क्यू के अंदर। सोर्स सबसे पहले हमने कौन सा नोड डालना है, बी को डालना है, बी को हम क्यू में डालेंगे जहां से हम स्टार्ट कर रहे हैं। ओके, और उसका कलर ग्रे कर दिया, सोर्स नोड का कलर क्या कर दिया, ग्रे, क्योंकि हमें अपने को पता है जो भी नोड क्यू के अंदर जाएगी उसका कलर ग्रे हो जाएगा। और उसका डिस्टेंस कितना कर दिया, 0। उसने बोला 0, बी से बी का डिस्टेंस कितना होगा, 0। उसका पेरेंट जो नील ही रहेगा, द पेरेंट ऑफ बी इज नील बिकॉज पी डोंट हैव एनी पेरेंट, पी इज ऑर्फन, पी डोंट हैव एनी पेरेंट, पी हैव lots of children maybe, but p don't have any parent. Okay, so p parent is nil, and so in the starting the q is also nil, this is nil, this is empty, means nil, so q is nil, the starting q is nil. After that we inserted this source node inside the nil, b. Okay, then we will keep executing this loop until unless our q will become empty. Okay, so इसके बाद तो वही होने वाला है जो हमने पहले डिस्कस किया था, बी को डिलीट करो, यहाँ पे इसको हमने बी को डिलीट किया और उसके सभी एडजेसेंट फाइंड आउट किए, कौन कौन से बी के एडजेसेंट थे, ए और एफ, उनको आप किसी भी ऑर्डर में इंसर्ट कर लो, एफ और ए और ए और एफ, यही थे ना 2 एडजेसेंट, ए और एफ, तो दोनों को यहाँ पे इंसर्ट कर दिया। एडजेसेंट थे, उनका कलर व्हाइट था, यस, तो वो विजिटेड भी नहीं थे, तो और उनके जो डिस्टेंस थे वो अपडेट कर दिए, तो इसका डिस्टेंस 1 हो गया, इसका डिस्टेंस भी क्या हो गया, 1 हो गया यहाँ पर। और इनके पेरेंट को कौन बन गया, बी, बी से दैट आई डिस्कवर एफ, बी से दैट आई डिस्कवर ए, So B say that I am your father, I am your father. So उनके पेरेंट को भी हमने अपडेट कर दिया, उसका डिस्टेंस भी अपडेट कर दिया, उसका इनका कलर भी ग्रे कर दिया क्योंकि ये क्यू के अंदर है, ठीक है। और फिर हमने क्या किया, क्यू के अंदर हमने इनको डाल दिया ए और एफ को, और ये सभी डालने के बाद, एडिशन डालने के बाद फिर हम उससे बाहर आए और बी का जो कलर था हमने क्या कर दिया, ब्लैक, क्योंकि बी को हम डिलीट कर चुके हैं। तो सिंपल है, बस इतना ही काम किया। अब ये जो प्रोसेस है ना रिपीट होती रहेगी जब तक हमारा क्यू नील नहीं हो जाता। तो मैं रिपीट कर रहा हूं इसको वन मोर टाइम। एक we will dequeue one element from the queue, so we will delete the front element, that is a. We will delete front element, that is a. Who is the adjacent of a? That is e. We will insert inside the queue. Okay, and that's it. We will keep doing that. Which is the next element? F. Delete it, f. Delete the f. Who are the adjacent? C and G. B is already covered. C and G. So C and G will be covered, will be inserted inside the queue, and f will be deleted. That's it. Next one is e. So e will be deleted. Is there any adjacent? No. A is adjacent, but that is already listed. Next one is c. C adjacent is d and h and g. G is already there. D and d. H is not. H is not the adjacent of c. Only d. Only d. Why I'm saying h? F is also there, but F is already processed. G is already inside the queue. D is the only one who is not looking at, nobody's looking, was looking at here. So C was looking. C, they say that it's okay, let me become your father. So he become the father, and I will update the distance also later on. So next one is G. G adjacent is H, then D, then H. That's it. So let me update the value also. So from here to here distance is 1. From here to here distance is 1. And what is the distance? The parent here will be, who discovered the E? This A discovered the E. So A become the parent. So from B to A distance was 1. And one distance is this. The total distance become 2 from B. This is the total distance from B actually. B to A to E. That is 2 actually. Okay. So this is already done. What about this? So C was discovered by the actually F. So parent of C is F, and distance is actually, यहाँ से E से F का distance 1 था, तो F से E का 1 more, 1 plus 1 2. ओके, यहाँ पे डिस्टेंस कितना हो जाएगा? G को किसने डिस्कवर किया? F ने ही किया है, तो इसका फादर F है, तो F तक पहुंचने में 1 टाइम लग रहा था, F से आगे जाने में 1 more 2. यहाँ पे इसका डिस्टेंस, D को किसने डिस्कवर किया? C ने. C का डिस्टेंस कितना है? 2. 2 plus 1 3. पेरेंट वाले में एक ऐड कर देना है, पेरेंट के में एक ऐड कर दो, दैट्स इट. तो H का पेरेंट कौन है? H का पेरेंट G है, आई थिंक, यस. और G की वैल्यू कितनी है? डिस्टेंस की 2, उसमें एक और ऐड कर दो, तो H का डिस्टेंस आएगा 3. ओके, दैट्स इट. ओके, तो इसमें अभी बस मेरे को 2 पॉइंट बताने हैं आप लोगों को. एक तो कॉम्प्लेक्सिटी, और एक और पॉइंट मैं बताऊंगा, दैट इज ऑल्सो वेरी इंपॉर्टेंट. तो लेट मी इरेज दिस थिंग. लेट्स टॉक अबाउट द कॉम्प्लेक्सिटी फर्स्ट. तो कॉम्प्लेक्सिटी में क्या है? यहां पर ये जो लूप है ना, ये n टाइम एग्जीक्यूट हो रही है, v टाइम, वी कैन से v टाइम एग्जीक्यूट हो रही है. जितने वर्टेक्स हैं उतने टाइम एग्जीक्यूट होगी. यहां से लेके यहां तक कांस्टेंट टाइम लग रहा है, एक एक स्टेटमेंट है, एक एक बार एग्जीक्यूट होगी. ये जो लूप है ना, कितने टाइम एग्जीक्यूट होगी ये आप बता दोगे तो मतलब बस कमाल ही हो जाएगा. अगर ये आपने बता दिया तो ये कितने टाइम एग्जीक्यूट हो रही है. ओके, बाकी ये आपका कांस्टेंट टाइम हो रहा है. ये आपका जो है ना, ये v-1 टाइम हो रही है एसिम्प्टोटिकली, अप्रोक्सीमेट आई मीन, एंड ये स्टेटमेंट जो है वो कांस्टेंट टाइम हो रही है. ठीक है, तो आप लोग मेरे को बता सकते हो क्या ये लूप कितने टाइम है? ये क्यू में कितने एलिमेंट होंगे कि वो ये लूप कितने टाइम एग्जीक्यूट होगी? ये लूप जब तक चलेगी जब तक क्यू में एलिमेंट है. आप मेरे को बता सकते हो मैक्सिमम कितने एलिमेंट आएंगे क्यू के अंदर? मैक्सिमम कितने एलिमेंट आएंगे क्यू के अंदर, अगर आपने ये बता दिया? सो सी, द साइज ऑफ क्यू विल बी v only, fix, and you already given the answer, that is there will be no repetition. We are not repeating the vertex, and that is also sure that every vertex is inserted one time. That will be inserted one time. Every vertex must be inserted inside the queue. That is also sure. And this is also sure we are not repeating the same vertex again inside the queue. So how many times this loop will execute? V time. Okay, now let's wind up. Now the time complexity of the let me make space here, and let me tell you the time complexity of BFS now. We know the time complexity of every line here. So initially that take order of free time. So time complexity of BFS is this order of V plus this constant. Okay, I'm not considering constant. I don't have space here. Constant is not making any difference. So this is V. See, this thing is inside the loop. Okay, so I will write in the multiply. Okay, so again we get constant plus V minus 1 order of V minus 1, and you can add this constant also maybe. So this constant you can remove. Okay, so we get this thing. Now V plus, this is V into 1 V plus V into, this is also asymptotically V actually. This is also asymptotically V. So V into V square. So I can write it as V 2V plus V, or I can write V plus V square. Okay, and I can write it as like V plus E also. Why? Because V square is approximately equal to E. So I can replace V square with E. So the time complexity of BFS is V plus E. So why I replace V square? How I replace V square with E is because for complete graph, you know that number of edges is actually equal to V into V minus 1 divided by 2. And this thing is actually asymptotically is how much? V square. So that's why I replace V square with E. That's it. So this is the time complexity of BFS. That's it. Okay. So we find out the time complexity of BFS. One last point I want to share with you here on this particular slide is that I tell you that BFS help us to find out the single shortest path. और आप यहां पर देख सकते हो B से S तक पहुंचने में शॉर्टेस्ट डिस्टेंस कौन सा है? देखो, एक डिस्टेंस तो ये भी हो सकता है मैं B से पहले G पे जाऊं, G से C पर, और C से D पर, और D से H पर. एक डिस्टेंस ये भी हो सकता है ना, एक रास्ता ये भी हो सकता है. तो कितना डिस्टेंस लगा? 1 2 3 4. पर मिनिमम देखो, यहाँ पे मिनिमम डिस्टेंस इसने बताया अपने को H तक पहुंचने का 3. कौन सा रास्ता बनेगा? B से F, F से G, G से H. And this is the shortest path. Actually, this is the shortest path not only up to H, but up to every vertex. D तक पहुंचने में, B से D तक पहुंचने में मिनिमम 3 स्टेप लेने पड़ेंगे. B से A तक पहुंचने में 1 स्टेप तो लेना ही पड़ेगा. B से E तक पहुंचने में 2 स्टेप्स तो लेने ही पड़ेंगे. B से F तक पहुंचने में 1 स्टेप तो लेना ही पड़ेगा. तो we are also able to find out the single shortest path with the help of BFS. In how much time? In V plus E time. Do you know how much Bellman-Ford take? Bellman-Ford take V cube time to find the single shortest path. Okay. So this is better than Dicastro also actually. Okay. So let me summarize this slide. One thing, the complexity of BFS is V plus E, order of V plus E. Second thing, BFS is also used for finding the single shortest path. That's it. Any doubt, you can write in the chat box. Otherwise, this is the GATE question for you people. Please try it. It's your turn now. Please try and reply in the chat section. So this is GATE 2017 question. You people have enough information with you and you can solve this question easily. Believe me, you can solve it very easily. Please try it. So we need to find out breadth first search has been implemented using Q data structure. We know that is implemented using Q data structure. Which one of the following is the possible order of visiting the nodes in the graph? So how we can visit the which can be the possible sequence of visiting the nodes. So let's check out if this is fine or not. First of all, if we are starting from P, then in the queue, which nodes will go actually? Then you can see directly, you can see one. First, if we are visiting this, then next level is this, because this is level order traversal also. Then we will visit these nodes. And after these nodes, actually, we will visit these three nodes. And even I can say that I will visit these nodes before this node. So first I will visit this node, then these nodes, then this node, then this node. How I am finding this? Because BFS is level order traversal. You do not even need to apply the BFS over this. तो पहले P होगा, फिर इन दोनों में से होगा, क्योंकि यही डायरेक्टली कनेक्टेड है ना P से O और Q, और उसके बाद फिर M और N या तो Q O से कनेक्टेड है या Q से कनेक्टेड है. R नहीं कनेक्टेड है तो R तो नेक्स्ट लेवल पे चला गया, R नेक्स्ट लेवल पे चला गया, तो N और M और N आ गए हमारे इस लेवल पे, थर्ड लेवल पे, और R फोर्थ लेवल पे चला गया. अभी देखो पहले P एग्जीक्यूट हो रहा है, ओके हो सकता है, बिल्कुल P से स्टार्ट कर सकते हैं, फिर O और Q एग्जीक्यूट होगा, किसी भी ऑर्डर में हो, Q O हो पहले या O Q हो, कोई बात नहीं, ये होंगे, ये श्योर है, ये दोनों होंगे, ये बाद में नहीं होंगे, ये पहले होंगे अगर P पहले विजिट किया हमने. उसके बाद N और M होंगे, बिल्कुल थर्ड लेवल पे N और M है, ये होंगे, ये M और N भी हो सकता था, वो भी ठीक था. उसके बाद R होगा, बिल्कुल सही. और अब इनको चेक करते हैं, देखो तो बहुत इजी है. अगर हम M से स्टार्ट करते हैं एक केस में, M से, अभी देखो मैं इसको इरेज करता हूं. अगर हम M से स्टार्ट करते हैं तो नेक्स्ट लेवल कौन सा बना? नेक्स्ट लेवल बना ये, क्योंकि ये डायरेक्टली कनेक्टेड है M से, और उससे नेक्स्ट लेवल हमारा ये बना. ठीक है, तो पहला लेवल, दूसरा लेवल, तीसरा लेवल, सीधे मतलब सीधा अगर आपको टाइम वेस्ट किए बिना फाइंड आउट करना है तो पहले M विजिट करेंगे, फिर उसके बाद R, N और Q विजिट होने चाहिए O और P से पहले. N विजिट हो रहा है, ओके. O नहीं विजिट हो सकता, O नहीं विजिट हो सकता पहले, O विजिट नहीं हो सकता पहले ये तीनों विजिट करने पड़ेंगे अपने को, तो तीनों नहीं हुए हैं, O पहले कर दिया इसने, तो ये तो आंसर हो ही नहीं सकता. तो ऐसे ही आप इनके लिए भी चेक कर सकते हो, इनके लिए भी ये फेल कर जाएगा, इसके लिए राइट शो कर रहा है. अदरवाइज आप पूरा एल्गोरिथम अप्लाई भी कर सकते हो, अगर आपको पूरा एल्गोरिथम अप्लाई करना है तो पूरा कर लो, अदरवाइज ये सीधा शॉर्टकट है, सीधे शॉर्टकट से कर लोगे तो और इजी हो जाएगा. एक और करके दिखा देता हूं मैं आप लोगों को, लास्ट इस सी के लिए कर लेते हैं. अब क्यू से आप स्टार्ट कर रहे हो, तो देखो क्यू से स्टार्ट कर रहे हो तो ये पहला लेवल हो गया, नेक्स्ट लेवल पे कौन से हो गए? नेक्स्ट लेवल पे ये हो गए, ये चारों हो गए नेक्स्ट लेवल पे, ये चारों कनेक्टेड है ना क्यू से डायरेक्टली, ये उससे नेक्स्ट लेवल पे होगा, तो पहला लेवल क्यू का हो गया, दूसरा लेवल इनका हो गया, तीसरा लेवल इनका हो गया. तो इतना श्योर है, ये जो दूसरे लेवल पे नोड है ना, ये सभी पहले एग्जीक्यूट होंगी आर से, पर इसमें आप देखो आर पहले एग्जीक्यूट हो रहा है और पी से, हो ही नहीं सकता, और पी पहले एग्जीक्यूट होगा क्योंकि वो सेकंड लेवल पे लाई कर रही है. और ये बीएफएस जो है ना हमारा लेवल ऑर्डर ट्रेवर्सल है, तो लेवल ऑर्डर ट्रेवर्सल क्योंकि है ये, तो और पी पहले होनी चाहिए आर से, पर ये आर पहले कर दे रहा है, तो ये भी रॉन्ग होगा. तो सीधे आप सीधे आंसर फाइंड आउट कर सकते हो rather than applying complete BFS. Otherwise you can apply the complete BFS and give the solution. Okay, so let's check out this ISRO 2020 question. Can you try this one? You people try, and let me also make the let me also try also here. I'm not speaking anything, just trying it. So you people try yourself, and I will try at my end. I'm trying at my end. V4 to V5. This V4 is already here actually. तो यहाँ से यहाँ है, यहाँ से यहाँ है, V4 से V5, V4 से V6 is also there, V6 is also there, 5 से V6, okay. V6 to V7, okay. Okay. So any answer from your side? Otherwise, I'm trying this. अगर पहले आप ट्राई करोगे तो आपको कॉन्फिडेंस भी आएगा इन क्वेश्चंस में, और उसमें लर्निंग भी ज्यादा होगी। उसमें लर्निंग कितने परसेंट होगी अगर आप सीधे ट्राई कर रहे हो? 100%। अगर मैं ट्राई कर रहा हूं, आप समझ रहे हो खाली, तो that can drop actually at very sharp rate, that can reduce to 20% even. Okay, so if you are trying, you are not getting solution, that doesn't matter, still the learning is 100%. But here, if I will explain only and you will just listen, then believe me, learning will happen, no doubt, but that will reduce to 20%. That is the harsh reality. Okay, let me try at my end. Meanwhile, if you are trying, please keep trying. Don't listen to me. You can put me on mute if you think that I'm disturbing you. So G is an undirected graph with vertices this. ये अपने पास एक ग्राफ है, इन V1 से V7 vertices का एक ग्राफ है। ओके, उसमें एक एजिस है, ये वाली एजिस दी हुई है, हमने सब एजिस बना ली है, हमने सब एजिस यहाँ पे बना ली है। तो अब ब्रेडथ फर्स्ट सर्च ऑफ ग्राफ ऑफ द ग्राफ इज परफॉर्म, BFS इस पे हमने अप्लाई किया। V1 एज द रूट नोड, V1 को रूट नोड हमने मान लिया। ओके, विच ऑफ द फॉलोइंग इज द ट्री एज, तो लास्ट में जो ट्री बन के आएगा BFS ट्रेवर्सल के बाद, उसका उसमें उसमें इसमें से कौन सी एज उस ट्री से बिलोंग करती है, वो अपने को बताना है। तो BFS अप्लाई कर लो उसके ऊपर। तो अगर पहले V1 को डिजिट कर रहे हो, उसके बाद किसको कर रहे हो? V2 को, V3 को, V4 को। तो डायरेक्टली कर रहे हो तो इनको कनेक्ट कर दो, V1 V2, V1 से V4, ठीक है। इसके बाद किसको करोगे? मे बी ये आउट हो गया तो V2 को कर लो, V2 से इसको आपने विजिट कर लिया, ठीक है। V5 आपने इंसर्ट कर दिया था, तो फिर V3 को किया, V3 से आपने ये तो ऑलरेडी हो चुका है, इसको नहीं करेंगे अटैच। और V4 से V6 आप कर दोगे, V6 को आप क्यू में डाल दोगे, तो V4 भी बाहर हो गया। पर ये वाली एज हमने कंसिडर की है, एक ये की है और ये की है। ओके, ये वाली की है अभी तक। V5 से V6 पे जा सकते हैं, V6 ऑलरेडी है, लेकिन उसके बाद V6 से V7 पे जा सकते हैं, तो V7 वाली ये वाली एज आ गई हमारे पास, ठीक है। दैट्स इट। तो ये वाला जो ट्रेवर्सल ट्री हमारे पास बन के आया है, इनमें से देख लो कौन सी एज यहाँ पे बिलोंग कर रही है। V2 टू V4 एज नहीं है, ये हमने एज नहीं है हमारे ट्री के अंदर। V1 टू V4, यस, V1 टू V4 है। और V4 से V5 नहीं है, ये वाली हमने कंसिडर नहीं की। V3 से V4 भी कंसिडर नहीं की। तो आंसर कौन सा हो गया? बी हो गया। आंसर कौन सा हो गया हमारा? बी। दैट्स इट। So yes, B is the right answer. Okay, let's try next one. This is GATE 2016 question. Please try it yourself first. If you want full learning, 100% learning, then you need to try it. I will definitely try. So maybe I can give, don't look at the answer. So maybe you can get some idea from this tree also. Okay, let me try this question. This question I think require little more time, no doubt. So if you want to try it, you can try it at home maybe. Okay, so right now he is asking, okay, we are applying BFS is started at the binary tree. We start apply the BFS, okay, at binary tree from the root node. From the root node, okay, we apply BFS on this graph. This is also a graph. Tree is also a graph. There is a vertex t at the distance of 4 from the root. So this is 1 distance, this is 2 distance, this is 3 distance, and this is 4 distance. So he's saying that there is a one vertex out of these are the vertices which are at the fourth distance, which are at the fourth distance. if t is the if t is the nth vertex in BFS, if t is the nth vertex in BFS, then the maximum possible value of n is what? Okay, so he's asking actually what should be the uh, so if we will traverse this tree, and what will be the if we will traverse this tree actually. So one thing is sure, we are traversing level by level. So first we will traverse this, then we will traverse these two nodes, then we will traverse these all nodes. BFS will work like this only. Then that will traverse these nodes. Okay, and actually at last level, he's asking what can be the uh, nth vertex, maximum possible value of nth vertex, maximum possible value of nth vertex. So here you can see that in a complete binary tree, this is a complete binary tree, the last node will be of actually 31. That will be the 31st node. That will be the 31st node. That will be the that node will be actually visited in can be visited at the end. So this can be the maximum value actually of a node. Actually, this is the maximum number of the node which can be visited at the fourth level, by the BFS. Okay, so that's why C is the right answer, because this is the maximum number. Even we can have only 31 nodes in a if a height of the tree is 4. Okay, so C is the right answer. You can think more over it, or you can think more over it. And let's move to the next one. Let's move to the now DFS, how DFS work. That is also very easy. Let me tell you, first of all, let me tell you that the complexity of DFS is same as BFS. Both have the same complexity. So the time complexity of BFS is same as time complexity of DFS. So that is actually order of V plus E. Okay. Okay. Now let's apply the BFS over here. DFS, depth first search or depth first traversal. So we want to traverse all the nodes of the graph with the help of this algorithm. That is also very easy. Okay. Here actually we find two information at every node. One is there. One is there. One is there. One is their finish time, and one is their, I can say, okay, discovery time. One is their discovery time. Discovery time and finish time. Discovery time is that time when I discover that node first time I met with that node. And finish time is now it's over. It's over. First time you meet your girlfriend, that is your discovery time, and when you say it's over, then you say finish time. Okay, so let's find out the discovery and finish time for all the girlfriends. So maybe you have 6 girlfriends here, and you are starting with this girlfriend. So you find this girlfriend at 1 unit of time, and then when you were having this girlfriend, you can move to these 2 girlfriend also, this one and this one, because arrow is going here also. Okay, so let me give the name of your girlfriend, A, B, C, D, E, F. So we can move from A to B and A to D also. So while you have a girlfriend at 1 unit of time, you can make another girlfriend at 2nd unit of time. Right now you have 2 girlfriends. Okay, then from B you can move to this E also. Okay, so now you have 3 girlfriends. You can have 4 girlfriends now. After this you cannot move anywhere, because you are again moving back to this B one. Okay, so you don't see any new girlfriend here. So you say that, okay, I'm finishing with you. You say to D, I want to uh, search for new girlfriends. So I'm finishing with you. You finish this node actually. Okay. And you come back to E, and now actually you go from here to here, here to here, and then here to here. Okay. Then you will roll back. You will track back. You will go back here. Now you are at this E. Then you see that, okay, you cannot go further from E to anywhere. Okay. So you are saying to E also, I'm making over with you also. I'm finishing with you also, because I'm in search of new girlfriends. So you are now at B. At B also you don't find any other new girlfriend. So you say, I'm finishing with you also. Then you come to A. You don't find any new girlfriend, and you are very eager to have new girlfriend. So you finish with A also. And then you find a new way to find the new girlfriend. And at ninth unit of time, you were free. You just jump to a new girlfriend here, and from new 9 you jump to 10, because you can go from C to F. Then from 10 you don't find any new girlfriend, you come back from here to here and here to here. That's it. You have visited all the nodes. You have visited all the nodes. This is what how you can apply the DFS algorithm to increase, to find out your all the girlfriends actually. I mean, you have to find out all the nodes in the graph. Okay, so this is what this is how we are traversing. That's it. This is DFS we have applied. That's it. And these are the two information we find. One is discovery time, one is finish time with every node. And we are also seeing that we are backtracking. We are also backtracking. Okay, and we also see one more thing, that when we come back to A, we were not able to go any further. Then we randomly start with C. Okay, we can pick, in place of C we could pick F also. Means, rather than writing this thing and this thing, at ninth unit of time I could start with F also. And from F I cannot go to C, so I need to finish with F. Then I can go to C, discover C, and finish with F, C. Okay, so this is how the DFS algorithm work. And if you want to check you know about the DFS algorithm or not, what you can do is, let me little bit modify it, and you people tell me what should be the discovery time and finish time. Okay. So what I'm doing is now, so this arrow is like this right now. Okay, I'm now reversing this arrow. This arrow is this, the direction is this. I just change one direction in the complete graph. I just change one direction, this. So can you tell me now, what is the discovery and finish time of C? Only C I'm asking. Of C node, what is the discovery and finish time? Can you please tell me? Can you please tell me what is the discovery and finish time of C? I have reversed the node. This node is not in both direction. This node is from E to C. Okay. So can you apply the DFS algorithm here? And can you tell me what is the discovery and finish time? If you want to really try for it. So if you can reply, then that's mean you know the DFS algorithm, how DFS is working. Maybe you are still thinking about your girlfriend otherwise. So maybe I can apply this for you people. If you are applying, that's great. So Sachin, let me tell you how you can find out. Let me tell you how you can find out your girlfriend. See, these are the different girlfriends you have, like A, B, C, D, E, and F. From E to C you can move. Okay, from this girlfriend to this girlfriend you can move. Okay, and this direction is showing this thing. So you're starting with A. So you discover your first girlfriend, that is A. And after discovering A, you are not satisfied with A only. You discover another one, B. Okay, and after B you discover another one, C. After E, you have two options. Either you can go to D or you can go to C. Which one would you like to go? You can reply. Which girlfriend you like to go with, C or with D? You can reply, please. You can reply, please. Now it's your choice. Definitely don't write I want to go with both of them. Okay, you want to go with C. So at fourth time you discover this node, C node, and after C node you can discover the F. So after discovering F, you cannot go further, you need to finish with it. So you finish at 6 unit of time. From C also you cannot go further now, so you need to finish with it. And here I cannot mention the finish because from E I can go further to D. So this will be 8th unit of time. At 7th unit of time I finished with C, and at 8th unit of time we find out D, new one. And from D I cannot go further, so this will be 9. Finish with D. With E also I cannot go further now, so this will be 10, and this will be 11, this will be 12. That's it. This is how DFS algorithm is working. That's it. Okay, so this is all about the DFS. Now you can try this question. You can try this question now, and you can reply the answer. Okay, so this is GATE 2008 question. So you need to tell, okay, a DFS is started at node A. Let's suppose we are starting at A, and the nodes are visited in the order they are first visit. Which of the above is the possible output? So the sequence of visit, first met, discovery time they are asking actually. Based upon the discovery time, they are asking the sequence of the nodes. So based upon the discovery time, and you are starting from A, let's suppose. Please try this. If you will solve this GATE question yourself, then more confidence you will get. In the same lecture, you will be becoming able to learn the concept, and here itself you are solving the GATE questions. This is what we are doing in the our premium course also. Okay, so GFG is also providing the GeeksforGeeks is also providing the GATE course at very low price. Actually, you can check out that detail. You can find out. You can write in the Google GeeksforGeeks GATE course, and then there you can check out. Otherwise, in the description also. So there you can find that course you can check out, and if you are serious about GATE, then that can help you. Otherwise, if you want free content, then this GATE crash course, which is also helpful to at least clear the GATE exam or revise the important topics, that is free of cost. You can check in the detail in the description. You can check that also. So option, which is option 4? Sachin says that option 4. Sachin को ज़्यादा ही clear हो गया है. Sachin, you are saying second, third, and first. I'm little bit okay. Let me check out the answer first. I think, yeah, B is the answer here. So your two options are right actually. B, second and third is right. These are the right sequence, but A is not the right sequence. So this is not the right sequence actually. Let's check out if this is the right sequence or not. So first we discover A, okay. Then we discover B. See, directly B आप देख सकते हो. तो A से B पे गए, B से कहाँ पे गए? B से E पे जा सकते हैं क्या? हाँ, जा सकते हैं, क्योंकि ये अनडायरेक्टेड ग्राफ है, तो यहाँ से वापस भी जा सकते हैं, आगे भी जा सकते हैं, कहीं भी मूव कर सकते हो. तो यहाँ से यहाँ पे गए, ओके. यहाँ से जा सकते हैं, बिल्कुल जा सकते हैं. और ए से बी पे गए, बी से ई से एफ पे जा सकते हैं क्या? हाँ बिल्कुल जा सकते हैं, कोई प्रॉब्लम नहीं है। एफ से डी पे, एफ से डी पे, भाई एफ से डी पे कैसे जंप करेंगे? सीधे सीधे कैसे जंप करेंगे? सीधे कोई कनेक्शन नहीं है। एफ से डी पे जाने के लिए या तो मेरे को वापसी करनी पड़ेगी, या मैं किसके थ्रू जाऊंगा? जी के थ्रू जाऊंगा। तो जी पहले आना चाहिए डी से, जी पहले आना चाहिए डी से, तो पहला ऑप्शन नहीं हो सकता। दूसरा ऑप्शन देखते हैं, चलो दूसरा ऑप्शन देखते हैं। सीधे सीधे ट्राई कर सकते हो। ए से बी पे जा सकते हैं क्या? बिल्कुल, ये गए। बी से ई पे बिल्कुल जा सकते हैं। ई से एफ पे, ई से एफ पे बिल्कुल जा सकते हैं भाई। ई एफ से सी पे, एफ से सी पे जा सकते हैं, सीधे कनेक्टेड है। और सी से जी पे, देखो अभी अपने को जी पे जाना है, बिल्कुल जा सकते हैं, क्योंकि सी से और कहीं नहीं जा सकते। और सी से हम कहां से आए थे? हम एफ से आए थे, तो एफ पे वापस जाएंगे, हमें पता है हम बैक ट्रैक करते हैं। कहां पे बैक ट्रैक कर सकते हैं? जहां से आए थे वहीं से बैक ट्रैक कर सकते हैं ना। आप एफ से आए थे तो एफ पे वापस गए, अब एफ से जी पे जा सकते हो। तो एफ तो हम ऑलरेडी कवर कर चुके हैं, तो सी के बाद हम जी कर रहे हैं, बिल्कुल कर सकते हैं, सी के बाद जी कर सकते हैं, उसके बाद डी, यस वो तो सीधे ही कनेक्टेड है। तो ये वाला ऑप्शन बिल्कुल सही हो गया। ऐसे ही आप बी 3 और 4 भी चेक कर सकते हो। 3 इज द राइट आंसर, 4 is the wrong answer. So these two are the right options. So B is the right option actually. So I just give you the idea. So 1 is not the right option, GATE aspirant. You are also giving the same one we have already discussed. That is not possible. How I can come from F to D directly? I cannot come. I need to go through G. So G must come before the D. Okay, so 1 cannot be the option, 1 cannot be the right option. Okay, okay, so okay, thank you for reply. So let's move to the next question. This is GATE 2014 question. So this is the this is the okay, it's okay. So you can try this question. Okay, you do not need to try right now, you can try it at home. So let me, you can comment, you can write the answer in the comment section. Okay, for these questions I'm stopping it here for some time. You can read the questions and you can answer them in the comment section. Okay, so let's discuss about the applications of BFS. So these are the applications. One application of BFS is finding all nodes within one connected component. So let's suppose I give you this graph. So I ask you, in this graph, this is one connected component, this is another connected component. How many nodes are there in one connected component? 4 are here. Here how many? 2 are here. Can you count this? Yes, with the help of BFS we can count. इसके ऊपर BFS अप्लाई करो एक बार, जितने एलिमेंट्स क्यू में जाएंगे वो उतने इसके नोड्स हैं। इसके ऊपर दोबारा फिर अप्लाई करना पड़ेगा, जितने एलिमेंट्स क्यू में जाएंगे वो उसके नोड्स हैं, दैट्स इट। साइकिल भी डिटेक्ट कर सकते हैं। साइकिल कैसे डिटेक्ट करोगे? अगर एक नोड से दूसरी नोड पे गए, दूसरे से तीसरे पे गए, तीसरे से चौथे पे गए, इससे फिर वापस पहली नोड पे आ गए, फिर पहली नोड पे आप पॉइंट आउट कर रहे हो, इसका एडजेसेंट ये हो गया। दोबारा एडजेसेंट नोड तो देख रहे हैं, यहां से स्टार्ट किए थे और एडजेसेंट देखते देखते जहां से स्टार्ट किए थे वहीं पे वापस आ गए, तो साइकिल मिल गया अपने को। तो एक नोड अगर दोबारा विजिट कर दे रहे हो, घूम के वापस आ जा रहे हो, तो साइकिल है इसका मतलब। और ये भी चेक कर सकते हैं ग्राफ बाई पैराटाइट है कि नहीं। बाई पैराटाइट ग्राफ कौन से होते हैं? बहुत इजी है, कुछ नहीं है। बाई पैराटाइट ग्राफ होते हैं जिसमें सभी वर्टेक्स को ना हम दो ग्रुप में डिवाइड कर लेते हैं। जैसे कि एक ग्रुप ये हो गया, एक ग्रुप ये हो गया। ये टोटल एक ग्राफ है, इसमें सभी वर्टेक्स को ना 2 ग्रुप में डिवाइड कर लिया। एक ग्रुप ये है, एक ग्रुप ये है, और इन दोनों ग्रुप के बीच में ना एजिस जा रही है, यहां से यहां, यहां से यहां, ऐसे एजिस जा रही है। ठीक है, एजिस है, पर ना ये जो ग्रुप 1 है ना, इसकी जो वर्टेक्स है ना, इनके बीच में एजिस नहीं है। यहाँ पे एजिस नहीं है, ये इंपॉर्टेंट है। ऐसे ही यहाँ पे भी एजिस नहीं है। तो इस टाइप के ग्राफ को क्या बोलते हैं? बाई पैराटाइट ग्राफ। ओके, तो ये चेक करना है भी बाई पैरेड ग्राफ है या नहीं, तो उसके लिए भी हम BFS अप्लाई कर सकते हैं। ये तो बहुत इंपॉर्टेंट है, ये तो बहुत ही ज्यादा इंपॉर्टेंट है। फोर्थ पॉइंट, फाइंडिंग सिंगल और शॉर्टेस्ट पाथ फॉर अनवेटेड ग्राफ, वी यूज BFS, क्योंकि ये तो बेस्ट एल्गोरिथम है BFS इस चीज के लिए, तो इससे बेस्ट तो कोई है ही नहीं। फाइंडिंग डायमीटर ऑफ द ग्राफ, डायमीटर भी फाइंड आउट कर सकते हैं। डायमीटर क्या होता है बताता हूँ आप लोगों को, ये पिक्चर से समझ आ जाएगा। इस पिक्चर में देखिए डायमीटर, इस पिक्चर में डायमीटर इज 4 एक्चुअली। डायमीटर क्या होता है? डायमीटर ऑफ ए ग्राफ इज द लेंथ ऑफ द length between most distance nodes. So the most distance nodes are 2 and 7 here. तो इनके बीच में डिस्टेंस, इनके बीच का जो डिस्टेंस है ना, वही ग्राफ का, उसी को बोल देते हैं ग्राफ का डायमीटर। तो इनके बीच का डिस्टेंस कितना है? 1 2 3 एंड 4। तो जो नोड्स एक दूसरे से बहुत सबसे ज्यादा दूर है, उन नोड्स के बीच में कितनी एजेस आ रही है वहां से वहां तक पहुंचने के लिए, तो उस टोटल नंबर ऑफ एजेस को हम बोल देते हैं डायमीटर ऑफ द ग्राफ। तो ये भी हम फाइंड आउट कर सकते हैं BFS की हेल्प से। एंड दीज आर द एप्लीकेशन ऑफ DFS। जो ये आप स्टार्टिंग वाली देखोगे ना, स्टार्टिंग वाली ये सब मैच कर रही है, इतनी तो सब मैच ही कर रही है, यहां तक तो सब मैच ही कर रही है BFS से। ओके, उसके बाद टोपोलॉजिकल सॉर्ट इसमें एक्स्ट्रा आ गया, और ब्रिज आप फाइंड आउट कर सकते हो, और ये भी सेम है डायमीटर वाला, BFS वाला। तो ये दो एक्स्ट्रा लिखी है, ये वाली और ये वाली। ब्रिज क्या होता है? तो ब्रिज देखो क्या होता है, मैं इसको इरेज कर लेता हूँ। ब्रिज फाइंड आउट करने के लिए भी हम DFS का यूज करते हैं। जैसे कि ये हमारे पास एक ग्राफ है, ठीक है, ये ग्राफ है। इस ग्राफ में ना इस नोड को हम क्या बोलेंगे? ब्रिज। क्या बोलेंगे? ब्रिज। ओके, क्योंकि इसके टूटते ही ये ग्राफ डिस्कनेक्टेड हो जाएगा। ओके, सो इसको फाइंड आउट करना है तो DFS का यूज करो। और टोपोलॉजिकल सॉर्टिंग ऑल्सो। टोपोलॉजिकल सॉर्टिंग क्या होती है? जब तक प्रीवियस नोड्स विजिट नहीं होती, डिपेंडेंट नोड्स नहीं विजिट होती, तो आगे वाली नोड हम विजिट नहीं कर सकते हैं। ओके, so in topological sort, graph traversal, each node V is visited only after all the dependents node are visited. Okay, so these are the applications of BFS and DFS. And this is the last question I'm taking from you people. If you will give the answer, just give the answer and then we will find out. That's it. Last question for you people for today. And if you can answer this question. So you are right, actually GATE aspirant, C is the right answer. Both are the applications of the BFS. Yes, you are right. So C is the right answer. And you can try this. This GATE out 2016 question. Sachin says C for previous one, I think. This one, what is the answer? This one, what is the answer? So let me take meanwhile one question. Meanwhile, you try this question actually you solve. And GATE aspirant is saying that okay, I'm getting tension due to the exam is approaching. So yes, that is natural. Don't worry, that is natural. You are that is natural actually if you are getting tension. But what you can do for that actually is just see that, just make a schedule now onward. Just make a schedule, forget about the past, whatever you have done till now, please forget about that. And now make a chart and hang it on the wall in the room, or maybe if you are in your home, you can hang it on the wall. You can show to everyone in your family, okay, I will follow this chart now onward. You can tell your sister, at definitely you have to tell your sister or your friends, I'm going to follow this chart. And उस चार्ट में आपको लिखना है आप क्या क्या करने वाले हो पर डे के हिसाब से. Mention that thing for next 1 month, what you are going to do, and what you are going to do, that you need to decide yourself. इस टाइम पे तो वैसे आपको जितने क्वेश्चंस आप लगा सको वही सबसे बढ़िया है. क्वेश्चंस जितने लगाते रहो, PYQs या फिर टेस्ट सीरीज, दैट इज द मोस्ट इंपोर्टेंट थिंग यू कैन डू. ओके, I'm a hostler. Okay, you can tell your roommate that I'm going to follow this, so that he will keep poking you. You are not following it. You are not following it. Okay, okay. Best of luck for your exams, and lage raho. Definitely you will get the good results. That's it. Okay. Thank you everyone for joining. Now I'm ending the session.